All right, we'll get started here. Welcome everyone. It's great to see everyone, some familiar faces and some new faces. My name is Sean Collier. I'm the current president of the North American Weather Modification Council. Let's see, I want to thank Kayla and the Idaho Department of Water Resources for the lend of this room. It's a beautiful facility, and Kayla for doing all the legwork of setting this up and getting everyone to come together. I think we're going to have a great day today. We have some goals today. We want to talk about weather modification or cloud seeding. And generally, those terms, you'll hear both of those terms used. And generally speaking, you can use those terms interchangeably. But sometimes there's a few little nuances there. So you'll hear us talking about that. We're going to go through why do a cloud seeding project? What is it? What do we know? What don't we know? And just go through the process. If you're thinking of doing a cloud seeding program, we'll talk about going through and picking out a site to do that, a target area, and checking to see to make sure that's working, the effectiveness of it. So we have some really good, probably the foremost experts in the country and among the world here in this room today. So we're really fortunate to have that. I'll just talk really quick about the North American Weather Modification Council. We're co-sponsoring this with the Idaho Department of Water Resources. Our mission, and I didn't get it in time, this didn't copy and paste over correctly. Our mission is to advance and promote the proper use of weather modification technologies through education, research, and education and research. So we have many members. We formed in 2011, and I'm the current president. I represent the Southern Nevada Water Authority as a member. Jake Sarago is here in the room here back there. He's our vice president. Mike Schneider is our secretary, making sure everything's being recorded. And Julie Gonzar is our past president with the Wyoming Water Development Office. You can make it today. So our members are comprised of agencies or entities that have, they have regulatory, operational, or programmatic controls over weather modification projects in their states or provinces. We have some, we had some folks from, I think, Canada at one point as a member. So any agency associated with weather modification. So here you see as a list of the members from all over, mainly the Western United States. So just really, really fast, I know there's some other folks doing one-on-one talks, and you might see this picture a few times in other presentations. The origins of cloud seeding. So this concept was first discovered by a person named Vincent Schaefer and another person. He's the guy looking at the. So what you're seeing here on the left is it's basically a chest freezer, to simplify the terms, where they had a icy fog in there, and they put some materials in there to see if they could get the fog to turn into the precipitation. So you have Vincent Schaefer looking in the chest. You have Bernard Vonnegut there. He's the brother actually of Kurt Vonnegut, and that's Irving Langmuir, I believe. So it was after World War II, and they from the story I read is Schaefer was he was investigating icing on aircraft, which was. Being up here, you're very familiar with that. You're always being de-iced and everything. But they were researching that and noticing the the behavior of the particles in the clouds and how they were icing, and then it sort of came up with an idea. It's like, well, can we make this come out of ice out of the sky? So they later used a modified B-17 bomber, and they dropped some dry ice out of the plane. And that picture on the right is you can see the effect in the cloud bed there. Just coincidentally, This was in, I think, Schenectady, New York. I grew up like literally across the river from the laboratory for General Electric, where they developed that, and this test was done, I believe, over the Berkshire Mountains in Massachusetts. So I consider myself the relative newcomer to this science, and so I think people will go into a little more depth on it than that. But I've found like talking about the purposes of cloud seeding. You're going to hear about warm season cloud seeding, that's used to increase precipitation. It can be used for hail suppression. It can also be used for fog abatement. We saw a really interesting project up in up in Medford, Oregon, where they were using using a balloon and some dry ice to sort of increase the visibility for aircraft to land. So there's all kinds of interesting purposes for this. Cold seeding is what mainly got me drawn into this world. That's to increase precipitation and snow. So you see this map here. I believe it's pretty up to date with a lot of the projects that are going on in North America. The green shapes are if they're doing it for increasing liquid precipitation or for hail abatement, and the blue is for the cold season seeding for snowpack. And I'll talk about more specifically about some of the seeding that occurs in the Colorado River Basin later on today. But that's everything I have. I would just also add that as water professionals, we always look at the hydrologic cycle. You learn about that in school, and there's you have in a given water basin, you have inflows of water coming in, and you have outflows of water. A lot of when the question comes up of if we have too many people or too many crops, how do we get more water out of this? The first answer is always like, okay, well, let's look at the out part. Let's do more conservation, which is great. Let's do maybe land fallowing to bring that back in balance. But cloud seeding is one of the only ways, or weather modification is one of the only ways that, without building a pipeline from somewhere else or diverting water from somewhere else, to actually bring a little more water from the input aspect of it. So that's what you're going to hear about today. And is it going to solve all the water problems in a basin? No. It's a really good tool to have in the toolbox of water management, I believe. So you'll hear more about that today. And then I'm going to pass it off to Kayla for the first session.
All right, good morning, everyone. My name is Kayla Golden. I'm with the Idaho Department of Water Resources, and I represent the Idaho Water Resource Board as their cloud seeding program manager. So as your host today here in Boise, I will be your tour guide this morning. I'm going to walk you through the agenda and what we have for you today. I'm going to start by saying, this workshop that we have put together, I've asked each of our speakers to take a step back and think about, if I were a water resource manager, if I were a stakeholder or a policy leader who has never been exposed to cloud seeding, and I've been asked to either approve funding, to start a program, or to contribute in some way, what are the basic things that I would want to know? And so today we put together about 3 different panels for you. This first panel is going to go over the basics of cloud seeding 101, the current state of the science and what type of operations. We'll do a break at 10:15 and wrap up the cloud seeding 101 portion, and then cover some environmental topics and do our question and answers. So the next panel that we will have is on developing a program. And this is not meant to be sort of a step-by-step for how you develop a program, but it's rather a comprehensive collection of all of our expertise, all of us who have participated in cloud seeding over the years. And this is basically all the information that we put together that we feel would be useful for somebody who has never been exposed to cloud seeding before and may be considering developing a program. So we'll cover some of the basics of breaking ground, feasibility and design. After lunch, we will break at 12. After lunch, we will continue with developing a program and cover some of the basics of program implementation, monitoring, and analysis. And this does include how do we evaluate cloud seeding, what is the increase in precipitation, or how do we know what the impact is. In the afternoon, the last portion or last panel that we'll have for you today is the collection of our existing programs. So you'll hear from program managers across different states on how they operate their programs, how they started, how they're funded, and some of the challenges that they've faced as well. And so our last panel that we'll have, the final Q&A, will be for the entire workshop, a chance for folks to ask questions of our speakers today.
Okay, so everyone complains about the weather, but today you're going to hear about people that actually do something about it. You're going to hear from top scientists, longtime operators, enthusiastic project sponsors like me, with collectively hundreds of years of experience in this field. I want to add one thing to what Sean said. The Council, the North American Weather Modification Council, we've actually been meeting since the 1970s in one form or another, but in our latest incarnation is when that's what Sean was talking about. I want to set some expectations. If you think that I'm going to put in some money up here and it's going to end up with acre-feet of water with my name on it over here, that's just not going to happen. What we're going to do, we're going to talk later about the cooperative agreements, models of cooperative agreements, just like on the Colorado River, for example, where everyone agrees it's system water. And the science also isn't there. We can't quantify what's going on and identify. We identified all the links in the chain that need to occur when someone says, I'd like to do some seeding in this area, and then here we have the output over here, but there's still work that needs to occur on a lot of those links. We've been able to prove some of them, but others, the science isn't there yet. But today you're going to hear about the state of the science, and you'll know what we know and what we don't know. The bios of the speakers are in your packet, and so I'll just introduce the folks as they go. One final thing, one final story. So I started a program at the Winter Park Ski Resort in Colorado, and they were very happy with it. And then I thought, well, let me start one here at Telluride. And so I asked Winter Park if they would come with me. Will you come with me and tell Telluride how much how much you like the snow that we've been generating? And they said, are you nuts? This is our secret weapon. We believe this is what gives us the edge. I'm not going to go help you. I help our competition. And so that's a testimonial on how folks really like what we're doing.
So I'll be talking today. I'll probably be giving the only talk that doesn't have anything directly to do with cloud seeding. I am tasked with discussing some of the basics of cloud physics, what we know about cloud physics, which will set the stage for the later talks that you'll be seeing this morning in regards to how do we actually modify clouds, right? Because we start with a base state of how clouds evolve naturally, and the idea behind cloud seeding then is how can we modify them in such a way to alter their evolution and produce precipitation that otherwise would not be produced. So I'm going to start very basic. When we look at a cloud, what is a cloud? What is it made up of? Okay, what do we see actually when we look at cloud? Do we see water vapor, or do we see particles, or what is it? And are all clouds the same, right? Are they made up of the same thing? And short answer is no, they're not. Some are made up of ice, some are made up of liquid water droplets, some are made up of combinations. The cloud on the right is almost entirely ice. The cloud on the left is almost entirely ice. The one on the right is almost entirely liquid. And what we see is we're actually seeing those small particles in the cloud, okay? We're not seeing the water vapor in the air. Water vapor is invisible, okay? How do clouds form, and why do clouds form, okay? Clouds rely on natural processes that are occurring in the atmosphere, and kinematics in the atmosphere that lift the air, cause the air to cool, and lead to the formation of a cloud. So rising air is important to the formation of a cloud because when air rises, it expands. Okay? You take a balloon and you put it in your car and you drive up to the top of a mountain. That balloon is going to get larger because the air pressure is lower around it. As that air expands, it cools. It cools not because the air around it is cooler. It cools as a basic principle of physics that when you expand a gas, that gas cools. Okay? As that gas cools and the temperature drops, okay, the relative humidity in that balloon is going to go up. And as the relative humidity increases and gets closer to 100%, when it reaches 100%, okay, the water vapor that is in that balloon will begin to condense. And then we have a cloud, okay? It will be composed of liquid water droplets, condensed water droplets that form from the water vapor condensing, and we have a cloud. Okay, so most of us probably know some aspect of this story already, okay? What's the big deal, okay? Clouds are made of tiny droplets or ice particles The real question is not how the cloud forms, but how do we get from a cloud that is composed of very, very tiny water droplets or ice crystals to particles large enough to fall out of that cloud and form precipitation. So this schematic shows the small circle in the lower left as a cloud droplet. Okay, a cloud droplet is typically 10 microns or so in diameter. We cannot see a cloud droplet with our naked eye. Okay, we look up in the sky and we see clouds, but we can't see an individual cloud droplet. We can see a whole bunch of cloud droplets together that are reflecting the light. Okay. If you take a cubic centimeter of air, so we're talking about a packet of air that is roughly a half an inch by half an inch by half an inch, there are 1,000 cloud droplets in that cubic centimeter of air. Okay, maybe 100, but there's a ton of them. There's a lot of them. Okay, to go from a cloud droplet, which will follow the air motion and won't actually fall out of the sky, to a drizzle drop, which is maybe 100 microns. So it's 2 orders of magnitude, or it's an order of magnitude larger. It takes 1,000 cloud droplets to make up 1 drizzle drop. Okay, and the concentration of drizzle drops in that same cubic centimeter of air goes from 1,000 cloud droplets to about 1 drizzle drop per cubic centimeter of air. So there's a lot fewer drizzle drops. And that makes sense, right? Because you need a whole bunch of cloud droplets to form to make that drizzle drop. Okay? But even a drizzle drop, it doesn't fall very fast, right? If we're talking about producing precipitation or thinking about a useful amount of precipitation, okay, a drizzling cloud is probably not going to get us there. We need a cloud that actually produces rain, which is the large circle in the bottom right. And now a typical raindrop is 1 millimeter in diameter. Okay, and it takes 1,000 drizzle drops to make 1 raindrop. Okay, or if we think about going from a cloud droplet to a raindrop, it takes 1 million cloud droplets to get to run 1 raindrop. Okay, and the concentration of raindrops is 1 per liter, which is 1,000 cubic centimeters. So you take your little cubic centimeter and you get 1,000 of those, and you might get 1 raindrop in there. Okay, so the challenge in natural clouds or in cloud seeding is how do we get from these small particles that make up clouds that form very easily to these large particles that actually fall out of the cloud. And to answer that question, we need to know something about the processes that actually allow us to go from a cloud drop to a raindrop. And that's what I study. Okay? So let's take a couple of steps back first. Let's consider 2 types of clouds. That last slide I was talking about all liquid clouds. Okay? These clouds generally exist anytime the temperature throughout the cloud is warmer than about -5 or -10 degrees Celsius, 14 to 23 degrees Fahrenheit. If the cloud is contained in a region that is entirely warmer than that, or the entire cloud is warmer than that, most of the time your cloud is going to be all liquid. That's actually easy. We're going to start with that problem first. The other type of cloud are clouds that are made up of both liquid and of ice. Okay? We call these mixed phase clouds, and these are much more difficult. But these are the clouds that we deal with most of the time, especially here in the Intermountain West. These clouds have some portion of the cloud that exists at temperatures colder than, say, -5 or -10 degrees Celsius. It may not be the entire cloud, but if the top of the cloud is at colder temperatures, at, say, -15 or -20, chances are it has some ice in it, okay? And it also is very likely that the entire cloud is not ice, but there's actually a mixture of liquid and ice. We're going to talk about why that is. These clouds are really hard, but they're really important to precipitation in the mid-latitudes. Okay? So what this looks like schematically here is on the left-hand side, we have a cloud that exists with a top that's only extending up to about 23 degrees Fahrenheit, okay? And that cloud is entirely liquid, okay? It's super cooled liquid because it's below 0 degrees Celsius or below 32 degrees Fahrenheit, okay? But it's liquid. And then we have this cloud on the right-hand side, right, that extends a little bit higher into the atmosphere to colder temperatures, and it is composed of both liquid and ice. But we can see, you know, at least in this little cartoon, that the liquid can occur even at very, very cold temperatures in the same regions where there's ice. And this is important. This will be important in terms of understanding processes. And then there's somewhere between these two where a cloud might have some ice in it or it might not. And we'll find out later in this morning's discussions that those types of clouds are often the types of clouds that are really targeted. Or at least they've been targeted in the scientific studies to understand what's going on in cloud seeding. So let's start with all liquid clouds, okay? We already set the stage of, hey, how do we get to these small cloud droplets to large, or to a raindrop, okay? And it's really, actually, it's quite simple in terms of understanding the physical mechanism. So we begin on the left-hand side of this schematic with a field of very small cloud droplets, okay? And these cloud droplets differ in size a little bit. Some may be 10 microns, some may be 20 microns. And if they have a little bit differential size, they'll fall or they'll move around a little bit differentially in speed. And if there's turbulence in the cloud, it can cause those cloud droplets to collide, okay? And when cloud droplets collide, some of them will coalesce. When they coalesce, they come together and they form a bigger drop. And that bigger drop will fall maybe even a little bit faster, and it will collide with other cloud droplets. And it's a cascading process, okay? So as the particles get larger, they fall even much faster relative to the particles around them, and you can grow to a raindrop size. Very simple concept. So if we look at, let's say, a cumulus cloud, we start at the cloud base with condensation that is occurring, and small cloud droplets form as those cloud droplets, as that region rises through the cloud, and you get different cloud droplets that begin to collide and coalesce. They grow larger, and eventually they fall out of the cloud, okay, as raindrops. And they fall fast enough that they can fall faster than the updraft is pushing them up, okay? Condensation followed by collision coalescence can be a very slow and inefficient process. It can also be a pretty quick and efficient process, but it needs a couple of things, okay? This process works best in warm clouds that have lots of water, okay? So we see this in the tropics. We see this in the southeast United States, in Texas, okay? Where there is a lot of water present, and these water droplets can grow very quickly. In colder clouds, okay, there's not as much moisture in the air, there's not as much liquid in the clouds, and collision coalescence is pretty slow and it's pretty ineffective. So if we have a cold cloud that's, say, -5 degrees Fahrenheit, and it doesn't contain ice, it contains only liquid, okay, the chances that we'll actually be able to grow cloud droplets to a raindrop size is pretty small, okay? There's not enough time, there's not enough liquid to do it. And in addition to the amount of liquid water, okay, how many droplets are present and their relative size is also very important. And this will come into play, I think, when there's some discussion later on about the actual process of cloud seeding. Okay, so the last part of the talk is, let's think about clouds that contain ice, okay? These are hard, okay? This is an order of magnitude more difficult in understanding the natural evolution of clouds because there's so many other processes that can occur. In liquid, it's simple. Condensation and then particles collide, they get bigger. In ice, there's competing processes between what's happening with the liquid and what's happening with the ice, okay? So everyone knows that ice melts at 0 degrees Celsius. If I take ice and I put it in a box that is 0 degrees Celsius or warmer, it's going to melt, okay? The same is not true about liquid. If I take liquid and I put it in a box that's 0 degrees Celsius or -1 degree Celsius, it's not necessarily going to freeze. And in fact, it likely will not freeze until I get it much colder, unless I add something to it, okay? So in the atmosphere, as has already been alluded to, okay, liquid water drops often exist at much lower temperatures than 0 degrees Celsius. And in fact, they'll exist at temperatures as cold as -40 degrees Celsius, which is also -40 degrees Fahrenheit, as it turns out, okay? Unless there is some particle that is added to that liquid drop, okay? And it could be dust, it could be smoke, particles, okay, that help that drop freeze. Turns out, though, that naturally in the atmosphere, these particles tend to be rather rare. So at relatively warm temperatures, below 0 degrees Celsius, and let's say warmer than about -15 degrees Celsius, it's a gray zone. Okay, clouds often contain both liquid and ice. And the liquid is much more abundant than the ice. There's a whole bunch of liquid particles, and there's maybe just a few ice particles. So why do we care about all of this? Whoops. Okay. Almost all of the clouds at mid and high latitudes, where we live, okay, are too cold to produce precipitation from liquid alone. We've established that. Some of these same clouds are generally mixed phase. They contain a lot of liquid and a little bit of ice. In these clouds, ice has an advantage compared to liquid in being able to grow. So if I take an ice particle and a liquid particle in the exact same conditions, that ice particle will have a distinct advantage to growing to larger sizes than the liquid particle. And this is known as the Bergeron process, or the Wegener-Bergeron-Feindescent process. Okay, it's not important. We can call it the Robin Hood process, because what's happening is this ice is stealing, if you will, the water vapor molecules from the liquid drops. Okay, it has to do with the vagaries of saturation pressure in ice related to water. But what this means is two particles in the same condition, liquid and ice, this ice particle is going to grow, this liquid particle is going to shrink. And water vapor molecules are essentially going to go from the liquid to the ice particle. And this ice particle gets larger and larger. Now imagine that you have a field of just a couple of ice particles and a whole bunch of liquid particles. These ice particles grow very quickly. And then they can begin to fall out of the cloud. And so the colder clouds are unable to produce precip through liquid alone. Ice particles are relatively rare in these same clouds, but they often exist at temperatures at least as cold as -15, okay? And if ice does form in these clouds below 0 degrees Celsius, okay, those few ice crystals will grow rapidly and very efficiently transform into falling precipitation. So we're zooming in on a cloud here, and let's start off and zoom in on a cloud that we have a small cloud droplet and a small ice crystal together. In reality, we have a whole bunch of ice crystals, or a whole bunch of cloud droplet and a small ice crystal. And the little red dots are water vapor molecules. And what happens, right, as we go through time as these water vapor molecules go to the large ice crystal, and that crystal gets bigger and bigger and bigger, okay? Eventually, it gets big enough that it begins to fall through the cloud. And when it falls through the cloud, it encounters other cloud droplets around it. And those cloud droplets attach to the ice crystal, okay? Getting that crystal larger and larger, and then eventually it falls out of the cloud as a snowflake precipitation, okay? In the wintertime, it falls to the ground as snow. In the summertime, it eventually falls into a layer that is greater than 0 degrees Celsius and melts and becomes a raindrop. So that's all I have for you. I will turn it over to our next
All right, let's
speaker.
thank Dr. Frank.
Good morning, everyone. I am so sorry I can't be there with you all in person. That is life, I suppose, and I am still happy that I can join you remotely to share with you some of the exciting things that are going on in the world of science with regard to cloud seeding. You know, I'll talk a little bit about how it works and some of these recent advances in the research, but I want to thank Professor French for laying the foundation of the cloud physics principles that are really the basis for how cloud seeding is meant to work. To get started, I just want to upfront run through 4 key messages that I'm going to be making in this presentation that I hope, if nothing else, you'll take away these 4 key messages. One is that recent studies have proven that cloud seeding works to enhance precipitation in winter orographic clouds. And there have been a lot of recent advances in modeling that are enabling us to do innovative research and improve our understanding of cloud and precipitation processes, including cloud seeding impacts. More research, though, is needed to advance our understanding of cloud seeding impacts in summertime clouds. And cloud seeding effectiveness will vary by storm and by location. So it's really important that we do feasibility studies, because just because we know that the concept can work doesn't mean it's going to work the same way and that's the same magnitude everywhere. All right, so getting started, I know Sean presented this map earlier. I just want to start out with that basic understanding of what is cloud seeding being used for, and it's typically a technology used to enhance precipitation. It is being conducted in many places of the Western United States, especially those shaded in blue are focusing on cold season or wintertime cloud seeding, generally in the mountainous regions. We also have places in North America focused on summertime cloud seeding, as shown by the green shaded areas. And it's happening around the world as well. And I just have a few countries listed here, but it's happening in many places around the world also. So starting off with winter orographic cloud seeding in particular, how do we seed winter storms? Well, there's 2 general modes for this type of seeding. The first would be to insert ice nucleating particles. As Jeff just explained, ice particles are not as high of concentrations as they could be in order to make that ice process as efficient as possible. Usually for this purpose, silver iodide is a commonly used particle because this ice nucleating particle has been shown to nucleate ice at relatively warm sub-freezing temperatures compared to where natural ice nucleating particles are forming ice. The other mode would be to create a supercooling effect to nucleate ice. And so this would be to use a material, generally dry ice or liquid propane have been used for this purpose, to create a really intense cooling that then brings that temperature down so cold that it nucleates all potential ice nucleating particles that might be occurring in the region. This second method has not had a lot of research on it lately, and so I'm not going to be focusing a lot of this, my presentation on it, but I will point out that there are some renewed efforts to look into this mode of seeding winter clouds. Otherwise, I'm going to really start talking a little bit more in depth about the silver iodide mechanism for seeding winter clouds. And just a quick note for those in the room, is there a way to mute your microphone? Because I'm getting a lot of background noise coming in, including cars driving by. It's a pretty sensitive mic. All right, so this is a diagram walking through the steps of the conceptual model for winter cloud seeding, especially with silver iodide. That first step is that we need a cloud to form. These clouds generally form over the mountains due to the airflow rising up and over the mountains, as Jeff mentioned earlier. We do not create clouds to cloud seed. So this is a very important first step that we need. The cloud also needs to contain supercooled liquid water. And so also, as Jeff walked you through, not all liquid will freeze immediately when it reaches that freezing point, and some will remain in that liquid form even though it's colder than freezing temperature. And so when we have a cloud with this type of condition, that's a sign that it's not as efficiently producing ice naturally, and it is a candidate for cloud seeding. So the second step then is to release the silver iodide particles. Typically this is done by an aircraft or by a ground-based generator. The benefit of the aircraft is that you can release the particles directly in the cloud or just above the cloud. The ground-based generator, depending on its placement and what the airflow is between it and the cloud, will vary in how well those particles can reach the cloud, which is why that third step, the dispersion step of the silver iodide, is an important one to pay attention to, is that in order for the cloud seeding to work effectively, we need to get those particles that are being released into the cloud in question. Once we get those particles into the cloud at the right temperatures that they will nucleate at, they will form ice. And as Jeff's recent animation showed, once you get ice forming in the cloud, the ice will rapidly grow larger into snowfall-sized crystals at the expense of that supercooled liquid in the cloud. And so that completes this entire process of going from the initial cloud that has some extra liquid in it to extra snow on the ground. We're basically converting that extra liquid cloud water into additional snow. Also, as Sean alluded to, you might hear about this a few times. This is just a brief step back in time to the origins of cloud seeding. This proof of concept actually came about in the 1940s. So this idea has been around for many decades. The photograph shown here on this slide from Life magazine is one of those early successes in showing this proof of concept that this liquid stratocumulus cloud could be converted to ice when it was seeded with dry ice in this racetrack pattern, which is not a very natural, pattern. So it was very clear evidence at the time that we could alter the cloud microphysics. But the real question then is, does that change in the cloud translate to a change in precipitation on the ground? All of those subsequent steps in the conceptual models proved to be very challenging to gain conclusive evidence on. Some of this is because of the fact that clouds are naturally variable. And so with large natural variability in clouds, it was hard to isolate what the effect of cloud seeding was versus what might have been something that naturally was going to occur. And over these years too, especially in the early years, there were much more limited observations and very limited computer modeling capabilities. And so that also limited some of the advances that could be made in these earlier decades. But if we fast forward to present time, first of all, we were in the field in 2017 in Idaho. We were based right there out of Boise, where you're all at now. And this project was called SNOWY, the Seeded and Natural Orographic Wintertime Clouds, the Idaho Experiment. We were able to collect, with modern day instrumentation, unambiguous signatures from cloud seeding. And in this case, we were focused on aircraft seeding. Some of the evidence that we collected here is shown in the Doppler on Wheels radar data that's animating in the center of the screen. In this particular event, the radar screen did not show much radar reflectivity because this supercooled cloud was not naturally producing much, if any, ice. So when we seeded along this aircraft track, that's the yellow line, the winds were blowing out of the southwest, so our aircraft track was perpendicular to the winds. So as it's seeding back and forth along this line, the seeding material, the silver iodide, is being dispersed downwind in a zigzag-like pattern. And Mother Nature does not produce zigzag patterns. And so this was very clear, unambiguous signature from the airborne seeding that you can see here on the screen now, that zigzag. This was This was a tremendous success and breakthrough for us to be able to collect these clear evidences of seeding, not only in the cloud, because we were flying the Wyoming King Air in the clouds to detect the ice formation and detect it with the onboard airborne radar, but we also got this information from this ground-based radar and from precipitation gauges on the ground. So we were able to really confirm that entire conceptual model from the initial ice formation all the way through to measuring and estimating snowfall reaching the ground. So this was one major success that took place in the last decade. Because of that, I feel confident saying that we've proven that conceptual model for winter orographic cloud seeding with silver iodide. However, there's still more research, of course, because as I alluded to in my key messages slide, cloud seeding does not work effectively in every cloud equally. And so a key question that we still need to better understand is where and when does cloud seeding with silver iodide work most effectively? And we also have questions forming about how effective is seeding with liquid propane? How do we confidently quantify those impacts of cloud seeding? Because not every case we're going to be able to readily see this zigzag pattern. Doesn't mean that there's not been a seeding effect. It just means that the cloud might be producing some ice in the background, and that makes it harder to detect that seeding effect with observations alone. Other questions are important as well, such as how does the cloud seeding impact stream flow? A lot of cloud seeding, especially in the western US, the ski resorts that Tom mentioned might be interested in the snowpack, but a lot of the water resource managers are interested in stream flow. And how cost effective is cloud seeding to augment these water resources? I will say there is some good news here as well, because our modeling and observational capabilities have also advanced in the last decade or so. And so we're working to address these questions and others with these new advances in computer modeling. So one of these initial breakthroughs in the computer modeling was demonstrated just over 10 years ago by Roy Rasmussen and his group, when they were running these high-resolution multi-year simulations over the Colorado headwaters region. So in this map here in the center, focused on Colorado, you can see the mountainous region outlined in the red box. That's the Colorado River headwaters. They were running over that domain these high-resolution simulations down to as fine of resolution as 2-kilometer grid spacing, and comparing that with observations from SNOTELs, or snow precipitation gauges in the mountains, shown here on the right. So this is all on the same color scale. And if you look at this first panel where the grid spacing is 36 kilometers, which some of our forecast models and our climate models rarely even can get to this scale too. This is that core scale that we were limited to before supercomputers, versus a 2-kilometer. You can see a very different picture in what the annual precipitation accumulation looks like over this mountainous region. On the left, in the northern Colorado region, we're getting maybe 300 to 350 millimeters of precipitation, and it's a very blocky pattern. In the center, we actually have a pattern that looks kind of like a topographical map, because the topography itself, that's the driving force for these clouds to form. So it makes sense that the clouds and precipitation would fall in a way that looks like the topography itself. And if we're looking in that north central Colorado region here, we have points in excess of 1,000 millimeters, which does line up with some of the point measurements that we have from the snow gauges. So this was really a major breakthrough, showing that we can now realistically simulate this precipitation in the mountains. And because supercomputing continues to increase at a rapid pace, we've gone from this just over 10 years ago to now running over the entire continental US for 40 years at 4-kilometer grid spacing. So this is providing us a lot of new insights into clouds, precipitation, and a whole bunch of other atmospheric features. And I know there'll be more presentations talking about this CONUS 404 type work later. But this was an initial breakthrough. From there, we then decided if we can simulate these clouds and precipitation over the mountains well enough at high resolution, maybe we can start to actually simulate seeding as well. So we built the WRF WeatherMod model at NCAR, where we now have a capability to simulate the physics of silver iodide seeding. So in this animation, it's showing 2 mountain ranges, with the white being those orographic clouds with supercooled liquid water forming over the mountains. And then the animation in the cyan color shows the silver iodide particles that are being simulated in the model. Here they're being released at an altitude where an aircraft might fly. They disperse into the cloudy region and form ice, which is yellow in this animation. You'll see it here in a minute. It's coming through, it's embedded within the cyan right now, so it's forming a lot of ice, and then it's producing snow as well. You'll see the snow, which is the green color, show up around other parts of this animation also, because this model, the Weather Research and Forecasting, or WRF model, was developed to simulate and forecast natural weather phenomenon. But what we can do with it now that we've got this seeding component in the model is we can run a simulation like this with seeding, and we can run the exact same simulation without the seeding, and we can look at the differences. We can map out spatially the amount and the locations of where the different precipitation is falling so that we can try to better quantify what the impacts of seeding on precipitation are, and do it in a controlled experiment. The other thing that's been happening besides the development and the realization we can simulate precipitation in complex terrain, and we developed WRF WeatherMod, in parallel to all of this, NCAR scientists were developing a hydrological model that was able to be driven by WRF forecast model output 2. We call this WRF Hydro. And this model simulates the spatially distributed runoff and stream flow from the WRF output. And so what we've been doing with all of these things combined is building capabilities to simulate cloud seeding impacts, not just on the precipitation that would be the output of WRF WeatherMod, but then we're using that to try to drive WRF Hydro and simulate the impacts on stream flow, because that was another key question for many stakeholders interested in cloud seeding. So this is kind of the state of the science. This is where we are today. These are some of the new capabilities that we're building, testing, and improving upon to be able to quantify the impacts of cloud seeding. So I'm going to take a moment and switch gears to summertime storm cloud seeding, since we're trying to be comprehensive here in this workshop. And I'm going to take a first step and just say there are also two modes for seeding summer storms in general. And the first is going to sound like I'm a broken record, because it's to insert ice nucleating particles, and silver iodide is common. This is the same thing that I just mentioned for winter storms. This is also a method that is utilized for seeding summertime storms as well. The other method for seeding summer storms is to insert hygroscopic particles at the cloud base. And these are typically calcium chloride or salt powders, and I will talk a little bit more about this in a moment. But first, I want to walk through this idea of why can we target a summer storm the same way that with the same materials that we might target a winter storm, using silver iodide to insert these ice nucleating particles. And it goes back to this fact that summertime storms are generally convective, which means they build deep and upward. And they do have regions in them, once they get to high enough and deep enough clouds, high enough altitudes, that are sub-freezing temperatures. And so they still also have the likelihood for supercooled liquid water in the cloud. So the basic concept here is very similar to that basic concept of winter storms in this idea that we're trying to convert more of that liquid water into ice to enhance the ice-based precipitation process. Unfortunately, I will say that this conceptual model for enhancing precipitation in summertime convective storms is not well proven, and I will walk you through some of the challenges for why that is in a few slides. The other mode, which we refer to as hygroscopic seeding, has to do with some of the principles that Jeff was presenting on before me about, in order for the warm rain formation process or the collision and coalescence process to be efficient, we really need to have a variety of cloud drop sizes, including some large cloud drops that can fall fast and collect a lot of smaller drops on the way. On this left photo or diagram here, when we have drops that are similar in size, they all fall at the same speed and they don't really collide and collect with each other very efficiently. So the concept with hygroscopic seeding then is that if we're in a situation where we have less efficient processes like this middle diagram, we can then insert these hygroscopic particles at cloud base, and they go into the cloud, through the cloud base, through an updraft. And these particles then would help form larger droplets. So we're basically trying to add larger droplets that will help initiate coalescence processes and improve the efficiency of the warm rain formation. Now, this type of seeding can be done in clouds that do get deep and have colder sub-freezing portions to them, because there still is a part of the cloud that's warmer than freezing. But this could also be done in any cloud that doesn't have that sub-freezing portion as well. But those clouds are pretty hard to come by. Most summertime convective storms, in especially the mid-latitudes here in the US, will have a sub-freezing portion. But this could still be a method for targeting those. So the science on hygroscopic seeding also is not well proven, but I will say that we have some evidence that that initial step in the conceptual model has some support, meaning that in some cases we've been able to detect an increase in the drop size. We've been able to show that there are larger drops being produced in the seeded clouds initially due to seeding with the hygroscopic particles versus those that were not seeded. But this effect really depends on what that background state of the cloud drops was before seeding. So on the left, these were clouds that had more of a maritime aerosol background particle type. So they were already producing larger drops. They were generally cleaner. They had some sea salts in them perhaps, so that we don't really detect that effect in those clouds. But the clouds that had more pollution, more continental type influences on their aerosol, had a little bit narrower drop size distribution, so they did not have those large drops. And then in the seeded cases for those, we were able to show a statistical impact in the larger drops as shown here. But that's that first step. What happens then to get the precipitation to the ground? The impact on precipitation in these cases is still pretty unclear. There were some randomized statistical studies done on this in various countries around the world that were starting to indicate that perhaps the seeded clouds were living longer and over that longer lifetime producing more rain. But there's been some recent studies in the last few years showing that the way that those clouds and storms were being detected and studied was using radar, and that the way that the radar was being used to identify those storms was potentially introducing an artifact into those studies. And so there's still some discussion and debate on the validity of those. The other challenge is that we were struggling to come up with a physical understanding and hypothesis for why this longer lifetime effect was actually happening. And so this new study showing that there might have been a flaw in the radar analysis methodology kind of helps us understand that perhaps it was an artifact and not really a finding. So this all leads me to summarize a few of the challenges why we're struggling to have the advances in the science for summertime cloud seeding that we've had in wintertime. And one of the reasons is that summertime convective storms are much more short-lived. They can be on the order of 30 to 60 minutes sometimes, generally around an hour at the, is the average lifetime. And they have very vigorous updrafts compared to our winter storms that occur over the mountains. 1 to 2 meter per second, strongest updrafts in the mountain or in wintertime storms versus 30 to maybe even 40 meter per second in really vigorous summertime convective storms. So very, very different storms. And so that leads to challenges in timing seeding appropriately if we have a very short window to target. Challenges in detecting the impacts are even greater because those really vigorous updrafts make things happen fast and make things happen in a quite variable way. And so that large natural variability in how that convective storm evolves really muddies the waters in our ability to detect an impact that was directly due to seeding and not something that was happening otherwise. Another challenge that we have is that our model simulations, which have come a long way, we've shown them to be able to reproduce the precipitation over the mountains fairly well. They do still struggle with convection, the size of it, the strength of it, and the exact location of it, because it's usually much smaller in scale to these orographically driven storms. So we still have room for improvement in our modeling of convective storms as well. And then, especially with regard to hygroscopic seeding, we have a pretty limited understanding of what the background aerosol conditions are. This is also a challenge in our winter cloud seeding too, because there is an impact on our seedability of clouds and how the microphysics in the clouds behaves based on the aerosol background in winter. But this is especially important for that hygroscopic seeding hypothesis that, you know, as I showed, if you already have larger drops, are you really making much of an impact on the collision coalescence process? So these are areas that we really need to continue improving our research in order to continue improving our models and our understanding of these types of storms in order to see the same science advances in this area that we've been able to see in the winter clouds. All right, so before I wrap up, I have a few more points I want to make, and one of those is about cloud seeding feasibility. So, you know, as Jeff presented and I've mentioned, you know, we know that clouds can contain supercooled liquid water, and clouds with supercooled liquid water are generally candidates for cloud seeding in order to enhance that ice formation efficiency of snow, especially in the winter storms, as I focused on in the beginning of my talk. But we also know that these opportunities to seed how much supercooled liquid water might be in clouds and whatnot, that will vary from place to place. Some locations or even some mountain ranges are going to be more amenable to cloud seeding than others. And so it's really important that we study the climatology of weather and aerosol conditions, if the data is available, to determine when, where, and how to seed before embarking on a cloud seeding program. And not every storm is the same either. So even if you have a program, you're not going to necessarily be able to seed every storm. And so, for example, even how you might seed a given storm in one day versus the other day might change. In winter storms, for example, some might be better targeted by ground seeding and some might be better by airborne. So these are all reasons to really focus on looking at a feasibility study before doing a cloud seeding program. One other thing I was asked to speak about too, it's a very common question that we get that is based upon a physics principle of conservation of mass, is what are the extra area effects of cloud seeding? So if we seed in one area and there's extra precipitation that falls out, what's going to happen elsewhere? And conceptually, we generally rely on this conceptual diagram shown on the right that concludes that the effect outside of the target area is estimated to be very small. Furthermore, one of the reasons that the effect outside the target area is likely to be quite small is because over all these decades, it's already been challenging enough to detect the effect in the targeted area. And so with that effect in the intended area being relatively small, that extra area effect is even going to be more diffuse and dilute and harder to detect. So this conceptual model shown on the right is just a pie chart showing us the total water vapor that would be over a given region at any point in time. And not all of it is consumed to create clouds and precipitation. So if you have this whole pie chart being all of the water vapor at any point in time, and say half of it is used to create a cloud, we know that not all of the cloud is consumed to form precipitation, so we have a portion of the cloud that's then forming precipitation. And then if we're enhancing precipitation by a certain percentage, you can see that the slice of this overall pie that is being removed, the extra precipitation is removing from the total water vapor is quite small. But I will say that now that we have some of these new capabilities, especially with the computer modeling, it does present us with some new opportunities to better address this question because it is such a common concern. And on that note, I want to make another point here that I think coordinated and collaborative science is really needed to do this. A lot of our weather modification research over the past decade has focused on local and state level programs. This has been very successful. It's been a great example of how research is being co-produced by the researchers and stakeholders alike. That means that the engagement of local stakeholders helps us address questions that are unique to those local and state regions, and it ensures that the outcomes of the research are very usable and useful. So this has been a very successful approach in many of the states that we've been doing this research on. At the same time, there is also a need now for some coordinated research at larger, broader levels across regions and larger scale to address some of these larger scale and/or regional questions like extra area effects. And so in the early years, there was more federal agency support for cloud seeding research, and I think we're at a point now that we could also use more of that type of support so that we can address some of these broader questions as well as continue to address these local and state level questions. So I want to just summarize that we've made some significant advances in the science. The SNOWY data proved the conceptual model that cloud seeding can enhance precipitation in the winter orographic clouds. And we've had some modeling capability advancements, including the fact that we've shown we can realistically represent precipitation and atmospheric conditions in the mountains now. WRF Weather Mod was developed to simulate the impacts of cloud seeding on precipitation, and we're using WRF Hydro in a way coupled with WRF Weather Mod to simulate spatially distributed impacts of the precipitation on stream flow. So circling back to my key messages, the first two I just reiterated on that last slide, but I also want to remind you that more research is needed to advance our understanding of cloud seeding in summer clouds, and that cloud seeding effectiveness will vary by storm and location, so feasibility studies are needed, and we will be talking more about the feasibility studies later on. And then my last slide I want to put up is that we have developed a training module, so if you don't get your fill today and you want to take your own at your own pace, a 45-minute online training module, our COMET training program at UCAR hosts this wonderful catalog of training modules, and we've developed one on how cloud seeding works. The focus is on winter orographic cloud seeding. This QR code should take you to the website. The website's also shown on the slide, but it's a bit of a lengthy one. You will be asked to create an account, but it is free, and you'll have access to all of the training modules that are there as well.
First, I need to congratulate all of our initial speakers for their limited use of acronyms. This is a business that is pervasive in acronyms, and there have been very, very few used so far. So I will struggle to maintain that. As the indicator there shows with my email address, that's how you can reach me. When we talk about warm seeding, we typically mean clouds that develop in the summertime season, the spring or summer, convective clouds, clouds that occur when the atmosphere is unstable. The purposes are generally, as it has been indicated, increasing the precipitation, but though there's some hail damage mitigation programs here and there, I'm going to stick with the precipitation enhancement aspect of this. I want to start with our premise. And our premise is that nature is not always efficient in converting that cloud condensate that Sarah showed in that pie chart to precipitation. The efficiency of a cloud can be summarized by saying it's the precipitation divided by the total cloud condensate. So in that pie chart that Sarah showed with the cloud condensing half the water vapor, and then 2/3 of that, excuse me, being left behind as residual cloud, that would make the cloud about 1/3 efficient. When we observe rain showers and storms, the cloud never ends up on the ground. This little picture here I showed you shows an orphan anvil of a failed turret there. Yeah, then the upper part is the upper anvil for a successful thunderstorm. But this is cloud particles that will never reach the ground. Eventually they will sublimate or evaporate and return to the water vapor supply in the atmosphere. We have to be able to identify the inefficient clouds, the ones that have potential for seeding, and we also have to target them effectively and appropriately. So I'm going to talk a little bit about that. First of all, modifiable clouds, those that can be successfully altered in their microphysics so that they produce more rain, are characterized by certain things. One is they have to be cold. Dr. Tessendorf mentioned that below freezing is necessary. Most of the programs that use ice-forming particles, glaciogenic seeding, go with -5 Celsius or +23 Fahrenheit for that kind of a threshold. And these clouds are warm clouds let me start again. The warm clouds that we can target are comprised of cloud droplets that are too small to form raindrops. And that's already been discussed very capably by Dr. Tessendorf and Dr. French. But I'm going to spend just a moment on them here. We've already heard about ice nucleating particles, so we know what those are now. And the thresholds conveniently that I mentioned here are those mentioned by others. They vary a little bit within the scientific discussions you see, but these are numbers that are right in line with that. So just direct your attention here to the diagram. The updraft is on the left-hand side of this hypothetical cold cloud where condensation is occurring and we're getting cloud droplets in that kind of blue zone. We get colder than 0 Celsius or 32 Fahrenheit. We get supercooling, but no ice. We get up to, well, here it has 0 Fahrenheit or minus 18 C, but we start to get ice above that. Minus 18, minus 15, varies from case to case, could be even colder. In the upper part of the cloud, the ice then forms. It's got the advantage, the drop, as you would say, on the droplets get converted to ice. The particles grow through several different ice phase or mixed phase processes, get large enough, fall through the cloud. If it's warm in the subcloud region, we got rain. If it isn't, we have snow or ice particles reaching the ground. We've already talked about the collision coalescence process. This shows the larger droplet has the greater fall velocity. It catches up to the smaller droplet, captures it, and becomes a larger drop. We'll talk a little bit more about that later. For cold clouds, though, what we need to do is identify what the viable candidate is. This is for ice forming treatment, that is glaciogenic seeding. We want an updraft because the updraft is producing condensate, which condensate means more droplets, and the droplets are what provide for the growth of the ice hydrometeors. We want a lack of natural cloud ice. Dr. French noted that when you get cloud gets cold and it gets a lot of ice in it, then the nature takes over and it does the precipitation on its own, and you need supercooled liquid water within the cloud. There are other ancillary considerations, but I'm going to not go into the weeds on those today. This is a little graphic that shows about supercooling. In the lower left-hand side, you see a cumulus cloud there with a nice flat cloud base. You see some isotherms sketched out on the side. The temperature isn't the same at all the levels through the atmosphere because there's latent heat released by the condensation in the cloud, and so it's actually warmer in the cloud at the same altitude than it is outside. That's why you have the updraft, because there's buoyancy there from the latent heat release. And so right here for glaciogenic seeding, and we're talking here now, there's the fine print here says with ice crystal engineering pyrotechnics. The threshold for nucleation is shown in the chart above the cumulus cloud there. It's from tests done by Paul DeMott at CSU some years ago. The 4 degrees of supercooling is equal to -4 Celsius temperature-wise. You see a little bit of ice, 10 to the 11th ice particles per gram of seeding agent being produced at -4, but it jumps almost 2 orders of magnitude to -6. So on the cumulus cloud there, you'll see the -6 isotherm in green. What we tell our pilots when they're going to be top seeding is to fly so that you're seeding at above -6. The ejectable flare that you would release at cloud top will fly into the cloud and descend. And so initially, it's going to actually be releasing nuclei at warmer temperatures, but because it's in the updraft, it'll be carried aloft and cool anyway. So that in a nutshell is kind of the importance of supercooling. Without it, we can't create ice, and with it, well, I'll just go to the next slide here. Easier under explanation here, I guess. For cloud top seeding, the second thing we look for besides an updraft is the existence of the supercooled liquid water. The picture on the right shows what your windscreen would look like on your airplane after you fly through a cloud turret with supercooled liquid water. That water glaciates, freezes on impact at temperatures that we would see that, and so we get this accumulation of ice on the windscreen. The pictures above the cloud turret show examples of what would be considered a turret that's, well, it's visually clues that a turret still has an updraft and it's developing on the left with the green yes, and on the right, the updraft has weakened, the cloud development has stalled, there's mixing around the perimeter of the cloud, and that cloud is no longer growing, so you wouldn't want to seed that. So that's the second criteria. The third is the updraft itself. You want the updraft because it's an indication of buoyancy. As I said earlier, it's creating additional condensate that's building the cloud, and it's indicative of the cloud is still in the developing stage. You see in this diagram, the red arrows indicate the most likely indication or presence of the updraft. There will be different bubbles coming up in the cloud very often. In the early days of conceptualizing this back in the 1970s, I was thinking that, oh, there'd be a nice uniform updraft through the cloud, and we tried some field measurements with tracers that showed that it's not a single uniform updraft through the cloud. It's variable from place to place as different bubbles come up. So if you have, again, the supercooled liquid water, the updraft, and the lack of natural ice, then you've got a cloud that potentially can be seeded. We've already seen some really nice indications of the importance of the convective life cycle in this. All of the indications that have been shown show the, that's interesting. Those characters didn't turn out quite the same. Anyway, the small cloud, the developing cloud, is the one you want to target. A, has no ice, B, it's all updraft, and C, it's super cool. And so we see the minus, the 0 degrees Celsius line shown on there. Once the cloud is matured and made ice of its own, the process is already underway. There's no need to try and duplicate what nature's already done and waste your time with that. So focus on the middle-sized cloud, as was shown early on. This is an idea, a concept of a multi-cell warm season cloud. Instead of having the individual clouds as shown here in the left panel, if you stack a bunch of those at various phases of their development, various stages of their development next to each other, you'll get something that looks like this. The updrafts get stronger as you go from the small clouds on the left toward the right. The strongest updraft can support the largest hydrometeors and therefore has the greatest potential of producing hail. We don't want anything to do with that if you're flying an airplane to see the cloud. But what we see here in the pink is where the cloud temperature is colder than -15 and ice is likely to develop naturally. So that's places where nature's going to do the job and we don't need to go there. This is a similar diagram from a different source. The white area is what we would see, or the pilots that were seeding a cloud would see with their eyes. The shaded regions, the gray and the green and the yellow, are what a weather radar, a typical weather radar might see. And what we see here is the oldest cell is on the right at time 0 in the top panel, cell number 1. And in this particular snapshot, there's no updraft left, it's raining out. So that's a dissipating mature cell. Cell number 2 is mature also, and in the dissipating stages, but we see the core precipitation echo, the yellow, is still aloft. Cell number 3 is developing, but it has precipitation. If it has precipitation and it's a cold cloud in this part of the world, that means it has ice. And so nature has already created the ice in it. And then cell 4 is the cloud that is yet developing. It has only an updraft and no radar echo. And guess what? That's the one we want to go after. 10 minutes later, the picture changes a little bit. We go to the middle cloud. Cell 1 is now basically gone. There's a little bit of rain remaining to fall out. Cell 2 has the precipitation cores on the ground. Cell 3 is still aloft. Cell 4 now has a radar echo. And cell 5 is coming along. And then the same process again another 10 minutes later. So when you combine all those, you get a multi-cell thunderstorm that looks something like this on radar. This is I've discovered that when you look for this kind of a pattern with a vertical cross-section through a warm season storm, you can find it almost all the time. Because it's so common, it reflects so accurately what exactly is happening in the cloud. And so if we were to go further to the left on this, we would have clouds out there that would not have any radar echo yet, that would potentially be seedable. In this picture, I've highlighted in yellow the supercooled area that would be amenable to glaciogenic seeding, that is seeding with silver iodide and other similar compounds. You noticed I put a couple of airplanes in there. They are focused in these small clouds, not in the taller clouds. If they're going to go far to the right in that yellow area, they would be focusing on that smaller cloud turret in the foreground, not on the area in the pink in the background. And that's how you would target these clouds. You have to be very careful not to go, well, you don't want to go where ice is because you're wasting seeding agent, but if you go where ice is, you're also going into a part of the storm that's potentially electrified. And that produces, can produce lightning. And lightning isn't likely to down the aircraft, but it can cause damage. And the main concern is damage that would require an expensive inspection. So this is a view from above of a similar type storm. There are two areas that I want to draw your attention to. The yellow area that you see, the oval at the bottom of the storm, is the area where we would most likely be looking for supercooled clouds to see the cloud top. The green area is where we would see the cloud base. I'm going to go back one here because we see an airplane out there flying at cloud base also. There are updrafts there. You can release silver iodide or other glaciogenic agent at that location, and the updraft will carry it into cloud and transport it in the loft until it becomes supercooled and forms ice. So that's a very good way to seed as well. The cloud-based seeding, the aircraft that do that have to take care not to go into strong updrafts. If they do that, not only are they getting into clouds that probably already have ice above them, high in the cloud, but they're also in an area where hydrometeors from above could fall on the airplane without warning. So we don't want to go over there. So yes, we have more. Hygroscopic seeding. I haven't talked much about this. It's possible in this part of the world. The big criterion here is we don't worry about cloud top temperature much at all, but cloud base temperature is really, really important. It's already been said that you need a wet cloud, a cloud with lots of water in it. We've kind of parameterized that for operational purposes to say plus 10 Celsius. That's 50 degrees Fahrenheit for a cloud by temperature. And the reason we code it by temperature is because the ability of the atmosphere to have contain water vapor is directly correlated with temperature. And temperature is really easy to measure. And so if we measure temperature, we find a cloud base at plus 10, that means the saturation mixing ratio, the amount of water in the atmosphere is going to be very high. And we're likely to get a juicy cloud out of it. So if we can find that plus 10 C cloud that has the base that's nice and flat, doesn't have precipitation come out of it, and get into the updraft and seed with a hygroscopic material, a powder or a hygroscopic flare, one that might burn and produce small particles, then we can actually affect, hopefully, the cloud droplet size distribution in the cloud and create more larger drops. This isn't going to work in a situation where the cloud already has large droplets. That's been said once, I'll repeat it here. Hygroscopic seeding doesn't work every time just because you have a warm cloud base. There's a lot of situations, particularly in the maritime, near water bodies, where the cloud droplet distribution can be very large. Can have large sizes. I will share with you a current situation that our company is dealing with in the Middle East on the Arabian Peninsula. The humidity on over the Red Sea next to Saudi Arabia can be excessive, plus 30 or warmer, quite often. And with, when those particles come ashore, those condensation nuclei come ashore and form clouds naturally, you would think that they would produce large numbers of large cloud droplets. But interacting with all that, we have the desert aerosol. And this ties back to something else that's been mentioned, is the importance of the natural aerosols, the tiny particles that are in the atmosphere all the time that really govern what the cloud droplet size distribution is. And so the question for us right now, we're trying to make, we are making research measurements with an instrumented aircraft to really assess the aerosols there and the implications of those aerosols for the potential for hygroscopic seeding along the Red Sea. It may be that hygroscopic seeding won't be effective there. The jury is still out, as they say. We've already seen a version of this diagram, so I can skip through it or go through fairly fast. I do want to point out a couple of things. One is the CCN, that dreaded acronym for cloud condensation nuclei, is very small here, a radius of 1 micron. A typical cloud droplet of 10 microns is the blue dot. A large cloud droplet is 5 times larger. That's the size cloud droplet we'd be striving for with hygroscopic seeding. We want a bigger cloud droplet. And then we have the very bottom, just the edge of the big raindrop, the millimeter, or actually it's 2 millimeter raindrop there because I have R equals 1,000. Again, it emphasizes the importance of converting the small droplets into the large droplets. One other thing I'll point out is the difference between rain and drizzle isn't how wet you're getting, how fast, it's the size of the droplet. The drizzle drop you see in the upper left, this example is a 200 micron droplet compared to raindrop is much, much smaller. I've got very wet from drizzles before. Hygroscopic seeding, the premise here, we want similar things. We want the updraft. We want to seed at cloud base because the droplets for the cloud are first forming at cloud base, where that aerosol is rising into the saturated, supersaturated environment at cloud base. So we want to tuck ourselves in close and circle there. And we want, again, that warm cloud-based temperature. We experimented with this a little bit on the summertime program up in Alberta several years ago and found that plus 10 cloud base was hard to get up there. So we bent our regulations and went to plus 7, and we really didn't see a lot in terms of a reaction. One of the challenges for cloud-based seeding, hygroscopic seeding, is when you find that updraft, sometimes they're quite localized, and it's hard to keep the aircraft turning tightly enough to stay in that updraft. Because when you're seeding at cloud base, at least the way WMI does it, you're burning a hygroscopic flare, and you can't turn the flare on and off when you get out of updraft. It's going to burn whether you're in updraft or not. And so that's what we do. We'll repeat this kind of a treatment as long as the updraft persists, or until we have burned a sequence of 3 or 4 consecutive flares in the cloud. Then we'll move on to the next. So that's the gist of how we approach hygroscopic seeding. And so we've kind of covered the winter or the warm season stuff, Derek, and now for real, you get to talk about the winter stuff.
All right, we'll try this again. Thanks, Bruce, and everybody that went before us. You really set the stage for what cloud seeding is in the winter. Before I get going, I want to start out with an analogy of what we're trying to do here in the wintertime cloud seeding. What would happen if I go out and give one of you guys a 1968 Ford Mustang halfback? What do? You go make it faster, right? So you start strapping on parts. You put on a supercharger, you change the exhaust out, and you start doing all this other stuff to make the car faster. And then what happens? You still need to tune it. So you get out there, you get a mechanic in there, and you start tuning the car to make sure everything that's on it is working well, is working to the top of its ability, and then you can go out and you can start racing that car. In a nutshell, that's kind of what we're trying to do with the storms that we're cloud seeding in the wintertime. You got your storms that's coming across the mountaintops, your orographic storm. That's your car. That's your muscle car that's already there. And then what do? You start strapping on parts. So you have your aircraft receiving, you have your ground-based generators that you put up on the mountains. But that only gets you so far. Then you got to tune it. So where do you put those generators on the mountain? That's kind of starting your tuning. You put some weather equipment out there to see where the temperatures are ideal for seeding, and so where you can operate the stuff to the best. And you start to try to optimize that storm to make it the most efficient that it can be, just like you do when you have a sports car that you go out there and you try to make a little bit faster. So when we get into this, let's talk a little bit about some of these seeding apparatuses. So these are what we're strapping onto that car. Are they the superchargers or whatever it is? So we have aircraft and we have generators. There's different types of all of these. And these work at a little bit different temperature ranges. They'll work at a little bit different areas. So with the generators, we have three main types. And I'll get into all these three later. You have silver iodide remote generators. You have liquid propane remote generators. You have manual silver iodide generators. And there can be other stuff that you can add to this, but that's kind of the nutshell of some of the generators that can be used for cloud seeding. You also have aircraft, and they have different types of seeding apparatuses that you can put on the aircraft. They can be burn-in-place flares, they can be ejectable flares, or they can be wingtip generators. Or there's different stuff that you can start strapping onto that aircraft to try to use that to try to optimize a storm. So let's look at these a little bit and then start to kind of peel back where you want to put these in a storm or where these are the most efficient for when you're cloud seeding. Right here we have a silver iodide remote generator. So this is a generator that you can place anywhere on the mountain as long as you have permission to get there, and you need to be able to drive to it. So there's roads and stuff that you need to get to it in the summertime, but they can go pretty much anywhere as long as you have land to put them. And the ideal part about this is you can get them high. If you guys ever are up in the mountains in the wintertime, it's a cold morning, you get up and everybody's burning their wood stoves, right? And you go outside and you see that smoke that's rising, and then it hits a level and it just flatlines, it doesn't get above that. That's called an inversion. So if you could jump up above that, the smoke line, all of a sudden it'll be warmer there. Where you're at is cold, if you can get up there, it'll be a little bit warmer. And so what these remote generators do, if there's an inversion in place, you can get them up into that warmer air. And when you start releasing that silver iodide into the atmosphere, it can get above that inversion line. Remember that smoke comes out and levels out. Your generator was below that. It would get up and it would get to that inversion line and it won't do good because it's stuck there. So that's kind of the nutshell of why remote generators can be ideal. You can get them high up. You can put them on the mountaintops. You can get above that line. Dr. Tessendorf was also talking about some of the most ideal times to seed, and that's when you're -5. Bruce went into this too. When does that silver iodide really become active? You know, that's -5 degrees Celsius, or it could be colder. And by getting the generators up higher in the mountains, you typically get into that colder and colder air. And if it's a warm storm, or if the storm has the temperature range that those temperatures are better at the higher part of the mountain than the lower part of the mountain, a remote generator can get that up higher and just get that silver iodide directly into that colder part of the storm. That's good for cloud seeding. Another type of remote generators is a liquid propane generator. And these you can also place at higher elevations, but as opposed to the silver iodide that you need to get to about -5 degrees Celsius to work, in theory, and the research that's out there right now shows that these can start working at -1 degree Celsius. So if you have a warmer storm, and then what silver iodide would be effective at, you can start using the liquid propane, and this would start working and start developing those ice nuclei that go out and create the snowflakes and go downwind. So these liquid propane generators, they work at a little bit different temperature than what the AGI generators do, but that helps to just broaden the range of storms that you can see. Another type is the manual cloud seeding generators, and this usually involves drinking a lot of beer. So the first thing you got to do is, no, I'm just joking. These are some generators, and in this case, this is one that was created. They used an old beer keg as where the solution is, and they can put the solution inside there. It was a cheap way of doing it, and so it actually is a pretty smart idea. These work the same way as what the remote ground-based AGI generators do, except for it doesn't have all the technology that's on board to go there and to remotely turn them on, remotely turn them off, and to basically monitor everything there. It needs a person to do so. And so these are really high to get in the higher elevations, but you can still use them at some low elevation places where a farmer has a ranch or they have their house that they can go out and turn stuff on. And if there's no inversion around, they work great because they work the same way as what the remote generators do. It just takes a person to operate them, as opposed to a meteorologist that just jumps on their computer and turns stuff on remote. The final mechanism for getting silver iodide or getting a seeding solution into the cloud is using aircraft. And now if you think of that same temperature range that we have, that we're talking about, -5 or colder, -15 maybe, you're really trying to target that area for seeding. If it's a warm storm, or if it's a cold storm, that's down by the ground, so your remote ground-based generators work really well. But then as it gets warmer, that layer keeps going higher and higher in the atmosphere. Maybe your remote generators can't reach that portion of the cloud. And so what do? You fly an aircraft. And you can get the same silver iodide into the cloud using the aircraft, and you can use three different mechanisms. You have your ejectable flares, which is in the middle portion of the picture. These are flares that once you light them, they fall from the aircraft and they fall and burn up in about 200 or 2,500 feet. So you can see the block of air that's below you. You also have burn in place flares, which are like on the right picture. These are burned on the wingtips of the aircraft, and they stay with the aircraft, so the aircraft flies, and it keeps continuing to release the silver iodide as it flies through. So it stays at the same elevation, but you get a continuous burn as you move through the aircraft. Another way of potentially seeding is using a solution the same as you put in the ground-based generators, but you burn it from a wingtip generator on the aircraft, like in the upper left picture. And this one has, basically you put that solution in there, it has a fire that burns in the backside of the generator, and that has, in that solution has the silver iodide that then gets released into the atmosphere. So these are a few different mechanisms for actually seeding the clouds using an aircraft. So when you want to dive into and actually seed those clouds, or you're trying to fine tune everything, and you're trying to get to the what is the best, most ideal conditions to seed a storm. I always tell people that we're looking for three main ingredients for that. And the first one is there's liquid water available? And so that's in the clouds. Jeff did a great job, Sarah, Bruce, all talking about regions of the cloud that have liquid water. It's not ice, but it's liquid water. And then when we look at weather instruments, what can we use to try to identify those regions within the cloud that has the liquid water? The second question is, are the temperatures cold enough for ice nucleation? So with the case of silver iodide, we needed at -5 degrees or colder. Liquid propane, -1 degrees or colder. What can we use for weather instrumentations to start to answer those questions? And then finally, once you seed the cloud, where is that additional snowfall going to fall out? So what is the wind speed and direction that's going to basically take that additional precipitation and place it on the ground? So when we start to look at a lot of these, the first thing is the weather balloons. Don't look at the dude on there. We couldn't find any other pictures without me on it, so therefore I had to put one up of myself. We'll change that for our next slide. We'll get some more pictures of better looking people. But one thing that meteorologists use and is pretty critical for operations is they need to know what's going on throughout the atmosphere above them. And the best way to do that is to release weather balloons. And what these do is once you release them, it gives the meteorologist a nice little profile that they can look at. And remember when I was talking about an inversion, this is an inversion. As you go up that lower level, that's not good for seeding. If anything was below that, it wouldn't be a good case for cloud seeding, but anything above that, you can start to seed it. And so if that weather balloon comes back and says, hey, your remote generators are below that inversion, then you don't want to seed it. If they're above the inversion, then you can use them to seed. And so that's just a tool that a meteorologist can use. They can also look at the atmosphere and see where the temperature is. And so as you go up, it gets colder and colder. And here you want to be colder than -5. So you're up about here before you get into that -5 range. And so you're looking at, you're about 10,000 feet in elevation. So ground-based generators probably won't be a good idea to seed from this in this situation, but you can get your aircraft above that and get your aircraft to that level. And so in a situation like this, we launch an aircraft, and then the aircraft can go out and seed. You also can look at the other side and you have wind speed. So your balloons give you your wind speed and direction, so you can see where once you seed that cloud, where's the transport going to happen and where that fallout is going to happen downwind. So you get the benefit of that. And so meteorologists use that so they can put the aircraft on the right flight track so they can seed the target area downwind. Another thing that we can look at is a radiometer. So the weather balloons give you they can show you where clouds are, they can show you the dew point, they can show you temperature and wind, but they can't show you where liquid water is in the atmosphere. You can make some guesses, but you don't really know for sure. A radiometer, on the other hand, looks at the atmosphere and then it shows you, is there liquid water present above the radiometer? And if there's a liquid water present, and you know that cloud is cold, it's below freezing, then you know that super cool liquid water is there, and so that will be an ideal situation for seeding. Here's just a track that we have of one of the storms from a couple days ago that came through, and you can see wherever the tracks start to jump up, that's where more liquid water is coming through within the storms, and that would be those big blocks are where you start to target for cloud seeding, and those would be a great idea or a great location for seeding to occur. Another thing that you can use is an ice rate sensor, and this is also showing you the liquid water in the atmosphere, or the super cool liquid water in the atmosphere. In this case, on the picture on the left side, there was a lot of liquid water in the atmosphere that all froze around the ice rate sensor. This is a pinpoint location, and it has basically a probe that sticks out, and as water comes by, the probe has to melt stuff off, and then it can tell by the change of how much energy it takes to keep it clean, where there's liquid water in the atmosphere, or where there's liquid water at that point. So if you're running a liquid propane generator that you need to place at the super cool liquid water, this will tell you yes or no if there's liquid water at that point. Another one is web cameras. Meteorologists love web cameras. You can go out and you can look at any place that you have one, and you get a visual look. What's going on? Is there a winter storm going on? Here it's very cloudy, they're in clouds, so there's some sort of moisture that's going on. And these always confirm what's happening, and a meteorologist definitely likes these because they can confirm with what all the other instrumentation has. And sometimes you can even put sticks up or other stuff, and you can watch super cool liquid water attached to that stick and watch ice grow on it, and you know that, hey, that cloud is super cool because there's ice growing, and you can use visual cues for those. Here are some other instruments that you want for basically determine wind speed and direction. You can place these at different elevations. So the instruments on the left are on top of the pole. That's on the right. And so these are 10-meter instruments that get you off the ground. You can look at wind speed. You can look at wind direction. You can look at surface temperature and surface viewpoint. And this will tell your meteorologist what's going on the ground, if they should turn on certain generators, because the wind speed would be ideal for those generators to operate as you conduct operations. I think this is the final instrument that I have on here is a precipitation gauge. I have one more. But oftentimes where winter storms occur are in the mountain ranges, and we don't have radar coverage. So it's very difficult to see when a storm arrives and when there's precipitation starting to form. And the SNOTEL sites that we have, they measure to every tick mark on there is 1/10 of an inch. So you have to have a fair amount of snow. You have to have roughly an inch of snow before you get the first tick mark on a SNOTEL site. Plus they're an hour delayed, and and they only report every hour. So you can be 2, 3, 4 hours late from the time a storm starts until you get the first tick mark on a SNOTEL site. And so one thing that you can do is put up high resolution precip gauges in the mountains, and these will measure to 1/100th of an inch, or sometimes even a finer scale than that. And you can have them report as often as you want. So you can report every 5 minutes, every minute, every hour, whatever you want to program into them. And so you get a faster response to when a storm starts producing precipitation in the mountains. And finally, I have on here is a radar. When you're lucky enough, this is one of the Doppler on wheels from the Snowy, and this was designed to go up and be placed in the mountains to observe weather that occurred in the mountains at that time. But if you're lucky enough to have a mountain range that has the National Weather Service radars that are around, then you can use the radar to start to identify when there's storms that could be potential for seeding, and to look closer at some of that aspects as well. One of the final things that we really like to dive into and look at is numerical modeling. Sarah started to touch on this in her presentation, but you can bring a new high-resolution numerical model into your cloud seeding project to really start to forecast out when is the most ideal time of that storm to seed clouds. And on the left-hand side here is a bunch of parameters that a meteorologist will use for case calling. And so this is using the numerical model in a forecast mode that's looking out into the future, and it's looking at different parameters. Where there's liquid water, where the model thinks it's cool liquid water, when temperatures are correct, when there's precip, and where all those line up. The model then can start to show the best times for cloud seeding. Then a meteorologist can look at this and see what is driving that seeding situation, and then they can go back to their instruments that are on the ground and watch those to see if they react the same way that the model thinks they should. And if they line up, then it's a good time to call a case, and they can adjust their storm accordingly with those instruments that are on the ground. A couple of the final things that I want to get into is there's always questions about when you should seed and when you should. And a well-run project always has suspension criteria that are designed into the project. And this is for those extreme cases. If there's a lot of snowpack, should you seed? If there's avalanche concerns, should you seed? And so projects start to incorporate some of these criteria into their operating procedures. In the case of flooding, if there's two main reasons that cause flooding. One is that there's a rain on snow event. So this is when you have a large snowpack, and then you have it's in the spring of the year, or it could be in the fall of the year, and instead of a storm that's coming to produce more snow, it comes and produces rain instead. And that rain falls on the snowpack. And if your snowpack is already ripe, so it's ready to release the water from snowmelt, that rain will melt that snow very rapidly, and you can get some flash flooding because of the rain melting the snow, and you get a lot of water that enters the stream at one place. And so a lot of projects won't seed in these situations. It could be ideal situations for seeding, but you don't want to produce a little bit more rain that will fall on the snowpack. So you'd suspend operations if you wouldn't seed in this situation. We also look at the full size of the snowpack, and if that snowpack continues to grow and continues to get to a point that springtime runoff will probably start to exceed what riverbanks can hold, then you look at suspension criteria in that situation. So on the graphs on the right, this is just looking at some of the monitored basins, and if you had an average snowpack per year is the blue line on each of these graphs. The red line would be where you probably have your suspension criteria set up for, and then you can look at the operations of the actual snow when it falls throughout the year. And as that snowpack continues to build, it could hit the suspension criteria. And once you get close to it, or you pass the suspension, then more likely you seed you suspend seeding for the rest of the year. Some other suspension criteria that a lot of projects use are avalanche danger. When you get to the exceptional avalanche danger, you may not seed because you don't want to put more snowpack fall on unstable snowpack, so you probably won't seed in storms with an exceptional avalanche danger. Flooding, so when the USGS stream gauges reach a certain flood stage, more than likely anything upstream from that, you would suspend operations. You can suspend operations for search and rescue when they're going out to look for people that are lost or trapped. You'd probably suspend operations as that search is going on. And then there's severe weather stuff like lightning, localized heavy precip, strong or damaging winds, tornadoes, or even other special circumstances that pop up. A lot of times projects will suspend operations because of those situations as well.
Good morning, everybody. I'm Pat Golden with Heritage Environmental Consultants, here to talk about some environmental considerations surrounding cloud seeding. First, I just want to talk about naturally occurring silver in the environment. Silver is a rare metal present at concentrations averaging 100 to 1,000 parts per billion in the soil. And in fresh water, it's less than that, but it's 0.002 to 0.03 parts per billion. Again, naturally occurring in fresh water. Stream sediments are between 0.2 and 1.7 parts per million. And then freshwater concentrations, again, are typically between 1 part per trillion to 30 parts per trillion. with concentrations of 50 ppt not being uncommon. Parts per trillion is 3 orders of magnitude, or 1,000 times less than parts per billion. I want to just stress that because it will be important on another slide here. Silver concentrations in snow typically vary from 1 to 20 parts per trillion after a cloud seeding event. So that's when the silver iodide falls out of the sky into the snowpack. For comparison, that's 5,000 to 50,000 times more silver in soil compared to seeded snow, with about 20 parts per trillion or even less than that. Some localities exceed these concentrations that I just explained, but they tend to be a result of mining, photographic industry, urban refuse combustion, and things like that. So because these levels are so small, parts per trillion, in order to measure them, you have to do trace chemistry analysis. These analyses have shown negligible environmental impact from seeding operations, but we can find the silver in the snow. Again, they're such small concentrations when you go out and sample them. I think somebody showed a picture earlier, or maybe the one will come later, but you have to wear clean gear. You have to clean your equipment with acid because, I mean, your clothing has more silver in it than is in the snow where we're looking for it. So as part of the Wyoming pilot project that we worked on, the baseline in the snow was about 4 to 6 parts per trillion and about 36 parts per trillion in streams, which is just barely above detectable levels where seeding had not occurred. Again, it's far less than would be expected from other background sources of silver. So to just talk about silver speciation and how it relates to toxicity, we get this question a lot from the public. You know, you're spewing silver into the atmosphere. What's this doing to, plants and animals and such? So silver ion is free. The free ion on its own is very toxic to aquatic fish, plankton, things like that. Silver iodide, on the other hand, is a salt. So it's Ag+ bound with iodide. It's insoluble. It does not dissociate in water. So that means it doesn't dissolve. Ag+, so free silver is much less toxic to humans and terrestrial species, such as plants as well. The World Health Organization, EPA, and most state governments have water quality standards for silver, which is 100 parts per billion total silver. In a lab situation, which actually you can't do, but if silver iodide was allowed to sit in solution with unlimited time to react, you would get a solution of less than 1 part per billion of free silver. Again, that's 100 times less than the EPA limits. I won't go into that. That's kind of uninteresting. So silver accumulation and trace chemistry. Silver iodide primarily accumulates in soils or streambed sediments. It's found again at parts per trillion levels. Environmental sampling of cloud seeding operations have found no detectable increase in total silver concentrations above the background levels in soil, again, because we're looking for such a small amount. You can't even see it compared to natural baseline levels. We've done some studies here in Idaho, actually, where we flew a helicopter out to the target area for Idaho Power and took snow samples to look for where the silver is actually being dispersed. And we found it, but in very small amounts over a large area. So again, it's not being concentrated, it's way spread out. And trace chemistry is required to detect it. So measured silver from seeding, again, this is just some data from the Wyoming Weather Modification Pilot Project that happened a few years back. Total silver measured in water during the seeding operations was the same order of magnitude as the baseline. So we went out and collected baseline samples of the water, soils, snowpack prior to the beginning of the project. And again, it was the same order of magnitude, so there was no change seen. And again, several orders of magnitude lower than values considered to be hazardous. So you can see in this graphic here, the silver is the bright red bar. EPA and World Health Organization guidelines are in that blue band, and samples from the weather 2005 was the baseline on the left, and then the cloud seeding started, and you can see that those levels really didn't change. They went up and down a little bit, but they stayed relatively the same. Here's a picture of collecting snow samples with clean gear. This is again here in Idaho. So after a seeding event, we try to go out and you dig a column and you push little vials in. I don't know if you can see it very well in the photograph, but you're sampling the layers of snow. On the right is the silver. So you can see the green bands. That's where we're actually finding the silver, which we can relate to, given the timing, to the cloud seeding experiment. Another thing that comes up is bioaccumulation. After you release silver for a long period of time, is it going to accumulate? Is it going to increase? Bioaccumulation is the buildup of the substance as it moves up the food chain. And again, toxicity depends on the concentration of active free silver ions in water. Again, silver iodide is insoluble. It's very stable. It does not break down into free silver ion. Soil sediments and water toxicity is very low, even given high total silver concentrations. Most of it's bound into that stable compound, and it's not available for absorption by any plants or animals. Free silver ion does accumulate in algae pretty quickly, but once it's in there, it binds to stable compounds, and again, it's kind of like a grain of sand because it's so stable. Even if a fish eats a bug that has silver in it, it's going to pass through their digestive tract back out into the environment. I think Bruce or Sarah talked about this one, so I'll skip that. That's again extra. Okay, so noise impacts. When we did the Wyoming Weather Modification Project, we actually had to go through NEPA to get permits to place the ground generators on Forest Service land. One of the comments that came out of the public scoping was noise impacts, and I think the Wildlife Agency was concerned with this too. How loud are these generators that you've seen pictures of? So for comparison, a 3/4 ton Chevy diesel idling with its radio and fans off is about 67 decibels. A remote cloud seeding generator, the average noise level is 65 decibels when you're standing right underneath the generator. If you move 25 feet out, that goes down to 60 decibels. 50 feet, you're down to 54. 100 feet, it's about 50. So it dissipates pretty rapidly with distance. And for comparison, 20 to 25 mile an hour winds produce 72 to 78 decibels. 10 to 15 mile an hour winds are 54 to 60. So it really just sounds like a forced air furnace in your home with a high pressure gas stove. So again, there's very few, if any, impacts to terrestrial wildlife, residences, and any of that. And again, ground generators are often quieter than the ambient noise level during their operation because it's often windy. You need the wind to kind of get the stuff up into the clouds, so it's pretty imperceptible. So I know Derek talked about this a little bit, but this is another comment that we've had a lot with the public in terms of suspension criteria. How do you minimize potential hazards like flooding or avalanches? It says most operational programs have suspension criteria. I'd probably say that they all do. A few reasons to suspend are unusually heavy snowpack in the target area that could cause extreme avalanche danger, unusually severe winter storms as forecast by the National Weather Service or project meteorologists, insufficient reservoir capacity. So if you start the season off with the reservoirs already pretty full, they're really monitoring that to make sure, you know, if those are getting close, they suspend operations so that there's no overtopping or anything like that. And then seeding can also just be suspended at any time at the direction of the water management agency, a utility, or the program sponsor. So for permitting, a lot of the higher elevation lands where we like to put the generators are on public lands, federal, usually Forest Service, BLM. And the placement of those requires permits. So you kind of have to work through the process. There's a bunch of different kinds of permits. Special use permits are what you need for to put the generators on the ground, but you can do a categorical exclusion. Sometimes you have to do an environmental assessment, and then like the highest level is an environmental impact statement. We try to avoid federal lands as much as possible and site them on public or state lands or private lands to avoid that. But sometimes you just have to consider it if you're planning a project, work that into the budget. We also deal with, that's the National Environmental Policy Act in California. They have a similar act. We have to deal with the Endangered Species Act quite often with that kind of permitting. And aerial operators must submit annual reports to NOAA to describe the number of hours that were operated, the amount of seeding agent that was used over the course of the season, and things like that. Common comments we get during NEPA from the public are potential downwind effects, effects of silver iodide on the environment, which we're talking about here, stream flow monitoring requirements, consultation for listed species and plants, tower design. You know, raptors they could build nests up there, so sometimes you can do some things to discourage that. Excuse me. Crucial wildlife winter range, flooding potential, concern for public water supply intake related to silver iodide, and seeding wildfire burn areas. That's another, I guess I wouldn't even call it a suspension criteria, but if an area is burned, oftentimes projects will just be suspended for, you know, a matter of years, just so you don't create a bunch of erosion in those areas. So I want to talk a little bit about stakeholder involvement and public involvement. For the Wyoming Weather Modification Project, we spent a lot of time and energy trying to have continuous dialogue with stakeholders. We did public hearings, special presentations. We traveled to little communities and do kind of what we're doing here and explain it to everyone. They had some basin advisory group meetings for the stakeholders in Wyoming. I think one of the most successful things with that project was we also had a technical advisory team. So this was a group of, the public was invited, but generally it was concerned agencies. So for the Wyoming project, and I think it's probably pretty similar here, we had, I think, Bruce, what did we have, like a couple meetings a year?
Yes.
And we had folks from the Bureau of Land Management, the NRCS, National Weather Service had some folks represented.
Forest Service.
Forest Service, University of Wyoming, Jeff and company were there. The Forest Service, multiple, I think we were dealing with 3 forests on that one. The USGS participated, the Wyoming Department of DEQ, DOT, you know, that DOT had concerns with winter seeding and how it might affect traffic and safety. Wyoming Game and Fish, and also the state engineer's office. So I think that was really effective just for everybody to keep learning about the science and express concerns and talk about it. So in summary, total silver concentrations from seeding are orders of magnitude lower than naturally occurring background levels of total silver. Silver iodide is a stable, insoluble molecule compound. It doesn't dissociate in water, and therefore it's not toxic. Again, the free silver, which people tend to not talk about on the internet, they just say silver is toxic. It's not created from silver iodide. It's insoluble. Environmental sampling of cloud seeding operations before and during operations have found no detectable increase in silver concentrations over background levels in seeded areas. Extra area effects. I think folks talked about this a little bit, but seeding has a very small impact on the water budget, the pie chart that you saw earlier, and downstream effects to your neighbors are negligible. And then again, suspension criteria really help minimize the potential for flooding, avalanches, and overtopping dams. These programs have meteorologists on project 24/7, so they're monitoring that stuff constantly. I've got a few references here if anybody's interested in looking it up. Some good publications on environmental impacts. You can reach out to me if you don't have time to get these, or I don't know if you're going to share the presentation, but I'd be happy to provide any other information. And that's all I have.
Well, we had our one-on-one this morning. You now have a pretty good overview of how cloud seeding occurs, how to measure it, how to conduct it, what the environmental effects are. Go into much more detail, but I think that's enough. And we're just waiting to see if we have any questions from Sir.
So has anybody ever experimented with seeding with propane from a plane, or is that just too dangerous?
Repeat the question. I could take a stab at that.
Right.
I think the problem is you're taking.
The question is, has anyone ever done seeding with propane from an airplane, aerial?
Yeah, I think the problem with that, and Jody Fisher's here and can speak to this as well, is taking a flammable compressed gas aboard an airplane. I'm not sure what kind of permitting would be required to do that. The general alternative is to use frozen carbon dioxide, dry ice, instead to achieve a very similar effect.
The advantage, I think, of liquid propane, right, is that you can seed at clouds at relatively warm temperatures, below 0 degrees Celsius, right? And if you're flying around in an aircraft, as long as the cloud, extends to temperatures of maybe minus 10 degrees Celsius or something like that, you would probably be just as effective with dry ice seeding, I would expect. And it operates under the same general principle. But I don't know of anyone that is doing dry ice seeding operationally anymore. Maybe there are some.
Right.
What's that? Oh,
Yeah.
okay. Great. I did not know that. Yep. Okay.
That was North Dakota who does that.
Yes.
Sir.
So at the Idaho Water Resource Board, we get some messages from naysayers, and I'm sure Kayla has too, that say that we're putting, cadmium, PFAS, all kinds of things in these. Do the flares have anything in them that's other than an agent to burn them and the silver iodide?
They do not. I'm not aware of anything in any of the compounds that is hazardous, especially along those lines. It's curious to me how persons from the public would come up with those particular compounds. Right?
Yeah. No one online. Oh, over here.
Yeah, thanks for great presentations. I wanted to follow up on the liquid propane and have you discuss the effects of climate change and warming. Are we likely to see warmer clouds? Does that go against the physics? Is it a natural outcome of warming? And if so, does that portend more liquid propane type of techniques, or will silver iodide still work in a warming climate?
Has everybody heard the question? Just about the future of using liquid propane in a warming environment.
I can take a stab at that to begin with. If you look at global climate change, that's relatively slow change. You're looking at a few degrees at most over the course of decades or centuries that it comes along. When you get into the natural variation of storms that we have right now, there's a wide fluctuation of cold storms and warm storms. And so a lot of what we look at as what is the broadest range of storm that you can see, and how do you optimize your system so that you can seed as many of those storms as possible to create the best precipitation that you can, or the most additional snowfall. And so that's why we look at setting up liquid propane generators and AGI generators. That just broadens the scope. And also why we look at seeding from ground-based generators and aircraft. It broadens that range of storms that you can see. So if there is an increase in temperature over time, you would see that shift, that you could start to see more propane seeding. But that's one reason, if you optimize your system so that you have all these options available to you, you are in a set for that, I guess, in the future, whether it happens or not.
So again, for anybody, so we heard that, and we hear this a lot, that what's the downwind effect, and it appears to be pretty negligible, but in a more isolated area, say you've got the Tetons and you got Grand Targhee on this side and Jackson Hole right on the other side, do you enhance Targhee and reduce Jackson Hole a little bit on a storm coming from the west, or do you try to target storms coming from different directions to enhance them all? Or there's got to be a little bit of downwind effect right within a specific area, probably.
I think, if I may, I see Sarah's back online with us, and as part of the NCAR team evaluating the Wyoming pilot project, I think she has experience, or at least the team did, in answering that question. So perhaps that's one for her.
Thanks, Bruce. Yeah, so, and I also see there's a question in the Q&A coming online also, not just about downwind effect as a possible decrease, but another question came in about instances of an increase on the rain shadow side of a mountain range with any of these studies. And so I will say, on a storm by storm basis, the way that the storm is producing precipitation naturally, the amounts of moisture and liquid water in it, and each of those things can vary exactly how the seeding effect is being simulated in our model simulations. Let me just also make clear that the only way that we've been able to really look at this is with the model simulations so far on these localized case-by-case bases. So there is some variability storm by storm on if we see broad increases over an area, so to answer that question online, we do see sometimes even in the rain shadow downwind area of a mountain range, a broad increase. Sometimes we also see increases in subsequent mountain ranges downwind as well, because if that additional silver iodide nucleates ice and some of that silver iodide still reaches a mountain range downwind where there's conditions, opportunities for seeding, that it might also nucleate more ice and enhance precipitation there. In some limited cases, we occasionally will see some positives and negatives, and that's where the science research is trying to understand what is going on with these storms, what makes those specific storms more likely to have an increase in one place at an offset for somewhere else, because those would then be cases that we would not want to seed. So this is where science has still, got work to do. Over a whole of a winter season, when we do these evaluations, we don't see any systematic decreases. We generally see broad areas of increase. But again, on a case-by-case, storm-by-storm basis, there might be some changes that we're still looking into more.
I'll just add to that, because I think Sarah was talking mostly on the modeling side, but in the study that we did here in Boise and Fayette Basin in 2017, there was a case that comes to mind where we had direct observations of the impact of the snowfall coming out of the clouds actually downwind of the target area, and that was a case where Idaho Power may have not even chose to see that case if it wasn't particularly for the research that we were doing. It was a very high wind case, and the time that it took for the precipitation to actually develop and fall out of the cloud is such that in very high wind cases it may not fall in the target region. And that's a ripe area for research, both for observations and for modeling, to improve targeting of systems on a case-by-case basis.
Just to clarify, Jeff, you're saying that in that particular case, the increase observed occurred downwind?
Yes, yeah.
Okay.
The increase occurred downwind of what the target region was. Because, right, it takes a certain amount of time once you introduce the material into the cloud for the ice to form, for those ice crystals to grow, and then to actually fall out. And if you have a very strong wind, they are going to fall out further downwind than they would if the wind was weak.
And with this case, it was one that we wouldn't have seeded naturally. It was the research part, and so we did some additional seeding for that. But a side note to that is it also confirms some of our criteria that we have in place. And so this is just one of those cases where you have research that goes along with an operational program, and you start to fine tune the basis for your criteria that you actually operate under.
Yeah, right, and I think that justifies why having a lot of these additional measurements, if possible, or at times, are very useful to the program, right? Because then coming out of that, you can have a more robust program that is more specifically targeted for what you're looking at.
And I wanted to add something too, because I'm the layman here on this panel. I think a lot of times the public doesn't understand too that they're typically seeding storms that are inefficient, naturally inefficient. So they're trying to kickstart it to produce precipitation when nature wouldn't have. So you're assisting a storm that may not even drop snow on the upwind neighbor or the downwind neighbor, but by seeding it, you're encouraging it. And I mean, I don't know, that's, correct me if I'm wrong, but it's just my observation.
Yeah.
Yes.
I have a question. You talked a lot about cloud seeding for moisture here, but I've also read or heard about cloud seeding to break up hail, mainly in the Midwest. Is that going on in the Northwest? How does that work? Is that another lecture?
Is North Dakota doing hail suppression seeding right now?
Yeah, they are, and Darren can come up and take the extra seat on the panel if you'd like to talk about it. But with Weather Modification International, we do conduct hail suppression operations. And it's the same cloud physics as what Professor French spoke to us about earlier. But what we do is, in a hailstorm, the hail generally results from a cloud that has produced very, very extreme amounts of supercooled liquid water. And there aren't very many ice particles. And so each ice particle can grow and get very, very large. And so the way you mitigate hail damage is you do the same thing. You introduce lots of little ice particles in it, and they compete with each other. And the end particles are much, much smaller, and many of them may even melt as they fall through the warm subcloud layer. So that's the premise on that. We have an active program. Of course, the state of North Dakota has the active program out there that's run for decades. And the program that our company does in Alberta, Canada, on behalf of the insurance industry, has now run 28 years, and is scheduled to continue this next spring. So,
is it fair to say that the science is not as advanced in that area? From my perspective, I would say, right, in demonstrating this, it's a really difficult thing to demonstrate, right?
Because we're gonna be late for lunch.
It's not a criticism. It's just a fact, right? That you know, these storms are relatively rare.
Yeah, and
And-
they're extremely complex.
And they're
Yeah,
very
and the
complex.
measurement techniques are limited. And I'm going to actually make us on time for lunch, Jeff, by saying, I want to talk more about this later today when we get to the design and evaluation side of it, because we talk about the complexities of warm season clouds and that. And so I'll defer that until then. But the question is fair. It is a very complex situation. And there is a publication that's going to come out in Atmospheric Research within the next few months, an evaluation of the Alberta program conducted by scientists at the Canadian Institute for Catastrophic Losses Reduction, using independently using the project data. And I'll talk more about how that worked also, not the details of the hail suppression, but how collecting good project data over a long term paid off in the ability to conduct an evaluation. So I think I should stop there, Tom.
And I think just the last part of your question, I'm not aware of any hail suppression in the Northwest or even the inner Mountain West.
There was interest in Cheyenne, Wyoming a few years ago, and that got quasi-serious for a brief period, but kind of died on the vine.
Before you jump on to the next one, just to follow up a little bit too with the research side of things, and one of the real benefits of the Snowy project that we had here was it was wintertime orographic cloud seeding, and that is not nearly as complex as the storms that occur in the summertime. And so when we get down to modeling and looking at some of the research on it, the models that we have can identify and track that with a lot better confidence than what they can do with the smaller scale little individual thunderstorm that occurs, because thunderstorm is very small. We're looking at a larger area of orographic lift that occurs, and that really helps out when it comes to modeling. So.
Kayla.
Yeah, one of the questions I get commonly here in the Northwest is why can't we do summer rain enhancement here in the Northwest? Or why does summer precipitation enhancement not work in the Northwest? Is that something you can speak to?
It's something I intend to speak to this afternoon, Kayla. So.
Sounds good. All right, we'll leave it for this afternoon.
Thank you for planting that seed.
Yes, absolutely.
Remind me if I don't
Okay,
get
we'll
to
leave
it.
it for the afternoon then.
Any more questions in the chat?
I do not see any more in the chat for right now, so I think you're still ahead of schedule.
I thought Frank might have.
Kayla, actually, that question in the chat from the Science Advanced side, I can just briefly address. The question being regarding snow, do we have a broad average of how much falls? I'll just add from the Snowy research project that has been discussed in my presentation and the other panelists mentioned. You know, we had 3 very clear cases with that zigzag pattern where we were able to estimate how much fell, and it varied between 100 and 300 acre feet per case. In those cases where precipitation was not naturally occurring, but we're still working on trying to evaluate the impacts on precipitation in the many other cases that we studied during Snowy. And so this is still a question that's being researched. And yes, it will be addressed more this afternoon under the monitoring and analysis, but definitely we are finally getting to the point where we might be able to put some absolute numbers to that. In the past, it was always being reported as a percentage, which if you've heard me speak on this topic before, I highly discourage use of percentages because you always have to pay attention to what the percentage is relative to in order to really understand what that percentage means. And sometimes our studies will give percents relative to seedable storms over entire winter. Sometimes it might be a percent relative to one storm on its own, or sometimes it might be a percent relative to all the precipitation and snowpack that builds in the winter. Those can lead to very different percentages. So I really think that we're at a great place now where we can try to estimate absolute value in terms of like acre feet of water, where we were not really able to do that with past methodologies. And yes, you'll hear more about those in the subsequent panels.
I'm just going to add to that. I'm hopeful, but I'm probably not quite as optimistic as Sarah is that we're that close to being able to do this. I think there's a lot that's unknown, and exactly right what she said. You know, in these 3 storms, we were able to put together good estimates based on our observations. of storms that otherwise were not producing any precipitation, which is great. But those are pretty rare storms that would be seeded in the wintertime. You know, the normal condition, if you will, the majority of storms are already going to be producing precipitation, and that's a much greater challenge. I think we are on a cusp of being able to make the first reasonable estimates, but we don't have a really good constraint overall on the system. I mean, this was from one project in Idaho. The conditions that we encountered were, you know, pretty much similar across all of these storms. And if you go to different parts of the country and you look at different types of storms that have different cloud droplet distributions and have different temperature distributions, the estimates may be quite different. And so, you know, being an academic, you know, we need more research on this to really understand it. But we certainly know a heck of a lot more now than we did 10 years ago. That's for sure.
But it's really cool that we're starting to get to a point where you can take a first step.
Yeah.
Is it correct? We'll find that out in 10 years, 20 years, 30, whatever it is. But it's really cool that we're at that point. I think that's.
I have a question online from Marta Nelson. Is there any insight into the suppression or reduction of dangerous liquid precipitation?
Dangerous liquid. What is that?
Is there
I
any?
would say freezing drizzle.
Oh, sure. Sure.
That's a great question. I don't know of anyone that is directly doing work on that. There have been groups, and I think there still are, that do like fog dispersal, right around, especially around airports or in transportation corridors, where they add ice nuclei to freezing fog or to fog that occurs below 0 degrees Celsius to get ice to fall out and disperse the fog. But in terms of adding ice nuclei to actual clouds that would be otherwise producing freezing drizzle, I am not aware of that. We just had a big project just a couple of years ago looking at freezing drizzle and freezing rain in the Northeast United States. And the idea of seeding to reduce freezing precipitation was not something that I ever heard brought up, but it's kind of an interesting idea.
I think part of the challenge is real often that freezing layer is kind of shallow and not very cold.
Which is why it's yeah.
Was there a question over here?
Yeah.
It's Jake.
So I have a question for each of the panelists and your own area of expertise from academics and operations and environmental health. What would you, if you had unlimited funds, what would your highest priority be for what you need to improve your area of expertise or to fill some particular gap of knowledge?
So the question is, it's for each of the panelists. It's if you could pick some research that you wanted to do or questions that you wanted answered, and you know, money was no object, what would be your priority?
I'll go first. We just recently started, well, I guess that's not true. There have been some environmental samples taken over the last, I don't know, 40 or 50 years, but I think it's important, not because I think that this is an environmental impact, but to show the public that it's not, to conduct baseline sampling, understand what the baseline levels of silver are, and if you've got an operational program long-term, go back periodically, resample, and just put the numbers on paper to show that over time, this is not accumulating, nothing's being affected.
When I look at that, question. There's a lot of different areas that you can look at that need improvement, but what area do you want to go in? I'm on the operational side, and a lot of that is to fine tune when we seed to make the best bulk, or you want to seed only on times that are best for seeding, and limit the times that you're seeding elsewhere. And so operationally, I would always look at how can we spatially improve what data we're getting back from instruments that are out in the field. And a lot of this will have to do with even the creation of some new instrumentation that will be cheaper, and you can start to spread it across a field. So you can look at spatially distribute, supercool liquid water across the mountain ranges, and so you can really identify where the best locations for seeding are. This could be with liquid water, it could be with temperature, it could be with how that's integrated into the models that you have. So you can really track what's going on in nature with what's going on with models, so that you can really dive into where you're seeding. That basically gives you the best bang for your buck.
From a research and understanding perspective, I think improving our knowledge about how the system is constrained and how different environmental conditions impact the seedability, if you will, or the efficacy of seeding, I think is critical. And the way probably to go about doing that, if we at least start off thinking about like orographic winter clouds, is to repeat projects such as Snowy in different conditions around the Intermountain West that have different cloud conditions. The other part of that is to really understand the process level things of what are occurring. So in addition to going and doing additional field studies to sample different conditions, doing detailed controlled studies as best as possible in natural conditions, so mountaintop laboratories where you can make a ton of measurements, very detailed measurements of how a cloud and precipitation evolves in time, and doing this repeatedly with a long-term investment, right, will help get us to the point where Derek wants to get in terms of the operations, and it'll help get us to a point, I think, where Sarah wants to get in terms of improving our model simulations. And this also helps our basic understanding of natural cloud evolution and how aerosols impact that, which can feed back to, looking at climate change and all of those other aspects that are involved in precipitation.
Thank you, Jeff. My answer should, in theory, be the best because I've had the most time to think about it before I open my mouth.
There's Sarah after you.
Yeah, that's true. That's true. Sarah's
I'm not ranking.
I really like what Derek and Professor French have said. They both make so much sense. I too am from the operational world, work in wintertime and summertime environments. One of the things that excites me the very most right now is the advancements that have been made in instrumentation and the kinds of things we can measure them and how we can measure them. And it's largely been made possible by advances in computing technology. It's just an enormous difference from where we began this game decades ago. And with that potential, I think, comes a very bright light for the future of the technology in terms of recognizing when it can be effective and when it won't be. And the identification of those circumstances, Derek, as you said so eloquently, are very, very important. You can save your resources for the times when it's going to work. You can limit the impact on the environment, though Pat assures this at the present time with the current agents, it's minimal anyway. But it helps with overall perception, efficacy, and evaluation. I mean, there's so many microphysical things that are at play here, and one of the big differences between the complexity of wintertime and the complexity of summertime clouds is wintertime's microphysically the process may be simpler, but the convective, but you also are dealing in large part with complex terrain a lot of the time, and that's not simple. Yet, and so there are different things in play here. I'm starting to ramble, so I better stop, Tom. But everything that's been said is worthwhile, and I would, I think, be really excited about the not just the development of new instrumentation, but the use of more of it to get a better picture to fill that information gap where you just have point measurements here and there.
And then finally,
Can I add on that?
yes.
Okay, thanks. Yeah, so I will emphasize all the previous responses and point out that, as Bruce just said too, filling those gaps in our observations that Derek mentioned about higher spatial density of observations, gaps in our understanding that Jeff alluded to, and even though I've spoken a lot about models, I am an observationalist primarily, and so filling those gaps with observations is definitely something that would be great. Radars, more radars, gap filling radars, we call them in the Intermountain West, but even for summertime convective work, phased array, dual Doppler, dual polarization radars, there's a lot of advances there that will help us better resolve those quick evolving processes in summertime convective clouds. But in the Intermountain West, getting more radars out there to just observe the spatial patterns of precipitation in clouds and have a chance to try to observe more of those zigzags perhaps as well. But also, as I mentioned earlier in my presentation, our understanding of our aerosol, those background aerosol conditions, are also really limiting. We did not have measurements on aerosol in Snowy, so while I agree with Jeff, I'd like to take Snowy and do it again in many places, I want to add on to Snowy to make sure that we get some really good understanding of those background aerosol. And that's also, of course, important in the summertime convective work too that Bruce has mentioned that they are doing in some other parts of the world already. Supercooled liquid water observations, I think, is one of the ones Derek was alluding to that we really need to fill gaps on, because those, we don't have, I'm going to make this point again later, but we do not have routine measurements of those. And so getting that better resolved would be good. But I also want to point out that if we make these improvements to our overall understanding of how these clouds are behaving for the purpose of cloud seeding research, it also helps us more broadly, because if we understand these clouds better, that's an overall improvement to the field of cloud physics that we can then put that back into our forecast models and hopefully someday get better forecasts of the weather too, so everybody can stop doing that old joke about meteorologists keeping their job except they're wrong half the time, So if we can improve our models by improving that understanding with better observations and field projects, to me, that's the place we need to go. If we had unlimited resources, that would be great to do that. Time is still a limiting resource though, so I guess I'd need to use that unlimited budget to pay for a lot of folks to work with me, because that's the only limiting factor that I foresee for myself right now is the time to do all this great work.
Thank you.
So, Tom, there is a question in the chat. Is there any difference in the physical properties of seeded snow versus snow that falls naturally, i.e. physical properties such as density, grain size, structure?
Boy, that's a good question. I don't think we have the, okay, so first off, my instinctual answer to that question is no. They're going to essentially be the same, and there's no reason why there really should be any difference, because all you've done in a seeded cloud is you've introduced an initial ice particle, and once that ice particle has been introduced or has been nucleated, it's going to grow through the same natural processes. Now, where that answer might go wrong just a little bit is that in clouds that are otherwise not producing natural snow very efficiently, the conditions may be such that you will be growing, that the natural processes that are occurring may be more, maybe one process might outcompete another process that wouldn't necessarily be happening in natural conditions if there was more natural ice. Does it impact anything? No, it wouldn't anyways. I mean, it wouldn't matter in terms of, in terms of, you know, what that snowpack actually looks like while it's on the ground and all of that. But where it does come into play, or where it could come into play, are doing things like utilizing algorithms that we develop in natural snow conditions to estimate the amount of precip that falls utilizing a radar, for instance. Right? Those algorithms may need to be tweaked somewhat because the conditions of the snow are slightly different.
I largely agree with you, Jeff, based primarily on information Pat shared with us about the amount of seeding agent in the snow, and you know, a couple parts per trillion. That's such a small amount. When I think get my head around how that can change the density or structure or something, I just can't see it.
That's a good point.
Can I just add on? Can I just add on to what Jeff and Bruce just said, though, too? I think as a way to explain what Jeff's suggestion, that if there were going to be any ways to detect it, or that they would be different, it might be in the numbers and or the size of ice crystals that fall in the seeded region, just because we are imparting that, you know, really high ice crystal or ice nucleating particle to ice crystal concentration above what the natural cloud was doing. And so the way that those might grow, the sizes they might grow to, the numbers that they might fall out in, could, in theory, be different. I think that's what Jeff is alluding to, and that's where, when we do an estimation from radar of what that snowfall amount would be, it's very dependent on the sizes of the particles as well as the number concentration. So that's where we can't answer that for sure, but my gut instinct is just like Jeff's also, that I don't think that there would be really any readily detectable difference, but in theory, in a case where the process that those crystals form through could be different, we might see different numbers or sizes, but whether we'll be able to detect that anytime soon is unclear to me. Maybe in some lab cloud chamber studies, that could be an interesting way to look at that.
Thanks, Sarah. I think you said what I was trying to say a lot better than I did.
So we have time for maybe one more question if we move on to our next part of our program. And Frank?
Well, I'd just like to add to what this conversation was. So we've actually gone out and sat under the seeding foam multiple times and looked at the stuff that's coming out. And I think the one point that we need to talk about is the temperatures that the cloud seeding crystals are forming at. So, you know, if you're forming crystals at -6 versus -11, you're going to have needles versus plates maybe, and the efficiency of how the plates collect rime versus how the needles collect rime, and also how they grow based on vapor growth as well, is also a part of it. So you're going to see a little more maybe of the needly, rimed up needle kind of stuff, at least in the Sierra where we do our stuff. And so, as opposed to the colder stuff. And that's also important, I think, for aircraft seeding versus ground seeding. If you can get up and put the silver iodide at -11, -12, where you're going to get these nice crystals that have a good surface area that are going to really collect the rime, as opposed to needles that aren't quite as efficient at collecting, sweeping out the rime, you might have better precip enhancement based on what temperature you put the ice nuclei at as well. So I think there is a way to look at it, but it's like everything else is super complex, and there's no easy way to do this.
Thanks, Frank. I think it's the type of stuff that us cloud physicists totally geek out on, but no one really cares about.
Final question. Anything?
I will go ahead. There's one in the chat, or did you have one in here? Okay.
I just have a non-scientific question for Derek. So you put all these weather balloons way up high and they come down somewhere. Do you get calls from farmers in Iowa, or do you just put Chinese writing on them so they...
They burn up on re-entry is what it says. No, they're disposable, so people, when they find them, they just throw them away. I know the Weather Service has tracked some and they get some back, but yeah, most of them just end up in some farmer's field or whatever and they get disposed of.
Thanks, Darren. Thanks, everybody, for the opportunity to share this. This is a topic that I typically get to present about our programs, Cloud Seeding 101, why we do it. Going back to the start and talking about breaking ground, this is an unusual topic for me, but I hope it goes well. I hope it's informative. And one thing I'd start off with is when we were thinking about how to set this up, it was like, well, you know, how do you do this? There ought to be a recipe. I said, you know what? There isn't a recipe. Every project has its own nuances, its own stakeholders. It's for a different purpose. So we decided to present a couple of case studies that will hopefully highlight for you some of the take-home messages of things to consider as you're looking at developing a program. So the project that I want to share with you today is our PAYUP project, a case study and a review of that. That is our longest running project here at Idaho Power and in Idaho. So a little background about Idaho Power that kind of plays into how this project came to be. So Idaho Power is an investor-owned electric utility. We're predominantly a hydro company. We own and operate 17 hydro projects on the Snake River. When the PAYUP project was conceived, about 70% of our generation came from hydro. So a huge portion of our generation resource came from hydro. And water is the fuel source for that. And hydropower is Idaho Power's lowest cost generation resource. It continues to be our lowest cost generation resource. The typical model, financial model for a regulated utility is that the rates pass the power supply cost onto the customer. So, relevant or not, one of the perceptions is that Idaho Power pursued this as a way to build profit. Really, the low cost energy that comes from cloud seeding really flows to our customers. That keeps our rates low. So that was the driving reason to do this. And that brings into another piece of it is that the Idaho PUC played a key role in figuring out how to balance the cost of the program and the benefits of the program with our customers. So that was a key piece in figuring out, you know, how do we navigate this scenario to do an operation or to have a program that costs money to operate and both parties equitably benefit from it. A bit more on Idaho Power. So I mentioned that when we started the project, 70% of our energy came from hydro. In 2022, just over 30%. Some of that varies with water, but some of that is our customer base has grown substantially since the early 90s. And we haven't grown our hydro resources since then, but it's still a huge portion of our generation portfolio, hydro. So a little bit on where we're at. So we've got up here in the Upper Snake, we get water that starts up there, runs down the Snake River across southern Idaho. Let's see if I can get the mouse. So our most upstream hydro project is here at American Falls, and then we've got Milner. Milner is an interesting place. The minimum flow in Milner is 0. So we kind of have a two rivers concept here, and then most of our hydro is downstream of Milner, and our most downstream project is Hells Canyon Dam down here in Hells Canyon, which is on the border of Idaho and Oregon. So we've got all of this watershed that feeds into our hydro system. So the kickoff for the PAYUP project, and new programs really need to start with a question. You need to focus on what is that question and what are we trying to resolve with cloud seeding or address with cloud seeding. For the PAYUP project, in the late 80s, early 90s, there was an extended drought in southern Idaho and much of the Northwest. And a share owner posed a question in 1992 that I was a hydrologic engineer for Idaho Power at that time, looking at water supply forecasting. And I got this question to answer or come up with an answer for. And the share owner wondered why Idaho Power didn't have a cloud seeding program to augment snowpack for its hydroelectric system. And they referred to cloud seeding programs that were in California for the purpose of augmenting water supply for hydro utilities or hydro projects in Calofornia. I have an engineering background. I had no idea what cloud seeding was. One of the first steps that I took was I had to dive in and figure out, well, what in the world is cloud seeding and is it applicable here? And so in 1992, I didn't have access to it. I couldn't go just scope things out readily, quickly. I rallied with a water resource engineer that I'd worked with on other projects. You familiar with this? And so we did a pretty deep dive into literature review. And for me, that took a couple of years to just figure out, what is it? Is it viable? What kinds of terrain and watersheds do you seed in? Fast forward to today, I mean, these forums are a great resource for people to get information on what it is, how does it work, where can you do it. So there's been a lot of progress that's been made. I'm a little embarrassed to share that I started working on this over 30 years ago, but a lot of progress has been made over that time. Some of that early background is important so that the stakeholders that become important in the project for the long haul have some common understanding about what's being pursued, what's feasible, and what's realistic to expect. One of the, and I'll note that there's some iteration in this presentation of the topic because it was a very iterative process to get this project up and going. But one of the questions that I think need to be addressed early on is the watershed a good candidate for cloud seeding? And some of those considerations include the climate terrain. If you have unfavorable temperatures or lack of precipitation, lots of inversion, those can limit your seeding opportunities, which reduce your potential for benefits. The hydrology. If the hydrology is conducive to get additional snowpack in the mountains to where the benefits can be realized. And that can be a limiting factor. Does the watershed tend to flood? And if it floods, is that problematic? Do we care? Is there a municipality at the lower end of the watershed, or is it a headwater watershed? We really don't. It doesn't really matter. Access can be important, especially for ground equipment instrumentation. The primitive areas, national parks, roadless areas, those can be great places to target, but access can be a showstopper. And then politics are another good thing to take into account. And is it going to be feasible to make the needs and wants and the politics that exist work together so that you can have a viable program? So where to start? I had this question. I have all these watersheds to consider. The Upper Snake produces a ton of water, but there's a lot of regulation up there. Go to this slide here. So we didn't want to start there. This was really our first program. We wanted to make sure that we had a lot of assurance to get benefits from. So the Upper Snake regulation ruled that out. The Lost Rivers, well, that water goes straight into the ESPA. In those days, we were concerned entirely with surface water flow. It was going to go straight to our hydro project. The Wood River, the Malad, that's a pretty gnarly watershed to think about how you're going to get water out of it. We do see it today. That was not the case. That was not the place to start. There had been projects operated down in the Owyhee. DRI had operated some of those years ago. That's a long way to get around to see storms that were coming up from the west or the southwest. It was a long ways from Boise to operate a project. And then there's a lot of storage in the Owyhee River. So that one was kicked out. The Bruno had access issues. It does go straight into our hydro system there at CJ Strike. So it did get some consideration. The Boise had a lot of regulation and storage in it. There had been a project at the Boise Border Control. This started up about the time I started researching for the Payette. It was a pretty minimal effort, all manual generator program. Looked at the Weiser. The Weiser had a fair amount of potential. The Weiser is a very flashy watershed. It floods a lot. the city of Weiser is at the bottom end of that watershed. So we steered away from that. We still shy away from that. The North Fork of the Payette had some targeting issues. I mean, it's a long, narrow watershed. Knowing that you're going to be able to put snowpack in the North Fork, not see the Weiser, and not have all your benefit going to the South Fork salmon, it was like, that's not our sweet spot. We wound up focusing on the South and Middle Forks of the Payette. It's a very rich watershed in terms of water production. There's one little tiny reservoir in there, Deadwood Reservoir, not much storage, pretty much always filled. And at the time, there was the water users in the Payette had plenty of water. They liked the idea, more was better, but they really had no financial interest in supporting it at the time. So it was all on Idaho Power to pursue it if we wanted to. And so that kind of led us to, well, all right, we got a place to look, but we need to figure out, how much water might we get from this? And we just need to do this high-level feasibility, and does it pencil out? And do we expect to see the water at a time that we could get a benefit? So in that preliminary program design, going back to the literature review and working with experts in the operational part of the field at the time, well, do we look at aircraft, and do we have an airport to work from? Does the terrain allow flying the aircraft at the elevations that we probably need to be at? And when we went through all that, it was like, well, the aircraft looked pretty conducive for the Payette ground. Even though there's not a lot of wilderness area in the Payette, the access is pretty limited, and it's pretty rugged terrain. So we knew right away that we were likely going to need to have remote equipment, and then access to lands to put ground equipment on was really a concern. Most of the lands in the Payette watershed are national forest. Boise National Forest was pretty resistant right out of the gate to talk about putting this kind of equipment on the forest. And I've learned along the way that forests are managed very differently across the West at the district level. Equipment instrumentation, what was already out there that exists and what might be needed in terms of weather stations, radar. Back in that time, there was a lot of attraction to use radar to guide cloud seeding operations. We still don't have one in our project. But that was a consideration, or radiometers, balloons, SNOTEL data, that sort of thing. Rolling that into that initial feasibility, had to make some assumptions. It's like, well, let's just make some assumptions about what a program might look like, and what are the costs going to be to operate that scale of a program. So we started off with one aircraft, just kind of a thumbnail based on some guidance from DRI, and they had some scientists there at the time that aren't in the profession anymore, but they had a long history with operational cloud seeding. They gave some really good advice early on. And it's like, probably in the 15 or so generators in the Payette, how much benefit is that likely to give us? Literature suggested, the typical 5 to 15%, kind of focused on the 10% for precip, but what does that mean hydrologically? And I initially worked with regression equations that the Bureau of Reclamation had as far as, well, if you have this much snowpack, you're going to expect this much runoff. Doesn't tell you anything about the timing of it. So I was able to go in there and manipulate snowpack numbers and come up with some estimates for runoff. And this is kind of where my background and my day job at Idaho Power came into play. I was doing water supply forecasting. So we had hydrologic models. We were working with HSPF at the time and the SAR model. We looked at hydrologic modeling and manipulating the precipitation records of seeded and an unseeded sort of assumed scenario. These are all assumptions. How much additional runoff would we expect to get, and when would we see it? And, when we ran those numbers through our hydro system and looked at what the effectiveness of producing additional generation was and how that offset cost to replace that generation from other resources, it looked pretty attractive. It was definitely worth pursuing. But all that was based on assumptions. I needed to confirm some of those assumptions to move to the next step. And one of the first things that some of the folks at DRI encouraged me to do is go get a climatology of what is going on in the watershed. We really need to know how many seedable opportunities you have over a winter to really drill into the next level of efficacy of cloud seeding for that watershed. DRI at that time had a 2-channel radiometer that was the size of a large U-Haul truck. We parked that thing up in Lowman, Idaho. We had a pretty fancy weather station to go with it. And we ran that system through the whole winter, the entire winter, water year 1995. We were pretty fortunate that 1995 turned out to be a fairly typical winter. We had a typical number of storms through the season, and we wound up with a great data set to confirm what our normal-ish opportunities might look like, as well as some of the precipitation records that went with that, to do a more deep dive into the hydrologic and the generation analyses that went with that. Again, fast forwarding to today, there's a lot of retrospective climatologies that are available. And so, you don't have to go out there and luck out like I did to collect a season of data that you can use for a much deeper dive. But there are some disadvantages to those climatologies. They don't necessarily simulate the supercooled liquid water or the natural ice conditions, the ice nuclei that Mother Nature provides out there. These are some of the things the previous presenters have touched on. So those climatologies are great, but they're not the end-all be-all. You want some observation data to know about these things. All right, the next level of a deeper dive. The climatology found that the Payette was a great candidate for seeding both ground and air. And in this time frame, I took Arlen Huggins on a road tour through the Payette watershed. He was one of the scientists at DRI that I was working with. Arlen had a great history with cloud seeding in the past, and I was like, let's go lay some eyes on this place. We really want to know firsthand if that's a viable place. We're driving through the Payette watershed, and I remember distinctly, Arlen, we stopped up on a high point. We was looking out over all this very rough terrain, and he's like, oh my word, you can't miss this place. I mean, it's not, there is no way to miss with cloud seeding there as long as the weather conditions were conducive for seeding. One of the things that, that visit confirmed, though, is like, there's no way you're going to hit this well with manual seeding equipment. Some of those concerns with version, if we were to put that equipment down where the people live, and then just the terrain and being able to have a dense enough network to get the seeding material where it needed to be. Aircraft was still looking viable. The refined cost estimates from the experts in the field, we had a better idea of how much equipment to put out there, flight hours, seating opportunities, that refined our cost estimate. And in parallel with all this, we continue to refine our hydrologic modeling and the benefit estimates from the generation side of things. But one of the things I've got noted there in that last bullet, there's still a lot of assumptions. We did a lot of sensitivity analysis. Well, what if this assumption is too high, or this assumption is too low? And vary those things so that you can kind of bookend, what your high and low expectations are, just so that you can communicate that with the stakeholders. Remote seeding equipment, the options then and still are limited on where you can get that equipment. At the time, DRI was an option. WMI was just kind of in the infancy of considering it. We initially purchased generators and ended up building our own since then, and we still build our own. We're still refining them a little bit, but we found them to be a very robust design. We might run a generator about 100 hours a season. Over a 5-month season, that's like 4 days of continuous operating time. You want those things to work when you need them to work. If you miss some of those seeding opportunities, you put a lot of investment into all for naught. And then considerations for instrumentation, weather stations, again, radiometers, weather balloons. We use the weather service balloons, but we also launch our own balloons that are more germane to the target areas that we're trying to put snowpack in. Precipitation gauges, Derek talked about some of this before. Those are critical to knowing what's going on. We have a pretty extensive modeling system that we use, but having these observations is critical to knowing when it's go time to either dispatch an aircraft or turn ground equipment on. Another thing is learn the permit process for any of that equipment that goes on the ground. Because you're going to be looking to put it on public lands, that can be pretty arduous. My experience I mentioned in the Boise, they wanted a full EIS. They wanted us to hire a couple of people for them to review the EIS. They handed me their brand new land management plan that was 3 volumes thick and basically gave me the message, get out of here. I was in Colorado helping the city of Grand Junction install some of our equipment on the Grand Mesa. And one of the first questions I asked when we rolled into town, Slade, do you have a permit before we put this equipment on the ground? He goes, oh, don't worry about that. I'm going to have coffee with the district ranger in the morning and I'll get the special use permit signed then. I'm like, whoa. So it varies. You know, you get to know who you're dealing with and what it's going to take for that permit. Aircraft seat. We were still very interested in pursuing that. We have a corporate aircraft. Some of the questions early on, well, gosh, can we just use that? And as we drilled in, it's like, who's going to fly the thing? Do we have backup pilots in case, you know, somebody's sick? And again, you have, you know, a limited number of hours to fly in a season. You want to have a pilot available for that plane. Backup aircraft, they go down on occasion. And maintenance of those aircraft, the type of aircraft, the performance and icing conditions. Instrumentation on those aircraft. I mean, we're getting more and more devices all the time, and knowing what's going on where that aircraft is huge. A heated hangar so that the thing is de-iced and ready to go when it's showtime. Flare performance, access to flares, flight tracks, where are they? Having those pre-logged so that different storm conditions, like we discussed earlier, you have a lot of confidence that that aircraft is going to be putting the seeded snow mostly in your target area. Derek talked a little bit before about communications between the Mets and the pilots. You know, that's the thing. We want to be able to have that feedback. In terms of building a program, an aircraft is much quicker to get in place than a bunch of ground equipment. So that can be a quick way to get rolling. Other considerations, who's going to operate this program? Early on, I had a lot of advice to, you know, have an interest from within the company as part of the project operation. Don't just hire the whole thing out. That's sort of like, no offense to the operators, but it's a little bit like having a Sasquatch in the hen house. If the operator's doing the forecasting, owns the aircraft, they profit from the flares they burn, they're in control of the whole show, and they're reporting to you. I mean, of course it's going to work like that. Having a vested interest or a fiduciary involvement in that in the operation is, in my opinion, a good idea. Who's monitoring this suspension criteria? Who's forecasting for operation? Who owns the ground equipment? Who's going to put up the capital costs for that and the instruments? Who dispatches that equipment, turns it on and off? Who communicates with the stakeholders? I mean, that's a thing also. Derek and I spent a lot of time dealing with reporters, especially as operations are kicking up. We've got a field trip on Friday with one. It's a pretty routine thing. Stakeholders and funding. As I mentioned before, we were the only real advocate for the project in the payout, which made it really simple. We didn't have to balance who was going to pay up front. Like it either made sense or it didn't. But there were complications, and I referred to this earlier. When that interest was really ramping up for the payout, the electric utility industry was facing deregulation. At that time, even today, we're still an integrated utility. We have generation resources and the transmission resources. We weren't sure if those were going to be the same company back then. So if we did cloud seeding, who's going to pay for it and who's going to benefit from it? So we had a pretty lengthy effort with the Idaho PUC to sort that out. And as part of that initial effort with the PUC, they wanted an assessment to see that we were actually achieving what we set out to achieve. So we had a a 2-year period of intensive data collection. We worked with the Desert Research Institute on that. To go out and do a bunch of measurements, including trace chemistry, to be able to go back and show that we were actually seeding in the target area we intended to benefit. I think get your head wrapped around that this could take a while. I received the initial question in 1992. The investigation started in 93. The climatology was in 95. We did the assessment between 2003 and 2005. We went operational sort of in 2003, fully operational in 05. Build out took several more years. Today we have 17 generators that target the Payette. When we went operational in 05, we had 7. Today, I mean, it's been 30 years to get to where we are today with that project. Closing consideration, it's going to be an iterative process. You got to make some assumptions, do some analyses, and bring your stakeholders along. It's a long-term water management tool. It needs to be managed year in and year out. You've got to get past the idea that you can turn the thing on and off with budgets come and go. There will be a lot of interest for a program. More water is generally good, right? But everyone will want the other guy to pay for it. That was advice I received from day one, and the interest is soluble as water. You have a couple good water years, or even just one, and everybody's like, well, do I really need to do that next year? It's a long-term water management. Every project will have different stakeholders, regulatory considerations, funding relationships. The better you can pin that down up front, the more sustainable that project's going to be. And understand the question or the issues to be addressed. One of the things I think to understand up front too is this a project that just because we need to do something? Can this be a minimal or lower level effort? Will that satisfy the needs? Or in our case, I mean, we were really like, we want water on the ground. That water is electricity, keeps our rates down. We were after a program that would put as much water out there as was financially viable to put out there. There's a difference in cost in those scales.
Okay, I'm going to give a quick talk on a project in southern Nevada, the Spring Mountain project. This is a project that came online about 5 years ago, and it's grown significantly over the past 5 years, and it's a pretty good example of how multiple groups can help bring a cloud seeding program to reality. So the Spring Mountains, they're considered a sky island mountain range. That's in the southwest. There's a lot of these isolated high terrain spots that are isolated from other mountain ranges, and they tend to be really critical water supply sources for various places in the southwest. So this is a sky island. You're taking a look at Mount Charleston, which is just about 12,000 feet, I believe, somewhere in that ballpark, maybe even a little over 12,000 feet. The Spring Mountains is mostly groundwater recharge, so the water resources are primarily recharging aquifers. There's not too much runoff, and the runoff isn't that important in terms of water supplies for most regions around there. So there's some, one of the reasons we chose this mountain range to take a look at is because there's some kind of critical water issue going on down here. So on the west side of the Spring Mountains, there's a town called Pahrump, and Pahrump is kind of a lawless place, but they've sold all kinds of property, so there's all kinds of lots for buildable, and they all were sold with water rights. But nobody ever looked at how much water was in the ground. So turned out after about 20 some years, we started to see the aquifer started to go down a little bit at a rate faster than people were expecting. And so somebody finally dove in and took a hard look at the recharge amounts for the groundwater in Pahrump, and it turns out that the amount that they sold for property rights is about 60,000 acre-feet a year, and the recharge is 20,000. So huge problem. So the state engineer in Nevada went down, gave them 10 years to come up with a new plan to try to figure out how they're going to deal with all these lots that are for sale that supposedly have water rights, but they don't. So that nothing happened for a decade. And then in, I guess it's 2018 or so, the state finally had to make a move, and they basically made a rule that said basically if you want to develop your lot, you have to take 2 acre-feet offline. And that went over like, that was an outrage, but there wasn't any real other way to do it. And so the state passed this rule that basically said if you want to build your house, you need to buy up water rights from somebody else that hasn't developed their lot and pretty much take that lot away from having a well. And this has stood up. It's gone to court a couple times, and it's the law now. So like, if you want to develop your house in Pahrump, you've got to buy water rights from some other person that then they lose access to their water. So it's kind of ugly. So obviously there's a big problem with water here. And then we also have some other issues in the Spring Mountains. We have, we're in the Southwest, we're in the middle of a 20-year, except for last year, we're in the middle of a pretty significant long-term drought. And there's some folks, there's a Red Rock Canyon area, which is on the southeastern end of the Spring Mountains. Beautiful park, lots of great rock climbing and hiking, and beautiful desert park. And this mega drought's actually dropped the aquifer now low enough where the Joshua tree roots are are above the groundwater. So now we're seeing the loss of the trees in the park, and then there's a few springs in the park that are critical to wildlife, which also have dried up. And so this group Save Red Rocks contacted us and was like, well, do you think cloud seeding could help with the park? So we have 2 interests here. We have a ski area in the Spring Mountains. We have some other water issues that Southern Nevada Water Authority has a couple of areas that they service with groundwater from this area. So we have a lot of different groups that all have interest in water in the Spring Mountains. And so we were able to kind of put together a cloud seeding program to try to support some of these water issues. And so the first thing we obviously need to do is look and see is these mountains seedable. So the Spring Mountains are pretty far south. They're just west and northwest of Las Vegas. So we took a look at the climatology. The climatology here is not that many storms, but when they come in, they're usually pretty good. The storm track is pretty far south. The storms have to come in south of the Sierra Nevada, so they come in off the tropical Pacific, and they're loaded. So we did modeling, and then we also went down and toured the area. Like Sean said, you want to walk around and take a look at what's going on in the mountains. So we went down, took a tour, drove around, did some hiking, and we ended up at the Lee Canyon ski area. And we met up with one of Sean's colleagues, this guy Seth Shanahan, who's a ski patroller at Lee Canyon. And we started talking to Seth about snow and what goes on at the ski area. And Seth breaks out this book that he had, and it was basically observations of snowflakes for like 15 years of storms. And so we started looking at his book. It's like rhododendron, and it was every hour. And so there was rime on, and rime is a direct indication of supercooled water. So we know that if something's rimed, there's supercooled water in those clouds above there. And it was unbelievable. I mean, I don't think I saw any pristine ice ever in his record. It was like, whoa, what's it? And so that tells you that cloud seeding conditions are present. And so we did some modeling, and we did some climate studies, and we looked at how storms moved through the area. And the modeling confirmed that this super cold water is present pretty regularly. And so we felt pretty comfortable that, sure, we can see the mountains when the storms come through there. So we looked a little closer. We developed a set of rules to do cloud seeding. We took advantage of, this picture on the lower left on the lower right is a picture from the high up on the mountains up at 11,000 feet. You can see this pole here. This was something that I think Derek talked about, that where we have a webcam pointing at a pole, and so this is in super cooled water. It's hard to see, but this pole will accrete ice, and then you can see the brine ice forming on that pole. So that tells us that we have super cooled water, and it also tells us how much there is and when it's accreting. And we have a weather station up there, so we can tell when weather conditions are feasible to do cloud seeding. And then we obviously know the climatology of the storms down there, and so we set up a set of rules to do cloud seeding. We laid out a network of generators to do the cloud seeding. You know, these were, as Sean mentioned, you know, it's not, you just don't just drop a generator anywhere. You got a lot of issues with landowners and access, and sometimes you get stuff on the ground, and then you try to improve the spots for it. So it turns out the Spring Mountains, the storm winds are westerly and southerly, transitioning to more westerly, and then by the time the winds become northwesterly, the Sierra Nevada is blocking the moisture source, so there's not much precip after the winds, after the cold front goes. So anyway, we laid out a network of 4 generators, and we started a cloud seeding program, and it's been pretty successful. We generated about 8,000 acre feet last year with these 4 generators. That's our estimate. You know, we didn't direct measure that. We're still working on, we're looking at the groundwater recharge, because that's where the observations of the additional water is in the ground. But this is a great project. It's got 5 sponsors. So we have the Nye County Water District, the Southern Nevada Water Authority, the state of Nevada, the Lee Canyon Ski Area, and the Save Red Rocks environmental groups are all contributing to this project. So this is a great combination of local and state funded project, and it's successful, and it's running this year. So that's all I got.
Much. So I'm going to talk for a few minutes, and then I'm going to hand it off to Bruce Bowe to talk about this section on feasibility and design studies. My focus is on the research aspects of this, so I'm going to really be focusing on what research is needed in order to design a cloud seeding program, and then he'll talk more about some of the operational components. So for the research components, there's 3 general steps that we're trying to follow. The first involves a climatology analysis to try to answer some questions like, how often are there opportunities for cloud seeding in this region, and what are the characteristics of the clouds in this region? Then, using that information, we move into developing preliminary designs, which includes answering questions like what methods of cloud seeding might target the clouds the most effectively in this region. And then that last step for our research is to test and refine those designs, answering the following questions. How effective are each design option at targeting and enhancing precipitation, and which combination of design options is really recommended? So first, I'm going to talk a little bit about this climatology analysis. One aspect of this is we really want to analyze historical data. Ideally, we want to do this with observations. We want to know what are the temperatures, how much supercooled liquid water is in the region, and how often, what are the precipitation patterns and amounts, winds, and atmospheric stability. So as I mentioned, we generally want to do that with observational data, and the types of data that we would need for this come from various sources. Surface station data, like your ASOS meteorological stations, will provide you with surface temperature, moisture, and winds, as well as precipitation gauges. Especially in the western US, we tend to look a lot at the SNOWTEL gauge network, which provides measurements of the snow precipitation. We also like to look at data from weather balloons that provide a sounding of vertical profile of atmospheric data of temperatures and moisture and winds. This helps us know what are the temperatures at cloud top levels and the levels that we might want to target for seeding and how much moisture is in those clouds. The thing with the weather balloons is that our network, our operational network of weather balloons that the National Weather Service runs here in the US, they launch every 12 hours at 0 and 12Z. And they're in a very select few, I really put that in capitals for a reason, very select few locations. Most states have maybe 2 weather balloon sites. Some western states might only have 1 in the whole state. So that's a pretty scarce resource. We also like to look at radar data when we can. For doing a summer storm climatology, radar data tends to be a really good resource because we can look at the frequency of precipitation and the characteristics and cloud depths of the clouds with radar data. Summer storms over the plains, generally, I would say, because the radar data network is usually not very good over the mountains because the mountains themselves block the data. And so we have a lot more gaps in the mountainous regions. And so radar is a much less reliable resource over the western US in particular. But for a summer convective study over the plains, it's a pretty good resource. But there's several things that are really missing. For a lot of the premise of cloud seeding feasibility, we want to know supercooled liquid water content. How much is there and when does it occur? And we don't have a reliable operational network for that. Radiometers are a great measurement tool to deploy for this reason, but they are pretty expensive. I think Derek alluded to that in one of the previous panel discussions. Another thing that I've mentioned in the previous panel discussion was aerosol data is also not readily available in the ways that we would really need it. And then, as I mentioned, we have limited data resources from the soundings being so scarcely located and few times a day, so we don't get that vertical data as often as we want it. And the spatial precipitation patterns in the mountains are also not well understood from the fact that the radar has gaps and the SNOTEL data is just a few points. And so in a lot of our recent research, we've been relying not just on observational data then, but on multi-year high-resolution model simulations. And in my earlier panel presentation, I walked you through the development of these new simulations to the point that today we actually have these three-dimensional data sets, so to speak, for a 40-year period at 4-kilometer resolution. And this provides us three-dimensional information then on temperature. So not just temperature at the surface, but at any layer of the atmosphere, including where clouds are forming. We can get estimates of supercooled liquid water content then, winds, precipitation, etc. It is important for us to see how well these compare with observations. In my earlier panel, I showed you some maps and how it compared, but we've looked at these against SNOTEL observations closely and have shown that, you know, this is here looking at a comparison over Idaho and western Montana, that the comparison of the observations from SNOTEL in black and the model in red are actually pretty good. I think Roy Rasmussen will be presenting a little bit more on this again later. We've also compared these with the limited radiometer observations that we have to see how well does this represent the liquid water in clouds. And again, radiometer observations are pretty limited, but where we have them, we've compared it and it looks pretty good. So utilizing these high resolution long-term model simulations, then we are using them for these climatological studies to really enrich the information that we can understand about seedability of a given region. Compared to decades prior to this, we had very limited data to base this off of. So now we can map spatially where and when cloud seeding opportunities might occur. So here is a map generally showing most of the state of Wyoming. The dashed line on here is the state borders. And there were a few different regions that we had been doing some feasibility studies for several years ago. This map, the color coding is showing the frequency of time in a given winter season on average over multiple years of study that there are temperatures and supercooled liquid water contents amenable to seeding with silver iodide. So you can see that there's hot spots in most of the mountain ranges, but that not every mountain range is the same. So in region 1, the Wind River range has a lot higher frequency of temperature and supercooled liquid than, say, the Bighorn Mountains up in, oops, what did I just do? There we go, the Bighorn Mountains up in region 2. Either way, because of the limited observations, these model simulations now are a really important tool for identifying cloud seeding opportunities in the climatology analysis component of a feasibility and design study. So I'm going to briefly talk a little bit about the next two steps in this research in a combined method, because now that we...
Sarah, can I stop you really quick? Can you go ahead and share your slides one more time? I just kicked you off on accident.
So I'm back to this big dashboard here of these components. So, so I've walked through the climatology analysis, which is a really important first step. using that information, and I'm going to click back real quick in case this went off the screen, using this information of where we see these opportunities, and then we can dive in and use that data in a little bit more detailed manner for specific mountain ranges or regions of interest to understand where might we want to place ground-based generators or fly aircraft tracks based on those prevailing winds and other atmospheric conditions that the climatology illuminated. So then we can develop some of these preliminary designs. We'll place hypothetical ground-based generators or aircraft tracks out on a map, and then we're going to test those and refine those using simulations of cloud seeding with the WRF weather model that I previewed earlier in the morning panel. And we're going to use that to test each group of generators or flight tracks. And we can test those individually or in combined manners. The fact that we're able to use a modeling capability really gives us endless options for how we want to test and refine these designs, as well as combine them to come up with that ultimate option for optimal simulated results that then is the recommended design to move forward with. So just a quick animation to show, here we're placing 4 ground generator locations upwind of a mountain range. We can simulate their plume. This is the silver iodide plume dispersion, and we can look at, how well does it disperse up and over the mountain like the central one does. How many of these locations might get trapped in valleys upwind or get blocked around the mountain, that kind of thing. We can run any number of these simulations, and then we can do what I mentioned earlier, where we look at the simulation with seeding minus the simulation of the same case without seeding to map out what the simulated effect on precipitation would be. So from this example that I just showed in the animation, this is the precipitation difference map that was simulated. You can see that, again, this X was the target gauge point. You can see that this part of the generator was being very effective in enhancing precipitation and getting up and over the mountain. The one to the north was getting blocked a bit and didn't have as much of an effect. And the one to the south, and especially the one upwind, had more of a limited effect. But we can quantify this. We can study this in different case studies under different wind regimes in order to try to optimize that seeding program design. So again, these WRF weather mod simulations are really useful in testing program designs, as well as in evaluating and trying to quantify the impacts of seeding, whether it be hypothetical design or after an actual program is implemented. So in summary, these research components are in the top here, that climatology, developing the design based on that climatology, and then we test and refine the design. But there are a lot of other components that need to go into this for operational considerations, to engage with the public, coming up with those operational criteria and procedures, figuring out what forecasting data, whether it be models and or observations, are needed, suspension criteria, rules, how to communicate and manage all the data. I'm going to hand the screen over to my colleague Bruce Bowe to continue this part of the presentation.
So what I want to do is take the wonderful background that Sarah just gave us about feasibility and design and extrapolate from that into a little bit about more about how programs get going, some do's and some don'ts, and some different things that I've observed over the years of my involvement with the program. Go ahead. One of the first things I want to mention is intuitively, when you think about water availability, we tend to go towards surface water first and groundwater second, and only after those two don't work for us do we think about the atmospheric water. This is a graph I created a few years back that shows time in weeks and a logarithmic scale around the bottom. And to make it more interesting, more understandable, I've put 1 hour, 1 day, 1 month, and 1 year on there. And so you can see how the time goes by. The reason for doing this is because the atmosphere is in constant motion. And with it, it carries water vapor and condensed water and clouds in various forms. And it's always moving, and it can recharge very, very quickly. In addition to advection, that is the bringing of water in with the air as it moves, we also have recharge by evapotranspiration, evaporation and transpiration from plants at the surface. So it recharges much faster than these other resources. And so given that, it really is a very viable target for being able to get more water out of it. The trick is how to get that water that's up there in water vapor to the ground. So looks like I need Kayla to advance the slides, or I can dart back and forth as well. One of the things we've learned very clearly this morning is that cloud seeding works better in some places than in others. And sometimes the potential can be assessed in a straightforward way without time-consuming analysis, and other times it cannot. If you'll go to the next one, please. An example I'll cite here is Williams County, North Dakota. They recently approached Weather Modification International about doing a wintertime snowpack program for them. Those of you that know the topography of North Dakota know that the mountain removal project was completed a long time ago. There is no orography to speak of. The highest point in the entire state is barely 3,000 feet. And that's already in one of Darren's operational target areas. And Williams County simply was not well suited to a wintertime program. There was no barrier with which to work with. The county commission there asked me, well, couldn't we just seed storms as they come through? The answer is yes, you can, but there's no place to really focus the result, and there are not reservoirs to store it in. And so, long story short, when they asked me, it took me a day to get back to them and say, you know, folks, this really isn't even worth a feasibility study. Another example here is sometimes the potential is less certain, and at first glance it might look like there's a great opportunity. And I'm going to borrow a term we heard earlier in this section about the deeper dive, and talk a little bit about the Bighorn Mountains. Sarah showed a panel a minute ago that showed 3 regions. One of them was Region 2, and it was the Bighorn Mountains. To the southwest of the Bighorn Mountains are the Wind River Mountains, and the feasibility there, the opportunities, was red all the way down the crest line. Lots of opportunities. Further to the south, in the south central part of the state, were the Wind River and Sierra Madre ranges, and they also had a lot of red. The Bighorn Mountains, when they were evaluated, showed only a very small area of kind of red and orange in the central region. And most of it, though, it's a very expansive high mountain range with a peak well above, I think there's one that says 12,000, 13,000 feet in it. Really not much opportunity. The reason for that, it turned out, is that the escarpment, the west side of the range from which most of the weather systems come in is very, very steep. And there's a strong tendency for temperature inversion to simply block transport from low-level generators there. And so the model determined that the opportunities were really not very frequent, and because of the limited resources within the state, the other mountain ranges that had more potential, and there are other ranges like the Salt Range in Wyoming that also is being seeded, but not by the state. The determination was made, we're not going to expend resources on this range at this time. So if you go ahead, Kira, to the next one. This has already been said. We can go to the next one. Yeah, stakeholders are the persons having an interest in the program. And go ahead, Kayla, walk down through the rest of the slides here. For some people, a stakeholder is the people that have a direct benefit from it. A farmer may support a program because with more precipitation, they get better crop yields. Implement dealer might benefit in a secondary way because with better yields comes more income to the farmer and he buys new machinery. For still others, though, the interest in the program might come just from the fact that they know it's publicly funded for tax money and they're paying taxes. And so they want to know. And all of these viewpoints are legitimate and need to be respected. Let's go ahead. Public information, we can step down through this one too, Kayla. There's the bullets on the side. Full disclosure about the program and transparency is always the best path. Be upfront with what you're doing, why you're doing it, and how you're doing it. Understanding the technology's limitations is essential. Cloud seeding needs to be considered a tool, not a means to an end by itself. It's not a standalone or short-term solution. WMI always says that to a potential client up front, and we talk about long-term applications to put yourself in a better position long-term. This is a diagram. You've seen many versions of it in very tiny form in all the presentations up till now because they put multiple screens on the same one. But basically, this is a water year curve. The heavy black line is the median snow water equivalent from SNOTEL site. The dashed line that's vertical there is the current date, and this is as of yesterday, so it's a day old, it's the 14th. And you can see the dashed red line is the suspension criterion for snowpack that's in place for the Medicine Bow and the Sierra Madre ranges in the state of Wyoming at this time. So if the snowpack collectively, the red line down below, for all of the SNOTELs there, for the Sierra Madre range should get above that dashed red line, that would be a flag to cease operations. This is just the sort of thing that's out there. I put it in this slide because it's available online to anyone at any time. They can go look at this, not only just for this range, but for all the ranges. They can see how the range, each individual SNOTEL site is doing, or all of them. A shout out here to Adam Brainerd, who made all this possible for us. I used to have to do these weekly by hand online. So many, many hours saved. Next, please. Do all projects need a feasibility study before they begin? The short answer to that is yes, it is. And the depths of such studies vary though. Feasibility studies are not without cost. And the more thorough they are, the more expensive they become. Numerical modeling, especially when you're processing years of climate data, requires a lot of computational resources. Those are not cheap. The scientific ability to go through that isn't inexpensive either. But at the very least, any program that's contemplating beginning needs to make an assessment of what the objectives are and of the local climate. And those two things will provide an initial idea if the program could be successful. You want to go ahead there with the next bullet there. Thank you. A feasibility study establishes the baseline for expectations, which is very, very good. And also the findings from that can play a critical role in the project design. And they also lay the groundwork for eventual evaluations. You can't evaluate something that hasn't happened yet, but you need to have that in mind as you begin. If you would, please, there. Value. Ultimately, it's the value of the water that you get on the ground that determines program feasibility. And at this point, I need to jump back to a comment that was made very early in the day about water created by cloud seeding doesn't have any ownership attached to it. Water law in the United States is such that any additional value that might be created by clouds, water that's created by cloud seeding, is considered part of the natural pool and is allocated according to existing water rights. And so saying that first, keep that in mind as I go through the rest of these bullets. The analysis of the climatology of the clouds and weather situations provides an estimate of how often seeding opportunities would occur. We have to make assumptions about how large a subset of those opportunities are seedable, because we know we're not going to target everything that's seedable just because of response times and complicating ramifications. One of the things we sometimes run into in Wyoming is that our base airport has adverse conditions, freezing drizzle, for example. We're not going to take off in a freezing drizzle. So there is an opportunity missed potentially. So we have to consider that too. And when we get an estimation finally of the additional rainfall or snowpack that can result from seeding, we can apply that to the intended target and scope and get an estimate of the precipitation, the complete gain acre feet, which is, Sarah spoke to this at length earlier on in the day. And my final note here is the big blue lettering there. Value is often correlated very highly with location of where that water is. And I think the going rate a few years ago in Wyoming was somewhere under $50 an acre foot for irrigation purposes in the south central part. And I'm told that it might be triple or maybe even 4 digits in the southwest. Is that right? I don't know, but it's much, much higher. So precipitation is, of course, a benefit in the short term when it supplants the need to irrigate, provides additional growth to dryland crops and that sort of things. It also will help, of course, anybody that's growing anything, makes you don't have to water your lawn and all that. Medium term, it builds up soil moisture, which helps when drier times come. And longer term, it can permeate deep and recharge aquifers. That seems like a pretty tall order for a cloud seeding program, but our current program in the Middle East is over an area that has a very sandy soil, and the water that hits the ground that doesn't run off is straight into the aquifer. It's so porous, it goes straight in. And the bottom line is that there's a benefit to wildlife, reservoir storage, and of course then hydroelectric power generation, general water supplies, and of course it trickles down to municipal and industrial uses as well. So go ahead, Sarah, if you would please. There we go, evaluations. My experience has been that programs that are purely operational, that is all they do is seed clouds year after year after year, don't survive long term, because at some point the need to know builds up to a point where too many of the stakeholders really want to know and say, well, we don't know if this works or not. We've been doing it for years. Maybe it does work and we're just used to what it does, but maybe it doesn't work either. And so the program ends. So when you start a program, it's always best to plan with a future evaluation in mind, even if it's acknowledged that it might be multiple seasons from the time the program begins before you have enough data for an evaluation to be meaningful. And another thing about evaluations is I really strongly encourage independent evaluations. Sean mentioned a little bit ago that having an operator that evaluates his own program is like having the fox in the hen house, and that's a very real possibility. For that reason, WMI does not evaluate its own program. We have not done so, and we declined to do so when suggested. And so we think qualified persons other than those running the program need to evaluate it. I'm not going to provide any details here, but we do have a program, an airborne seeding program in Colorado, which has a statute under its Water Conservation Board regulations that requires an annual evaluation. That program in Colorado is being paid for by the client, the Jackson County Water Conservancy District, and is being done by Dr. McDonough at DRI. And so that's an example of how that can work. Next, please, Sarah. Design. The design needs to include means by which you can identify when the opportunities are occurring. In a warm season program, that's usually radar. In a cold season program, it's webcams, it's satellite imagery, it's radiometers are really, really key. You can use cloud radars that can help tell when there's, if you have the resources to deploy the instrumentation, you can tell when there's suitable conditions. Surface precipitation measurements are always very important. The more, the better. If you don't have them in some capacity, you're going to be challenged. I guess when you don't have any surface precipitation measurements because the program's not funding that, you can go with the SNOTEL data, which is done quite commonly. The NRCS has lots and lots of SNOTEL sites in the western United States. Sometimes the problem is not having them where the program is, and so it's difficult to evaluate a program when you have very few sites within the target area or nearby to compare. For warm season programs, you can ground truth or weather radar estimates of precipitation with the surface observations. That can be very, very helpful. There's still limitations though. One of the biggest challenges you have, particularly in drier environments, is there's a deep subcloud layer that the radar is probably not sampling. So what you're seeing in the low scan of the radar might be above where the precipitation is, or it may be at a range so far from the radar that you can't see it. So there are complications. Suspension criteria we talked about. You've seen it mentioned several times now. I just showed you the graph that has the suspension criteria in it. The Weather Modification Association recommends strongly that all programs have suspension criteria. They should. I've been involved in a few that haven't. Without exception, they have been overseas. And sometimes people just don't see the need for it until they have a problem, like in floods in Jeddah. And they're saying, oh, why didn't we see this? Well, it's because you didn't have suspension criteria. That actually did not happen to us, but they did have a flood in Jeddah last year when no seeding was occurring. And we reminded our client, you really need to establish a criterion here, because had the program been ongoing and there was no criteria, there could have been a problem. And the last item on this is design your program with some kind of a component for public information and outreach involved. Have, like was mentioned earlier, a technical advisory team, a regular period where people can come and just ask questions, have public meetings. One of the things that we did during the Wyoming Weather Modification Pilot Project that was very effective in that state was we being the Water Development Office, would accept invitations to go speak at various organizations throughout the state. That included stock growers associations and irrigation districts and Rotary clubs and what have you, so you can get the word out there. Because in the absence of real information, people will imagine what they think is going on, and bad things can result. Is there anything after that, Sarah? Yes, data management. Detailed records need to be kept of the times, locations, amounts, and types of seeding agents dispensed. Not only is this necessary for evaluation, but it's also not in that detail, but the amounts of seeding agent and the dates on which they were used is required in the United States by the National Oceanic and Atmospheric Administration for airborne and ground-based programs. And when you know when you seeded, where you seeded, how much you seeded, you can combine that with other physical observations, radar or precipitation, for example, and perhaps have enough there to do an evaluation at some point. Project forecasts that are done, most projects do this on a daily basis. They're formally issued in some format, very often by email, sometimes by weather briefing as well. Those should be archived. Verify them the following day and then archive them so you know how you're doing. And the last thing here that's really, really helpful, WMI has really taken this a long way in the last half dozen years, especially the last 3, is a numerical weather prediction. We do that in-house now. Adam and his team have developed some wonderful products specifically designed for weather modification. Things that are plots, for example, of supercooled liquid water. These are available. They update in 1-hour time increments, so we can get through with that. And they're very, very useful not only to our forecasting team, but those that are conducting the operations. They have access to these as well. In a more informal environment, I would log into that right now and give you a quick tour of the site, or ask Adam to do that since he's more proficient at it than I. But that's a very, very healthy thing for a program to have. It allows the public to see what you're doing, and it allows that information to be available to all the stakeholders. Anybody that's the sponsor of the program, anybody from the public is curious can go and look. I'll ask you, Adam, because I can't remember the exact numbers, but we have a website set up for the program that we run in Alberta, Canada. It's a warm season program with lots of thunderstorms on it. Part of that website includes a radar. And during storm events, we get, what, thousands of hits? Yeah. From the public per hour?
It broke our site, yes.
They can actually, so many inquiries, they can bog it down. So, it's a wonderful public relations tool as well. So, is that the last one, Sarah? It is.
Yep, that's the last I have. Sorry, I
That's
didn't
the
get your
last one.
updated slides up
Yeah,
there.
if we can get the other slides in at some point, what I'll do is I'll show a graphic that actually shows some resources that I think are very helpful. that everybody should take note of. Regrettably, I did not yet assign a QR code on this slide, so we can't really see where to get it. I can just tell you, go to the American Society of Civil Engineers, ASCE.org, in publications, and look. And there are a couple of documents that are regularly updated by a team of people, experts in the field, that include some people that are in this room, that deal with precipitation enhancement. One is called a Guidelines Handbook. It's manual number 81. And it looks like we might even get to the point where we can see. There it is. That's it. These are the two. Thank you, thank you, thank you, Kayla. These are dated now because they're updated every few years. They don't get stagnant. The guidelines document on the right is presently undergoing, it'd be now the 4th edition, I think, not the 2nd. And on the left is the standard practice document. These are done by committee. They are publicly vetted, and they are published by the American Society of Civil Engineers. You can see all the logos down there. We are now going through the ANSI standardization approval process as well. So these are documents that really spell out in a lot of detail, a lot more than we can put in this workshop, about how to go about generating a program. So.
All right, well, thank you, everyone. I know you heard from me a fair bit this morning, but again, my name is Kayla Golden with the Idaho Department of Water Resources, and I represent the state of Idaho as their cloud seeding program manager on behalf of the Idaho Water Resource Board. So this afternoon, I'm going to be fairly brief, and somewhat of what I have is sort of a summary of some of the points that you heard in our breaking ground, but some of the major considerations that we think should be taken into account when you're looking at developing a program with regard to budget, program commitments, and supporting policy. So the first thing I'm going to talk about very briefly is budget development. So you know you want to get a cloud seeding program together. You've done your feasibility and design. You kind of have an idea of what type of infrastructure is possible and what type of seeding is possible within a basin. And so now the next step is moving forward with implementing that project. And so one of the first things, with the feasibility and design is they're going to tell you the full potential generally, but the budget doesn't always match up, or you might not always have the funding to build out a program to its full potential. For example, you may have a basin that is really ripe with opportunities for both ground and aircraft seeding opportunities. But you don't quite have the funds to maybe fund an aircraft for that basin, and you only have money to get a ground program in. And so those are the kinds of considerations once you get your feasibility and design put together and you see what all the options are and you start accounting for those costs that you'll need to be thinking about. So I guess the long and short point here is that just because your feasibility and design says that you might be successful with 15 ground generators and 2 aircraft, your budget might not meet that size of a program. And so really the key point here is that budget will constrain the size of your program. And one of the things that we've learned here in Idaho that's been super beneficial, and I think one of the key points that has made our program successful, is our ability to leverage funds. And so here in Idaho, you did hear from Sean Parkinson earlier kind of on how our programs developed, and I will talk more later about what that relationship looks like with the state. But basically, the success of our programs here in Idaho has largely been because of the collaborations that we have created here and our ability to leverage funds. And so what I say by leveraging funds, I have some images over here on the right-hand side. And you can see here on the right-hand side, you maybe saw earlier from Sean Parkinson's talk, but this is a cutout of what we consider the west central region of Idaho. The Payette River Basin that Sean talked about is up here, sort of this long piece up here. And these basins are separated by this red line. So the Payette Basin here in the north, we have the Boise River Basin in the middle, and the Wood River Basin in the southern portion. And so we operate this region sort of as one region. However, when it comes to funding these basins and the infrastructure, the cost for that is actually shared between the basins. And so that's one of the things that we're talking about when we say leveraging funds. So for example, the Payette River Basin has a number of generators, as well as the Boise and the Wood, that are each dedicated to those basins. And along these basin divides where you see these red lines, we also have generators that can be shared between basins. So in other words, when conditions are prevailing to benefit one basin or the other or both, these generators can be used to support either basin. And the benefit of that is then that translates to the cost. And so our stakeholders in all of our basins where we operate cloud seeding do pay in a portion of the cost for operating. And so by sharing the infrastructure, we then allow that ability to share costs in between basins. And that does make things a little bit more affordable. Same thing with aircraft. So for our regions over here, we have about 2 aircraft that support this entire region, split between the Payette and the Boise, and over here between the Boise and the Wood. Aircrafts, like you heard earlier, can be up to 50% of your seeding opportunities. They can also be the most expensive portion of your program. And for that reason alone, that again creates benefit when you have multiple basins where you can operate regionally, but you're benefiting individual basins that can then share costs for those operations. So leveraging funds when you're looking at costs for developing a program can be very key. So some of these programs, aircraft, for example, you can be ranging in the $500,000 to $700,000 range to run an aircraft operationally for a season. So that's a pretty significant cost. When you start, we'll hear later on some monitoring and analyses, but when you start translating that to water on the ground relative to an acre foot cost, it is pretty darn cheap for water. And you will see that a little bit later. But the ability to share costs between basins or leverage funds between stakeholder groups is pretty key to the success of a program. So the other thing I wanted to touch on is program commitments. And so you did hear a few folks talk about this a little bit earlier, but cloud seeding really is a long-term water management tool. It's not something that you can start and stop when there's a good water year or a bad water year. And unfortunately, because of the need for education, the support tends to go with the water year as well. So when there's a lot of water, people don't necessarily believe in cloud seeding or think it's that much of value, and vice versa. So when you're in a drought year, it might be the holy grail. And I'm here to tell you it's not the holy grail, it's just a tool in the toolbox. But the long and short of that is that cloud seeding is something that has to be consistently operated over time. It's not something you can start and stop. And not just for the efficiency, but you've heard folks talk about, implementing infrastructure and some of the hurdles that you have to go through with implementing infrastructure. So when you start thinking about stopping and starting a program, on varying years, it becomes extremely inefficient and cost inefficient to start and stop. And so we like to tell people that cloud seeding should be viewed as an insurance policy. Just because you're having a good water year doesn't mean that you should stop cloud seeding entirely. A little bit of water, even in a good water year, could carry out into something such as storage carryover for the next year. There's a lot of different benefits to cloud seeding, even though you are having a good year. So we like to tell folks that it's an insurance policy. You're building up over time. And just because you don't need it this year doesn't mean it isn't going to be beneficial to you over time in the longer run. So the other thing I wanted to touch on was long-term program commitments. And so we don't deal with it so much here in Idaho, but in other states, when their programs are funded by legislature and they require annual approvals for those funding. And so when you have legislative members changing in and out, every couple of years, you have that dire need for education. That's a need to continually re-educate people over and over and over again. And so when you're having to go to legislature every year to battle for funds for your program, that becomes a strain, on the program and the success of it in the long term. And so really considering multi-year, longer-term agreements is generally, I think a lot of us would argue, much better than doing annual one-over agreements, because it does help support, the longevity of your program and keeping that support for a number of years. One of the other things with commitments that I wanted to talk about was potential statutory limitations. And so many of the states that participate in cloud seeding do have some requirement for their stakeholders or their water users to pay into the program. So some states will pay into it, but a lot of programs, water users are required to pay as well. In Idaho, an example that we ran into here, we have water users that pay through water districts. A few years ago, we discovered that water districts didn't actually have the authority to collect money for cloud seeding. Their authority was only to collect money to operate the water district. And so we had to go back to legislature and ask for a modification so that they were able to contribute contribute funding towards cloud seeding. So that's just one example of potential statutory hurdles that you may run into, or things that you have to consider when you're thinking about how you structure the program. So I sort of stole this analogy from Jake Sarago in Utah, and you may see this a little bit later, but it's a really great example. And, we talk about the three-legged stool or the corners of the triangle. The triangle, everyone likes to joke, is sort of is the strongest shape out there. And we feel like it's the strongest shape for a lot of reasons in the success in developing a program, because really having that interaction or that collaboration between your research and operations, your stakeholders who are interested in this water, and then your policy leaders and your resource managers who sort of help the development and implementation of these programs, having that relationship and consistent communication is really, really vital to the success of a program. So you heard earlier in our talks today, some of the research folks that were speaking is, there is definitely a dire need for more research to answer some policy questions. So we have definitely figured out the base concept model. We've proven that it works, that we can make, more precipitation, if you will. But that's a major advancement. So cloud seeding has been around since 1946. Snowy, the research that you heard about earlier with the radar and the zigzag patterns, that happened only 5 years ago. So in the terms of science, or the speed of science, that's sort of like yesterday. That's this lightning speed. There's still a lot of information and a lot of research that has to go into cloud seeding to be able to answer some of these questions. Questions like, how well does it work? How much water are we putting on the ground? How does that impact the hydrologic system? Is it safe? The downwind effects that we talked about earlier. Are we robbing Peter to pay Paul? There's still a lot of research, especially as more and more programs come online and we're wringing out more and more of that water across the West. That might be a question that we have to dig a little bit deeper into. Demonstrating benefits. So when you're going around advocating for funding from your stakeholders and who's going to pay for this program, the first question they're going to ask you is, why should I support this program? What is the benefit for me? And that's been a pretty tough question for a lot of folks to answer, directly, because translating that, one-on-one benefits to individual water users is not something that we have the tools or resources to do. But we do know that we can benefit an entire basin or an entire watershed by putting more water broadly. And so I think most programs that operate, most of us have some sort of language in our statutes that say that basically cloud seeding water is treated like natural water. And in Idaho, our legislation states that, seeded water is not treated any differently than natural water, and it's all distributed according to the prior appropriation doctrine. And so, I guess the key point here is that we don't quite have the ability to say who benefits, but having more water in a basin is certainly a benefit to everybody who uses water in that basin. So the next part that I wanted to talk about today with program implementation was some regulatory considerations. So when you're going through the implementation of a program, what are some of the major hurdles that you have to deal with? We've heard from Pat earlier and some other folks on NEPA or some of the other processes for implementing a program, and that's not something that we've had to deal with as much here in Idaho. And so the next speaker that we have, Rachel Gray, is from the Santa Ana Watershed Project Authority, and she's going to cover some regulatory considerations with implementing a program.
So we've noticed some common themes throughout some of the presentations we've heard in the workshop. And so for us at the Santa Ana Watershed Project Authority, or SAPA, we're a local government entity. And so we're subject to compliance for the California Environmental Quality Act. And so our pilot program is defined as a project under CEQA. So we hired a CEQA consultant to perform an environmental review to determine if the project would result in any significant adverse environmental impacts. And so an initial study was conducted to determine how the project might impact the following aspects. You see a bunch of aspects or elements that are shown on the right side of the screen. And so ultimately, we went through the process. There's a public comment period. There's tribal consultation, so on and so forth. We were able to adopt a mitigated negative declaration. And so there were a couple of potential environmental impacts that were found, mostly related to sensitive species and habitat. And so we are implementing a mitigation monitoring reporting plan for our project. Next slide, please, Kayla. So one of the key hurdles, I guess, it just didn't occur to us how long it would take to finalize site access agreements. It was definitely a much lengthier process than we had anticipated, maybe over a year and a half. And so just in terms of like the elements and negotiating, language and legal reviews, it was just a tremendous effort, with our site sponsors, as well as, our agency. And so some of the elements that we had to consider or negotiate were the fact that some of our sponsors were requiring commercial general liability of insurance of up to $4 million, definitely liability insurance. Language included about remediation in the event that there was any release of, any of the chemicals. And indemnification is huge, and there's a bullet on indemnification, but it seemed like, people were really nervous about the liability, right? Being, and the public perception. So definitely language about indemnification, pollution liability insurance, and then hazardous waste indemnity as well. Next slide, please, Kayla. So just in terms of the Federal Aviation Administration, we don't have an aerial component in our pilot project. However, we did assess the feasibility of having an aerial program. But as you'll see, I don't know if it's as evident, but we have, several, we at least have 3 major international airports and a lot of local municipal airports within and adjacent to our watershed. So even if we were able to obtain like the proper permits, waivers, and licenses, we would still be, subject to air traffic control. And so, for example, an aircraft can be grounded when operational conditions are ideal. So we didn't move forward with an air program in our watershed, but definitely something we had to consider. Next slide, please. So just some additional environmental consideration. Something that came up was, that a long-term program could potentially contribute to greenhouse gas emissions, particularly the release of carbon dioxide. But based on our analysis, we determined that, running our 15 seating units over a year, the emissions were similar to that of a work truck on an annual basis. And so, our whole idea was, if an insurance carrier could insure a vehicle, and they're releasing a certain amount of carbon dioxide, then our program is also just as sound, because the insurance company wouldn't otherwise insure the vehicle. And then the other component that we're all aware of is the impact or concern of silver iodide in the environment, and Pat did a great job, as well as others, in terms of defining the silver iodide, and it doesn't associate, and then also like the low levels of concentrations that we're finding in the environment. And then just generally our findings with the impacts associated with the operations would be less than significant. Next slide, please. So we've heard a lot about suspension criteria, but it's critical to the success, of any program. And we've heard about flooding situations, with increased snowpack and warm rain on snow. I think of particular interest to us because there's been quite a number of fires in our watershed over the last few years. It's just working really closely with our flood control districts and monitoring conditions to ensure that we don't contribute to debris flows. So that was definitely something that we're watching closely, as well as our normal, severe weather conditions, so on and so forth. Next slide, please, Kayla. There was also concern of sound and noise. So we did a study for one of our units. It's our automated high output ground units, and there's an instantaneous sound output of 105 decibels 1 foot away from the unit, which is like, an instantaneous clap, but then about 45 decibels during the consistent burning. So we provided that information to the public as well. Next slide, please. A very real reality that we deal with is, vandalism. It's a real threat. Our equipment is vulnerable to tampering from, out-of-house communities and trespassers. Even though, most of our units are on agency, public agency lands, it's not security 24/7. So definitely a real threat. Something that we're monitoring closely as well. Next slide, please. And then just collaboration. Collaboration is critical to the success of any program, whether it's with, our regulatory agencies, through the CEQA process, our Regional Water Quality Control Board, or Department of Water Resources, as well as our partnering agencies, adjacent agencies, public agencies, cities, so on and so forth. And then the public, I mean, it's just critical. We've done so much outreach, and I know you guys all have as well. And I'll talk some more about that when I talk about our program later in the presentation. Next slide, please. And then we have, public perception, just, again, communication is key, right? And having the resources that I have being part of this organization is just, it's critical, right? So to be able to answer some of these questions, some of the things that we've heard about was, obviously the toxicity of silver iodide, somebody was like, oh, well, I'm allergic to acetone. So just having, some scientific, responses to be able to provide. And of course, cloud seeding doesn't work, whether we're doing manipulation, chemtrails, so are common themes, but being able to have the resources to be able to communicate on these issues is key. Next slide, please. And then, yeah, another element is just, contracting. There's such a limited pool of operators out there, and, the RFP process is a lengthy one, and just even being a new project for us, defining the scope and what does that look like can be challenging, right? Even through our RFP process, we got very limited responses, due to the specialized nature of operating such a program. So that's definitely something, that's a limiting factor. And then also just operators in general, we have some of our public agencies, they were willing to operate the units, but many of them didn't want the liability. So just finding private contractors, and then just building in compensation, because that's also something that we found is critical to finding operators to be able to operate the units.
Well, thank you, Mark. As Mark said, I'm Cloud Seeding Coordinator at the Utah Division of Water Resources. And Kayla asked me to speak a little bit today about this topic. I think perhaps because we're in the midst of acquiring and implementing a large-scale increase to the cloud seeding infrastructure throughout the state. As Mark mentioned, we do have over 160 manual ground-based cloud seeding generators in operation throughout the state. Most of the mountain ranges which contribute significant water supply are actively cloud seeded, and these manual generators have that coverage. And so the manual generators were placed gradually as the state program built up over the last 4 decades, and that equipment is owned, maintained, and operated by the consultant who does the cloud seeding operations. And but last year, last legislative session, the Utah legislature dramatically increased the statewide budget for cloud seeding, and with that increase, we've made plans to deploy remotely operated ground-based generators. And the reason for this is they have one is there's considerable costs to make the initial purchase or investment in remote generators, which is funding we didn't have before. And then the operation and maintenance is also higher than with the more simple manual generators. So it was really never part of our program because of budgetary constraints. So now we have a goal of citing these. And folks have covered this. Derek covered a lot of this in even more detail, but typical infrastructure that is used in Utah and pretty much anywhere where cloud seeding occurs are either ground-based generators or some kind of operation, some kind of aircraft outfitted to target. And as Bruce covered in detail, that type of infrastructure, and it depends on what your goal is of the program and the type of cloud seeding that you're doing. And then, as others have shown, acquiring equipment that helps to make observations of the weather, both for real-time operations and forecasts, as well as to collect that data that can be used by researchers. So I mainly want to talk about these remote generators and the changes that we're making to our program, because we're in the midst of trying to figure out exactly how to do this. So I have lots of questions. Some of them we have answers to, some of them we don't exactly. But the goal is to eventually deploy 120 remote generators, which is quite ambitious. And we'll do that over several years. And one of the advantages that we have is that since we have been operating these programs for several decades in some areas, we've been evaluating and assessing the programs, and also in doing so trying to determine how we could improve the effectiveness and efficiency of the programs. And a lot of times what we found was that remote generators would really help the program. And part of that is because manual generators have to be turned on and off by some human being, and so it has to be in close enough proximity that when they get a call or an indication to turn that generator on, that they can do so in a timely fashion to be effective. And but because of that, because of the need to be within proximity of a human operator, those generators are sometimes not in optimal locations, because it'd be better to have them at higher elevations, closer to the cloud base, as close to in-cloud as possible. And in some of the very important areas where we seed, we have temperature inversions, and so that stability traps material and doesn't allow it to get up into the cloud and into the target area. And so these remote generators can allow us mostly to get above those inversion layers. And so we had already identified about 40 sites throughout the state where we would put remote generators if we could get them. And so that has allowed us to, we built 20 last year, and have this year I think this season we'll be able to deploy all 20, partially because the winter has been slow to get started, fortunately, but allows us to, I think, to get all the generators out there. But that's one of the major considerations, is knowing, figuring out where to put the equipment. And so, as Rachel mentioned, one thing that can be a little tricky in the weather mod or cloud seeding world is that there aren't that many experts or operators who can do this kind of thing. We just put out a notice for an open position to be a cloud, to get more staff to work on the cloud seeding program in Utah. And it's very hard to find someone who has, experience or knowledge about cloud seeding, let alone, that can actually effectively operate the program. So for us, finding the vendor that we use is a vendor who has offices in Salt Lake City. And so that geographical proximity makes a big difference to us, because we visit each other in person, they come to our office, we go to their office, we go out, we have a good working relationship with them. And we've been working with them for several decades. So there's a lot of history, and it just works out really well for us. Another advantage of determining who are we going to purchase this equipment from, it has to do with their willingness to work with us to design and customize our design, to test it out and go back and forth. So we really like that. And then another issue is the ability to build these generators. It's
It's not always a quick process, and that can be a bottleneck when you have a goal of deploying 120. And so this company actually recently applied for a grant in the economic development office of the state, and so they won this industrial development grant, and they were able to make some new hires and build some manufacturing capacity so that they could crank out these generators that we designed a little faster. And then, of course, you have to consider contracting and purchasing. So I know from working with my colleagues like Kayla and others Andrew in Colorado, that they have all kinds of different rules for how you go about making a request for a proposal and awarding contracts, and all that procurement process can be different. For us, it's rather streamlined. We have special call-outs in the cloud seeding statute, which basically gives us leeway to contract at will for operations and research. When making a large investment in infrastructure, you also have this question of whether the equipment should be leased or purchased. And so you also have a range of options there. Sometimes the operator actually owns the equipment, and so they build those costs and expenses into the program that they bill us for. Other times, like Idaho Power, they can build their own equipment, they own their own equipment, they service their own equipment. And then in other cases, so for us, in the case of these remote generators, we're actually purchasing them so that the state owns them, but then we, because we don't have the capacity to store them or maintain them, we actually, the contractor does that for us. But that comes with, that can come with some additional costs as well. So those are just considerations that you have to make. And then setting up and taking down the equipment can, when you have a few generators that may not be much work over before and after the winter season, but once you start scaling up at the level that we're looking at, that becomes a considerable amount of time and effort, especially when we're looking across the entire state of Utah. So all of these kind of considerations, we have to figure out what to do. And then lastly, siting. And Rachel just mentioned the kind of one of the major lessons that Santa Ana learned was the amount of time that it can take to attain and negotiate site access. And so that's no trivial matter. So our approach has been in this priority to first find private lands where we can site the generators, then to identify state lands, and lastly federal lands. And there are some advantages and disadvantages to each. The reason we prioritize the private is because often there's no cost to site it there. We have a lot of willing landowners. We have a lot of large landowners in Utah, and so lots of times they're more than happy to put the equipment on there and work with the operator. And we also don't need any permitting, in order to do that. It's just based on permission. And but one difficult thing about that is it increases the logistics for us, because then you have to have contact number, name, coordinate, with the landowner, figure out where exactly to put it, and that list of contacts can get quite long. So for the state, that's our next best choice, because since we are in the Department of Natural Resources and the executive branch, we can work closely to streamline some permitting with other agencies. who own land. The Division of Water Resources doesn't, but the Division of Wildlife, Forest, Fire, and State Lands, and parks, they all own land that's sometimes in ideal locations for siting these generators, and we can work with them to get those permits. But it's limited in the amount of state land that also overlaps with these ideal siting locations. And then lastly, federal lands, which are most of the primary lands where we would want to site remote generators are on federal lands, but that can sometimes be burdensome to get permitting from them. Fortunately for us, we have a Forest Service liaison in the Department of Natural Resources he has an office in our building, and he's in there 2 days a week, so we can face-to-face with him, and he's helping us to do a single permit for the entire state, and that's valuable because it simplifies like the number of permits, but still each site on Forest Service land has to be identified and visited and detailed. So it still takes a lot of time, and we probably won't be able to make all the site visits or and get that permit until next spring. So I think that's all that I can put it out there. So a lot of considerations and questions to make. Questions to answer when thinking about investing in a program and how to make it as effective, efficient, and sustainable as possible. Thank you.
Okay. I'm going to be talking about something completely different than Jake was. I'm going to be talking about evaluating winter orographic cloud seeding programs. And this is going to be based on what we did for Wyoming. And the outline of my talk in my 15 slides will be the need for observations and high resolution models. So this is something that Sarah and I have been talking about a lot, and Derek and I have talked about this a lot. We need radiometers and gauges and radars to measure precipitation, and we need high resolution models, and I'll talk a little bit about that. And the second part of my talk was the need to use verified models to inform the evaluation. And verified models means verified compared to observations, and that's why we need the observations. And so a lot of what I'm going to say is written down in detail in a JAMC article in 2018. And something that Barry Lawrence taught us all is that evaluators should be independent of the operators. So with that in mind, I'm going to move on into the next slide. And do you see my next slide? Okay.
Yes.
Okay. Once you've seeded a cloud, you don't know what it would have done otherwise. So we can use randomized statistical trials like the pharmaceutical industry does, or we can do something else. What we're finding when we do that is that the signal from the cloud seeding is relatively small compared to the variability of natural weather. And so it becomes problematic to get enough cases to do this kind of an approach. In the Wyoming case, we estimated it would take about 1,000 independent cases, and we had about 118 or so. So it would have taken a lot more money and time to generate enough cases to be statistically significant. So what we did is we did a modeling approach instead, and I'll talk about that in a bit. Something that Sarah mentioned was the simple And Jeff French mentioned about additional precipitation, and Sarah showed this nice schematic diagram of a cloud on top of a orographic barrier. However, when we look in reality, if we look at the radar data, we can see that it's much more complicated than that simple. Sorry, not sure what's going on here. Than that simple diagram on the upper right. The clouds are much more complicated, and a lot of the complication is due to the fact that the mountain barrier is complex, and that creates updraft, downdraft patterns that are difficult to reproduce in the model, and or difficult to reproduce anywhere in any situation. And it's not the water cycle that we see depicted on the left. Yeah, it is much more complicated than what we see on the left. So this is one of the reasons why we started moving into the modeling world. And this diagram shows a little bit of our rationale. If you look at the global and regional models, they're typically around 50 to 30 kilometer resolution. And if you look at the type of microphysics involved and cumulus parameterization, because they're so coarse, they need a cumulus parameterization. You can see that you have simple microphysics and you need to have a cumulus parameterization. And PBL means planetary boundary layer parameterization. Sorry, Bruce, for the acronyms here. So what we've decided to do is go down to 2 to 4 kilometer resolution, which is the star here. And I want to thank Jeff French for bringing up the concept of mixed phase microphysics. What we're able to do is eliminate cumulus parameterization in simple microphysics, and now we're able to simulate mixed phase microphysics, which means we can do cloud, ice, and cloud droplets together. And this turns out to be a critical thing to do. The other thing that 4 kilometers or 2 kilometers allows us to do is to resolve the topographic forcing. And this is something that Sarah showed earlier. This is something we did many years ago. Now, 10 years ago, we ran a model at the WRF Weather Research and Forecast model at 36 kilometers and 2 kilometers over the Colorado headwaters. And what we found is that, as Sarah described nicely, when we run at 36 kilometers, we only get about 300 millimeters in this region, whereas at 2 kilometers, we get a 900 to 1,000. And that agrees well with the SNOTEL observations. Now, one thing that Sarah didn't show, and I will show, is the picture of the SNOTEL gauge. This is the gauge at Gliese in the southeast Wyoming, and you can see it's a very tall gauge, about 25 feet tall. And the reason it's so tall is because you generate a lot of snowpack in this region, and you can see an altar shield around it. So the SNOTEL data is wonderful. I didn't know it existed when I started this project, but I quickly found it, and I've been evaluating models using the SNOTEL data. The one drawback is that its resolution is not that great. It's 1 millimeter resolution, but if you do it over a season, it worked out really well. And I'll show you some results here in a second. So having observations is critical. A radiometer to measure the vertically integrated supercooled liquid water. One thing that I didn't hear this morning, and maybe I wasn't able to attend all the talks, was that supercooled liquid water is important, but I know that was something that was emphasized, but what's producing that is the vertical motion of the atmosphere, and that has to do with the air hitting the sides of the mountains, causing vertical motion. So having that information is really critical. snow gauges, and atmospheric sounding. These are all things we use in the Wyoming pilot project. And gap filling radars was something we dreamed of. Now I finally got one, and hopefully we can do that in Idaho and report back at the next meeting. So these are some of the instruments we had in Wyoming. We had radiometers at each of the ranges. We did a double crossover design where we did two ranges. One sort of we randomly seeded one and not the other, and the other one was used as a control. And we had snow gauges. And one of the things that I really insisted on was we have 3 snow gauges at each site. So this site I think is Gliese, and this is one of our target sites, and you can see three snow gauges. And when we did the evaluation, we compared all 3 together. If 2 are wrong, you don't know which one is wrong. But if you have 3, then you know which one is the right one, and hopefully, and which one is the wrong one. So we typically had 3. We had 3 at all of our sites. I mentioned to you earlier that I would talk to you about SNOTELs. SNOTELs tend to be all over the West, and they are a wonderful resource for evaluating models. And what we did is we looked at the seasonal snowfall and snowpack. Each of the SNOTEL sites has a snow gauge, which measures the precipitation, and a snow pillow, which measures the snowpack. And we looked at both. And we looked at all these ranges over the West. And you can see the comparison in the Pacific Northwest, Sierra Nevadas, Utah, which we just heard about, and Colorado, and all SNOTEL sites here in the lower plot are excellent in terms of precipitation. In terms of snowpack, we're a little bit underestimating the snowpack. So that's something we're working on right now, is to understand why we're underestimating the snowpack. So in the next few slides, I'm just going to briefly talk about the Wyoming WeatherMod pilot project approach that we used, and this is in the 2018 paper that I mentioned to you. And one of the things that we determined was that, as I mentioned to you, using the standard statistical methodology that we've heard about and know and love, that we've been advocated, that the statisticians have advocated that we use in WeatherMod, the signal is just too small. We just have too many cases to calculate, and we need to do something else. And so what I've advocated here, and Lulin Shui and Sarah have been involved with this, and Terry Deschler was critical as science advisor for the Wyoming project to do this, was to use an ensemble approach. Now, one of the things that the models allow us to do nowadays that we couldn't do 20, 30 years ago is an ensemble approach, because the computers are so much faster, the models are so much better. So one of the things that this has allowed us to do is actually use an ensemble approach. And an ensemble approach, which I'll define here in a second, means that we vary the large scale environment driving the model, the natural cloud evolution in the land surface physics, planetary boundary layer physics, and the cloud and precipitation microphysics, and even the seeding. We have changed the planetary boundary layer for silver iodide dispersion, land surface physics, and seeding microphysics. This relates to what Sarah called WRF WeatherMod, and we've also done it in WRF Hydro. So what we've determined, and what the scientific community has determined, is that we have initial condition uncertainty. We have uncertainty in the model physics itself, and this goes for both seeding and the seeding module and the natural cloud precipitation. And because of that, you know, small changes, we don't know where the actual curve is going to go. So we have this cloud that forms instead. And oops, sorry about that. And we applied this approach for both the natural precipitation and the seeded precipitation in the Wyoming project. And we came up, we ended up doing 10,000 simulations. I can tell you which ones we did for each, if you ask that question at the end. But what we're able to do is tell you, like that 5% is the mean, and the quartile range is 25 to 75% is 3 to 7%. So you have some idea of what the results are. I think my time is just about up, so I'll just say that computer modeling is really the future of, in my opinion, of cloud seeding evaluation. But we need observations to help verify the models and make sure that they're fucking reality. You know, I'm very excited about the Snowy project because it provided some critical observations to help us tie down some of the seeding parameterization information. And Barry mentioned, Barry's always talking about evaluation should be independently from operations. We have the seeders and the evaluators. So with that, I'll stop and take any questions if there's time.
All right, thanks everybody, and just to give a little bit of background, I've been in the weather world of operational weather for just about 40 years. The last 12 seasons I've been with Idaho Power as one of the meteorologists. Today I'm primarily talking about two methods of precipitation enhancement benefit estimation. So not all the way down to the water, but how much precipitation is produced. Going to look at two primary methodologies, target control analysis, and then something that you guys have heard of a couple of times today, the weather modification model from NCAR. So target control analysis, there's a whole bunch of stuff up here, but basically it's a methodology that's computing the relationship between a target area and a control area, meaning the cloud seeding area and an area that's not being cloud seeded. And it provides a historical relationship between those two. This has been documented by a number of people, but the primary people that, or the person that is referenced most often is Arnett Dennis in his 1980 books, Weather Modification by Cloud Seeding. There's been tons of others from the California programs that have published quite a bit. North American has published quite a bit. There's a lot of information out there if you want more information about it. But in general, it's a regression methodology. So when we look at it, we kind of start out with some a priori guidance so that we kind of establish the rules, you might say. And in general, what I talk about is that you must have data prior to cloud seeding that occurred. And I say that you have to have at least 10 years, but preferably you want somewhere in the area of 15 to 25 or 15, 30 years where no cloud seeding occurred to be able to develop a strong statistical relationship. Problem is most of the data that we utilize is SNOTEL data. And that means that it started around 1980, give or take a year or two, depending on which area you're in. So if you have a program that started in the 90s, you don't have that long record. Now, Roy would probably tell us the best way to do this is by models. And up until recently, you really didn't have the computational ability down at an operational level to do that. But some of the other things that you can use is National Weather Service data, co-op data, RAWS data, and then you kind of break it down into target and control data. The target information from these sites should be within the basin of interest. And then
The other area has to be outside of that basin, but it has to be away from areas that have been influenced by cloud seeding. And this is stuff all of you guys know, so I'm trying to do it quickly, not to put you to sleep. Control stations should be upwind, meaning that the flow of the weather is coming from that area to your area. And that can be general. For us, it depending on the location, it's from south up to north. Most of our target or control areas are in the southwest to northwest of our target area. Individual sites don't necessarily have to be one-on-one correlated to be used, but when they are combined into a pooled target or a pooled control site, they need to be strongly correlated to give you a relationship that you're comfortable with. Because you don't want so much uncertainty within that regression model that you're not comfortable seeing that it's representative of the area. And just general, looking at all the literature out there, what we've seen that is the average expected benefit for target control areas is from 0 up to about 25%. Some individual storms have been identified much more than that. Some occasionally report annual benefits above that. But in general, what we're looking at is 0 to 25% benefit for precipitation enhancement. Process as we do it, we go in and select our target sites. We use generally the 8-digit HUC, so that river basin that's kind of predetermined and identified by other folks such as the USDA within the NRCS or National Weather Service for the river forecast areas. And that 8-digit, it breaks it down into areas that we're interested in, say the Payette River Basin, the Boise River Basin, things like that. Control sites are based upon excluding target areas and the surrounding areas that have likely been cloud seeded in the future. And probably everybody here is well aware of the fact that that's getting harder and harder and harder to find because there's more programs and they're becoming more extensive. When we looked at cloud seeding, let's see if you guys can see this mouse. Hopefully the ones online can see this mouse. These are kind of the areas in the Payette River, or the Idaho area that we look at, the Payette, the Boise, the Wood, and then out east, we have the Upper Snake, Henry's Fork, and a couple. An example here is when this area in the Mud Lake area was initially developed for a target control analysis many years ago. There was not really a lot of cloud seeding around it. There was, there was some to the south of us. Utah had been cloud seeding down below Pocatello and across through here. We had been seeding up in the Payette River Basin here, and the DRI kind of down to the southwest had some areas that they've been cloud seeding. Now with the expansion of the DRI program across some of the areas to the south, pretty much all the areas south of the Snake River Basin are no longer usable for target control analysis as control units. And the fact that we have started seeding across most of the Central Mountains, most of the areas in here that previously were identified for Upper Snake analysis are no longer usable. So the only thing that we have left is kind of from the direct north down through the southwest. It's more west by southwest. So we're rapidly losing the ability to utilize control sites. If Oregon, which there's discussions, cloud seeds this year or next year, we'll no longer have control sites. So that puts us in kind of a predicament there. But once you're in an area that you can identify control sites and target sites, basically we go to the SNOSTEL site, website, we download the November 1st and April 1st precipitation amounts, and we calculate a cloud seeding precipitation, basically taking the April 1st precip and minusing the November 1st precip. Why do we use precip versus, say, SWE or snow depth? Well, we've found that in many of our areas, in the last 5 to 10 years, that April 1st period is no longer truly representative of the total amount, because we're starting to see areas that are starting to melt out before that April 1st period. So if you compare across that time frame for SWE or snow depth, you may not have an accurate representation of how much precipitation actually fell. So we've started using the liquid precipitation, which is a cumulative amount and doesn't evaporate or melt out. We combine those sets, identifying years to remove based upon when cloud seeding occurred in them. In a number of our areas, cloud seeding has occurred at different periods. So some of them were seeded in the 80s, some of them in the 90s, and these may be 1 or 2 years at a time where projects started, stopped, started, stopped. So you have to pull those years out and use the remaining years to develop your control relationship, and then use them to predict your operational stuff. Select the most representative target sites and control sites using a combined. We use a bootstrap regression approach based on the a priori guidance. And to give you an example of how this becomes painful, so in the early 2010s, we redid the pay base and target control. We have 5 possible snow-tail sites. There's, at that time, was 73 possible snow-tails that could be control sites. And you can see going through here that if you had 3 control sites and 3 target sites, the potential was like 60,000 potential combinations that you could do there. Looking at it, we got strong relations across many of them, to the point that we had over 13,000 that produced an R-squared of 94 or 0.94 or 94%. But many of those would show a estimate from -10 to plus 120, which do not meet your A priority requirements. We kept working our way down. We had 2 that were between 0 and 32%. And eventually I came around and said, well, 3x3 is not going to work. I used 3 target sites, 4 control sites, and we wound up, out of the million-something possible potentials, of 1 that met those requirements. So, a little painful. So, develop your final regression based upon a full data set. So you've identified the ones that you want, develop your regression set, and then your regression equation is used to develop the analysis. From that, I put together a table and a figure of how it comes together. And this is an example of what that looks like in Excel. Across the bottom is the pooled control site information. So of that example for the Payette River Basin, I had 4 snow-tail sites that were control sites. I pulled those together, basically got an annual average of those. Same thing on the vertical there, that was the pooled target sites, those 3 sites. I developed a regression for this, plotted them here, and so just generally looking, you can tell there's a fairly strong relation there, or a linear relation. Plot the equation. This one came up to about 0.964, which is, for a natural system, is fairly strong. So the way this would be utilized is anything that is kind of to below that line to the southeast down here would indicate a negative enhancement or benefit. Anything above that would be considered a positive within the capabilities of the regression. Once we plot the years that we actually did cloud seeding, fortunately, every one of those years shows up above that regression line, and some of them are very close to the 1-2%. Some of them are up to the 15 to 20%. And we do this for each of our sites. So, some concerns, is that target control is a linear regression based on historical analysis. That is dependent upon near stationarity of your climate. And generally, everybody knows that climate is not stationary. But you're making that assumption through time that what you've developed based on data back here is going to carry through forward. So that's a big one. Upwind seeding, as I talked about, is getting more and more, and we're losing the capability to have control sets. And one of the things that we always talk about is that we don't put a lot of effort or strength behind any one individual year, because we know from the regression there's a little bit of slack in there. The uncertainty associated with 0.96 shows that there's a little room in there. But when used as an annual average across time, it gives you a solid idea of what the enhancement across that period is most likely to have occurred. So the thing that you guys knew a lot about, we've discussed. Now we'll go to the things that I know less about. So the NCAR weather mod, WRF weather mod, the benefit to it is it provides a physically based approach to estimating, and that means that we're not in the statistical world, we're not depending on the stationarity of the data. So that's a really strong forward movement. Uses the high resolution WRF data that we produce at 1.8 kilometer, and it identifies all the conditions of when the clouds are suitable for seeding, either by aircraft or the ground. And then it can be used in two different modes. One is the case calling to support operations, and that case calling has been improving through time, and we've seen that with the research in SNOWI. We were able to take those cases as called and compare them to physically measured data or information, and it did very well. So really quite happy with that. And this is an example of this. Is the thing on the left is a text that the model puts out, shows that no cloud seeding for ground was available. There's one available for aircraft, and in that time frame, there's a period that's beneficial between 1300 and 2130 during the day. That's identified over here in these light gray bar. And then the best case in that time frame where everything really comes together well is the dark gray picture on, or line here. What this represents is it gives a physical appearance of the member functions that we're looking at. So across the bottom in this example is average precipitation rate. How strong is it precipitated? We have everything from relative humidity with respect to ice, relative humidity with respect to water, temperatures, and then a combined seeding index on the top. And as we see across this top one, the solid line is what we're looking for that index to get above. Once that gets above that, that indicates that we've kind of met enough of the criteria for an effective seeding process. Now, if you really want to know how this works, you would talk to Lou Lin and the NCAR folks, because they can provide you much more detail. This is just a simple example of how this works. And then the next part of it is the benefit estimates, which ties back to the target control. It allows you to run your WRF data to establish the case calling mechanism that calls when you should seed, and then that is rerouted from that when it's identified back into the module. And I have a diagram so you don't have to try to follow my wandering around. And then it simulates what would happen if you seeded at that time. So you, for an annual analysis or benefit analysis, you would take your best data set, such as a reanalysis of data, run it through there, identify the times that cloud seeding actually occurred, have the module identify those, produce the simulated precipitation, and then you could compare the control runs versus the simulated precipitation from cloud seeding. So this is a better example of that. You run the WRF, control forecast, no seeding in it. It identifies over here when the best conditions are. You run it back through here. WRF weather mod then predicts the precipitation that would have occurred if you seeded at that time, and you can compare the two, control versus seeded. And then you do a delta. And that way you have a physically based estimate of how much precipitation difference occurred. And that is it.
All right, thank you. Maybe just a couple caveats to start off my presentation. The first is that I'm not a atmospheric scientist. I'm just a civil engineer, so please don't hold that against me, I hope. So the other caveat to that is if you ask questions, keep them pretty simple. That's always appreciated because I don't have all that atmospheric know-how like a lot of the folks in the room. But so I'm part of the operations hydrology group at Idaho Power. We work closely with Mel and Derek and Sean and the folks that you guys might be a little more familiar with, really to take what happens on the wintertime precipitation piece and then turn that into a stream flow at the bottom end of the basin. We operationally forecast for our fuel supply for our hydroelectric fleet day to day and support our hydro operations. But we also then help analyze the cloud seeding program from a planning perspective. So we use different suites of models to do both of those things. And we're always getting the question, you know, how much benefit, what's the impact of the cloud seeding program? And so there's the piece on what actually falls out of the sky, and then there's the piece of what ends up in the river. So I'm going to kind of cover that once it falls out of the sky and goes to the river. So ideally, once we had snow on the ground, and Roy touched on this a little bit, once we cloud seed, we don't know what would have happened otherwise. But it'd be a whole lot simpler if somehow we could go out there, dig a snow pit, and see something different that we could attribute and say, oh, that's cloud seeding snow and that's the natural snow. I think we all wish it was as simple as that, and then things would get a lot easier. Because then we could take our favorite hydrologic model, and we could say, what does my hydrologic model predict for snowpack, however it's handling that. And then if I run it again with or without cloud seeding, what's the snowpack under that scenario, and compare it to something we can observe. But because we can't observe it, we have to figure out how we're going to go about that analysis. And ultimately, again, for us, the snowpack is kind of the start of the hydrologic modeling world typically. And then ultimately, we're getting down to where we want this kind of answer. And it sure would be nice if we had the same kind of thing, where if we could observe the cloud seeding benefit discretely in the snowpack, sure would be nice if we could see a different color to that water or something like that. But again, we're not afforded that luxury. So really what I want to talk about is not the details of how Idaho Power does it. I really want to talk about kind of what options exist for how to go through this process of snowpack on the ground or precipitation benefit or impact to a water supply benefit. And really, whether you already have a methodology or not, if you're looking to develop a methodology, I think it's always good to kind of take a step back and say, well, what do I really want out of this part, this piece of the modeling chain or the analysis chain? What am I really after? And knowing what you're after will really help guide what kind of tool you develop to answer that question. So I put up some that come up for us, and this is by no means comprehensive, but I'll just start kind of at noon and just kind of go around real briefly. But
the first thing a lot of people want to know is, well, how much water? So how much additional precipitation? Snowpack is one thing, but a lot of stakeholders really want to know, well, how does that actually yield a water volume somewhere where I can pick it up, right, where I can use it. So usually the volume of water is kind of the first, most basic question we're asking of these models. But then there's a lot of other things beyond that. So just kind of going clockwise, you know, what's the timing? Because the timing of when you get that water can be really important to different stakeholders and different users. What spatial scale am I looking at? Am I looking at relatively small catchment? Am I looking at something like the entire Snake River Basin in southern Idaho? Am I looking even larger than that? That will guide maybe the right type of model that you use to answer that question. Because there will be trade-offs associated with different choices. What physical processes am I curious about? Talked a lot about once that snow is on the ground, it can run off, it can infiltrate. A lot of the infiltrates might have a benefit, say, to an aquifer. Do I want my hydrologic model to capture that or not? Is that of concern to me? The more things we want to capture as far as physical processes throughout the system, the more complex the model will likely need to be. What futures? Obviously, the big one here is probably climate change. You know, if I have a program now and I'm analyzing it with historical information now, how might my program be impacted into the future? That's a question that could very well be asked of a hydrologic model. Am I looking at that long term? Like Mel mentioned, we view our program, or the collaborative program that we're involved with, on kind of a long-term average basis. What does it produce over the long term? But some folks might be interested in what did it produce this year? And that might drive some of your decisions on modeling selection as well. Talked a little bit about surface water, groundwater. You know, are we interested in more than just the surface water hydrology here? We're going to the subsurface. How many water users do we have? Sometimes in a hydrologic model, let's say the basin is cloud seeded, and initially in that basin, before you even get to the measurement point of a downstream gauge, there's agricultural diversions in between. Well, the hydrologic model can handle, some of them can handle agricultural demand, and you might want to anticipate how much more of that water is available for use even before it hits a downstream measuring point. So that might be something to consider. How many scenarios, you know, how many different questions or what ifs might you want to throw at the model? What audience, if you're going to go and shop a hydrologic impacts assessment or model around, who are you showing that to? What's kind of the breadth and background of the audience, and how are you going to communicate and educate on what you're doing? Regulatory and legal requirements, you know, if there's any framework there that you can be aware of. And again, the list goes on. This was just a 5-minute brain dump of some of the things that have come up on the Idaho Power side, at least, and with conversations with the state. So broadly, I would say the way I view it is kind of we're on this kind of standard 2-axis decision space of how complex of a model do I think I need, which generally will probably correlate to some kind of cost to develop and maintain that model, whether it's the cost to actually create it or the cost to maintain it. Some of these models, if they're pretty complex, obviously that might take just much staff time to maintain them. And then on the y-axis would be what's, you know, the information that I'm after, what kind of detail am I really going to be looking for on the hydrologic impact side, and kind of just have a progression of just a few really basic things, but some of your most simple and quick to set up models would be just a water supply regression model. So when I have the amount of precipitation or observed snow water equivalent, what is my periodic volume supply, my water supply? In the West, you know, April through July, April through September, looking at that runoff period. But as we go in more detail and get more complex, you can get conceptual models, semi-distributed, lumps-type parameter models, all the way up to fully distributed, fully physically based models, which are going to take quite a bit of computing power, but also output quite a bit of information as well. So I'll just go through these really briefly. I just wanted to note, kind of from our standpoint, where some of the examples of these models would be for kind of pros and cons and the input requirements. But regression, again, pretty simple. Positives are that it's, because it's simple, it's pretty easy to explain. You probably have to explain, you shouldn't take it too far, more than you have to explain what it is. People are pretty familiar with it, but where you should stop with some of your analyses, also things like that. But it's not going to give you a whole lot of spatial information or a whole lot of temporal information, obviously. The one that we're familiar with at Idaho Power, so we actually run the Northwest model similar to like the Northwestern Forecast Center or the National Register of Forecast System suite of models. And they're basically a semi-distributed lumped parameter model that, as their forcings, it's base and average or mean aerial temperature and precipitation. So that's pretty simple for inputs as well, and then they run off of area averaged parameterization and a lot of temperature index method, personnel accumulation, and things like that. They're still pretty quick and easy models to run. They're a little more time for those physical processes. Cons are that with some of those knobs, you can tend to kind of over-tune some of these, and it might be difficult to ask more sophisticated what-if questions or look at other scenarios. And then kind of at the most sophisticated level, we have models such as WRF Hydro, which are very spatially and temporally granular. Obviously, we've heard a little bit about how they can compare with other WRF products as well. And so there's some positives to that. It's highly granular, space and time. You get a lot of information out of those models because a lot of information comes out. Ideally, you have a lot of information to be able to go into that as well, and that can sometimes be hard to find in certain bases. And then, as I mentioned, these models do take quite a bit to maintain, keep going year after year as well, so that's a consideration depending on your staffing, your resource availability to do that. And then just to wrap it up, just some final thoughts that we talk about a lot, really knowing the needs and the questions, which is not trivial sometimes, and how many stakeholders there are, but really trying to remember what you're after will really help determine what kind of tool set you need and what you go with. We have a saying in our group is, don't build a Ferrari if Camry will do the job. Don't go and kind of get starry-eyed and go for the biggest and best thing if you don't need it, because it's going to be more expensive and cost more to maintain. Really think about what you need and start there. You can always trade in and go up down the road maybe, but really think about what you need right now, what you can perform and produce right now. And then there's just a lot of other uncertainties. So I talked about the atmospheric piece. There's a lot of uncertainties and variability in the hydrologic models themselves. So just keep that in mind as you go through. This is where kind of communication with the different subject matter experts is really valuable. That's all I had.
So the big question is, a lot of times, is where does the water go after it falls down and accumulates? For some people, all they care is to add water to the system, which makes sense. Usually more water is better, especially when you're in an arid environment, semi-arid environment. But also at times people want to know who's benefiting. And so that's really what we're looking at. We're in the middle of a process of modeling to see where the water goes in the system.
I'm not presenting that information because it's not complete yet. But if you just want to increase the water supply generally, there's not much need for further modeling other than target control analysis or trying to determine what that value is. But you may be trying to target cloud seeding for irrigation, and you want to know how often do irrigators benefit. You might be targeting hydropower generation. You might have multiple things you're targeting. One thing that probably benefits from cloud seeding in Idaho is aquifer recharge. And then there's other things, perhaps like increasing base flows for habitat purposes. It took off here. Sensitive mouse. I'm not going to talk about habitat, but that's one possible use. So where does the water go? First thing is uncertainty, understanding your system. So one thing we did is we don't know how much benefit we're getting. We have kind of a range of ideas, so we just started at 2%. We ran a reservoir operations model up to 22%. We're looking for non-linearities in that system. We're also looking at the reservoir system model to see how well it actually represents the system. But as you go through that range, how much does it change? Is there a threshold where all of a sudden you're getting less benefit? It's a kind of interesting way to look at it. You can also take a more simple approach and just look at a hydrograph. And I'll show a couple hydrographs where when you look at it, you can see, oh, here's when the benefit would occur. That's usually easier to do if you have a simple system. If you got a system like the Snake, looking at a hydrograph isn't going to do you a lot of good because there's so many different things going on. I'll talk a little bit about diversions and how we look at them in Idaho, but this is totally Idaho-centric with this diversion method. And you have to look at kind of how your system operates. Hydropower, I'll probably talk a little bit about that recharge. Changing, accounting for the uncertainty, I talked about that. We kind of we have a riverware model, and what we did is we just changed the inputs into the model for a range of different increases in stream flow. We're also running a hydrologic model with different levels of precipitation increase, which we're now going to run through the model. But there's different things you can do to just look at the variability of the system. And Mel covered a lot of that. So if we look at a couple hydrographs, the one on the left is the Salmon River Canal Company's reservoir south of Twin Falls. This is not an area that's currently being seeded, but if somebody wanted to seed it, when would it benefit? So this is the reservoir, and the interesting part is the reservoir can contain about 180,000 acre feet. So the reservoir almost never fills. It was built in 1910. It didn't fill until 1984. So, but when would the benefit occur? It's a multi-year reservoir. If you seeded, let's say in 2006, the reservoir would peak out here. You probably get a little bit more into that reservoir, but you're not going to get any additional diversion. What you're benefiting is you're putting more storage into the system. You're building up an insurance policy the next time you go into drought. So when you hit these years where the reservoir is bottoming out, after a couple of years of seeding during conditions where you didn't need it, you've now put extra storage into that reservoir, and you're going to have more water at least for 1 or 2 years in here. And that's kind of, you can begin to start quantifying that if you know how much additional seeding you're putting into the system. If you go over here, here's another flashy system. This is one we actually seed. And you can see here the reservoir peaks out at about 180 here too. And there's a lot of times that reservoir is peaked out. So anytime that reservoir peaks out, it's gonna, any seeding that's accumulated in the reservoir up to that point is gonna spill over. And in this system, it goes down across the Snake River Plain. A lot of water is lost into the aquifer, which of course is a benefit in Idaho. And then it goes down and it's usable as hydropower and other purposes downstream. But it's in these lower years, that you'd be gaining more of the benefit in these drought years. So kind of understanding how your system works is important if you care where that water ends up going to. If you look at diversions, in Idaho, we cut priorities strictly according to priority. Not every western state does that, but most do. And what we find is if we plot the July through September diversion against the water supply, and it's labeled on the bottom the July Swazi for the Snake River, that's as a volume. So it would be the June 30th storage plus the July through September runoff. And if we plot that, we can see that from American Falls to Milner Dam, there's a certain point at which all of a sudden the irrigators benefit. Of course, they're building up storage in the reservoir system, which in these other years, so that's an insurance policy, but when would they actually divert that water? It would probably be during this period where they're limited by water supply. If you look at the Henry's Fork on the Snake, and the Henry's Fork Swazi, whenever that water supply in July is less than 800,000, then they're going to divert more water out of the system. And so however much you increase that water supply would be how much more they would divert. So that's some ways to quantify benefits. Hydropower, run-of-the-river versus storage. In the run-of-the-river system, you're mainly looking at how many extra CFS, which translates into how many megawatt hours of electricity you can produce. With storage systems, you get additional head, and that increases the amount. So it's not just the CFS, it's also the increase in head. And then there are some systems in Idaho or Utah where the hydropower is supplemental. As the water's passed through for irrigation, it's kind of a supplemental supply. And so if you're diverting more, then you're going to produce more hydro. And so to understand kind of how that works is important. If you're trying to identify a specific benefit. Groundwater responses, and this is one thing that's big in Idaho with the Snake River aquifer, is as we divert more water out over the aquifer, or we're able to divert more in the winter to recharge the aquifer, that then has an impact that brings more water back into the river. So in a sense, when we cloud seed up above, and then we're able to divert that as recharge, we're going to get that water not only diverted as recharge, we're going to get it coming back into the river system where it can be re-diverted again later. So the benefits, cloud seed, as it passes through the system multiple times, you get multiple benefits out of that water. And in the East Snake Plain aquifer, we're able to just put response functions into a model because it's a single layer, unconfined aquifer is the way it's been modeled. And so there's a pretty simple way to put that into a reservoir operations model. I've done it in PowerSim, and then also Riverware. And there's an article from way back in 1999 where Gary Johnson did that with the Bureau's Monson model. So that's a pretty common thing if you have that single layer. If you don't, then it's a much more complicated analysis of running it through the and so how do you add water into the model? I'm not sure what the audience's experience with this is, but you need to add it by reach, and you can either do it as percent of precipitation if you don't have a hydrologic model. It may not be one-to-one, so you may want to do a variety of different options as how much of that increased precip is going to end up in the river, or you can run a hydrology model and then look at that increase from the hydrologic model. And so the concept is by reach gain. So let's say just as an initial step, you're going to increase your stream flow by 2%, and then shift it around in your hydrograph. But to get to those numbers, It depends on, you know, if you're seeding and then this reach above the reservoir and below the reservoir, you want to distribute where that water enters. And so we look at the reach gain. And in this case, you've got a reservoir, it's releasing 500 CFS, 60 is being diverted out of it, it's declining by 150. You can do the math to figure out that there's 410 of natural flow entering into that reservoir. So any additional water would be on top of that 410 from a modeling perspective. And then in the reach below, you're increasing the actual inflow into that reach is 150 CFS. So if you're doing it by percent, you've been increasing that 150%. You won't want to just increase flow at the 400 CFS down at the bottom because that's a regulated number, and it doesn't account for the fact that that flows entering across multiple reaches. So that's what we do in our reservoir operation model. And so kind of a little bit of the system we're using here in Idaho is we have a hydrologic model that we're adding precipitation to. That then goes into a reservoir operations model, which has response functions built into it so that as we change in reservoir operations, that impacts the aquifer, and then the aquifer response goes back to the river. And you can look at responses, and then at the tail end of the system, you can look at how much additional water leaves the basin. So from a hydrologic perspective, we have our hydrologic model adding stream flow above the reservoir system where we're seeding up the mountains, and then goes into our reservoir operations model, which where it interacts back and forth with the groundwater model, which represents the aquifer. And so as we're proceeding in that, you know, we're trying to figure out, you know, where the water goes so that we can talk to users and they can understand to a certain extent how much benefit and when and how that affects their system. And with that, questions?
Thank you, Sean. I've got a plane to catch, so I'm going to make this quick. So seeding in North Dakota has been going on since the 1950s, primarily. Started with some ground-based seeding attempts as early as 1951. But once we got to the 1960, airplanes became the method. And then a few years later, the North Dakota State Legislature established North Dakota Weather Modification Board, which was later renamed the Atmospheric Resource Board, which I serve as the director of now. And we have all the regulatory operations support functions. We conduct research and evaluation and also cost share with the counties that are in the program. So one of the first things, as far as the scientific foundation program, is called the North Dakota Pilot Project. This is a randomized program for 4 seasons in 1969 to 72, 3-to-1 randomization, looking at rainfall augmentation and also looking at hail suppression. And during that period of time, for the precipitation side of the equation, findings were statistically significant increases in the number of rain events on seeded days versus non-seeded days, higher average rainfall per event, and higher total rainfall in the target area by about 10% on seeded versus non-seeded days. These findings were published in the AMS Journal of Applied Meteorology. Also hail, there was indications of changes in hail energy being the rainfall, the ratio to hail energy was greater on seeded days versus non-seeded days, which correlated to what we would hope to find, but a smaller sample size didn't get statistically significant results there. So the program set up in North Dakota is governed through Chapter 6104.1 of the Century Code. This is a grassroots program, so counties choose whether they want to participate or not. So it's a ground-up program, not a top-down program in North Dakota. It's a public process that creates an authority in a county, so either a vote or a petition or something of that nature. The county commission can also consider a resolution and establish a temporary authority for up to 4 years to just experience the program. And then after that 4-year time period expires, then the county would need to create or establish a program through a permanent method. Once an authority is created, it has to be reauthorized by the county commission every 5 years. So then once that program is set up, the county commissioners appoint a weather model authority, a board of 5 individuals that oversees the project. This is the group that our board interacts with. We have agreements with them to conduct seeding operations every summer. And then we contract with vendors that provide the aircraft and technical services. And this is a cost sharing program, so the state does cost share 34% of the operational cost, the local share is 66%. Permits are required for the program in North Dakota. This is an annual requirement, so each year prior to the program being started, notice of intent has to be advertised in all the areas where the program is going to be occurring in all adjacent counties. There's a 20-day comment period, and then we go through those comments and the recommendations are made to the board for approval of those permits. And there's also a licensing requirement for all of the contractors that are doing this kind of work have to be licensed in the state of North Dakota. So the program, North Dakota Cloud Modification Project, we have 2 goals: hail suppression and rainfall enhancement. The program was established to assist with agricultural production, and that's still the reason that it's ongoing today. Operations are usually during the peak of the growing season, June 1st through August 31st, typically every year. Occasionally, we do extend the program into September if conditions allow, and in this last summer, we did extend to September 8th in one of our project areas because harvest was ongoing. It was a little bit late. And we're seeding convective clouds with aircraft at base and top using glaciogenic materials. Here's our operations map for 2023. So 2 seeded areas, one in the northwest, one in the southwest. We have radars in Stanley and Bowman that we operate to support the operations, and 5 aircraft this summer were deployed for the program, 3 in the Northern District, 2 in the southern one. The one in Watford City is a King Air C-90. The others are Piper Seneca 2s, which are just strictly used for base seeding. About 4.1 million acres or 6,400 square miles covered in western North Dakota. One of the unique things about our program in North Dakota too is our internship programs. We've been training intern pilots through an agreement with the University of North Dakota's aviation program since 1975. Since that time, we've placed over 400 intern pilots as co-pilots on our program in North Dakota. Many of them, after they have that experience, get some more flight time, come back as PICs working for WMI, or are working on other projects in the U.S. and around the world. So it's been a very successful program. Following on that, we started a meteorology internship program in 1996, and since that time, we've trained 73 students through that mechanism. We have a substantial training that we do. We have a 3-day ground school every year before the project starts in Bismarck for all our project staff. Here's our project radar locations. The aircraft that we're using are Piper Seneca 2s for cloud-based seeding, as I said, a non-pressurized twin aircraft, and a King Air C-90 for top seeding. Seeding equipment at cloud base, the far left and far right images are the base seeding methods, the Wingtip generators and the burn-in-place flares. The 2 photos in the middle are the ejectable flare racks, 3 on the King Air, a total of 306 flares on each flight, and then our dry ice hopper that holds 200 pounds of pelletized dry ice is dispensed through the belly of the aircraft. Independent evaluations. We also say we're not evaluating our own programs. We're involved in the cost sharing and also in the operations. So all of our evaluations of the program over the years have been independently conducted. There have been several. Just to summarize, as far as rainfall goes, most of the studies have come back with in that 5 to 10% areal increase in precipitation and target control analyses. There have been studies that have looked at hail, crop hail insurance data, and those have found lower crop hail damages in the seeded areas versus upwind control. That upwind control had a 50-year period of history before any seeding that was done that established the target control procedure like was explained earlier. Looking at yields, there's been studies that have looked at wheat yields, found that wheat yield production is higher in the seeded counties versus adjacent unseeded counties. And we've also looked at downwind effects of the seeding and found that the downwind effects of seeding North Dakota show a slight increase in precipitation downwind, not a decrease downwind, which is one of our studies was included in the Dave Felice et al. Paper in 2014 that looked at that topic around the clouds in the world. We've done studies looking at the economic impacts. If you're increasing rain and decreasing hail loss, what effect is that having on crops? North Dakota State University's agribusiness and applied economics school has been doing evaluations for us on about every 10-year basis, and the most recent one was done in 2019 and showed about a 31 to 53 to 1 benefit cost ratio, depending on if we're looking at 5% increase in rainfall or 10% increase in rainfall, and that it also includes the hail mitigation parameters in that as well. So a pretty large benefit cost ratio for the money that's being spent on the program. And a couple other studies, one recent that was published came out of Michigan State University, completely independent. We just provided some data at their request, and they came to us about this. They looked at wheat and barley yields. They found a statistically significant increase in wheat yields by about almost 4 bushels per acre. In seeded versus adjacent unseeded counties, they found crop loss insurance ratios were lower in seeded areas, and benefit cost in this case 36 to 1 as well. That was a very quick overview of the program. Thanks for having me.
So, Dave Pianzer, I'm actually with the Colorado River Districts. We're, I'll get into it, but we're a subdivision of the state of Colorado. So today I'm not speaking on behalf of Colorado, because Andrew had to go leave and catch a plane, unfortunately. But I'm very familiar with what's going on in Colorado, and I'll talk about Colorado's programs, and then I'll jump into what we're doing at the Colorado River District, which is a special district or subdivision of the state of Colorado. So Colorado has 8 permanent programs across the state. 7 of those are ground-based programs, and 1 is an aerial program. So the map is not quite complete here, not showing it all graphically, but essentially we have really good coverage across the Continental Divide on the west side, which is really key to the Colorado River Basin, which I thought we might have an overview of, but I'll cover some of that too in my talk. Because the Colorado River Basin, much different than what we've been talking about here in Idaho, got some unique characteristics and some great cooperation through 7 basin states. And again, I don't know, Sean, are you going to be talking about it
next?
Okay, so kind of jumping in and out, so you'll hear some of this maybe more than once. It's good to reinforce those topics, I think, anyway. But so the map, again, spatially, this is just sort of the spine of the Rockies, and to the west. The state of Colorado is the permitting agency for all these programs, and so they issue permits for these regions, whether, again, they're ground-based or aerial. Overall, there's about 27 remote generators in the program and 72 manuals across the state. So pretty significant, maybe just a little bit smaller than Utah's that you heard about earlier. The funding is sort of a portfolio approach where we get monies from the lower basin states that you'll hear about through a cooperative agreement. And then the state of Colorado has their own funding, and then local districts like my own and some of these folks in these shaded polygons here are self-funding as well. So you'll hear about this programmatic agreement with the lower basin. It's been going on since 2018, a very successful program. And so as we move through these slides, you know, some of these things will not be a surprise after a full day of looking at these, so I won't belabor it, except that, you know, the state is a regulatory agency. They are not operating the programs. The local districts are primarily doing these works. They are supporting through financial contractual arrangements and basically supporting operations, upgrades, studies, modeling, and evaluation. Again, you've heard a lot of these things, and it's in place, making a difference across the state of Colorado. Here's what the funding looks like. You can see it's significant, but not the most significant investment. Again, as you're seeing a lot of interest in cloud seeding grow, same thing in Colorado. And again, giving a hint here to the distribution of funding coming from the 3 agencies in the lower basin, Nevada, Arizona, California, and a small amount from New Mexico. So it's a significant program. It's complex in its reach and its funding. And, you know, it's been growing, as I said. This plot shows sort of a time series by program, the number of hours, seating hours per program per year. And you'll see kind of an ebb and flow. The orange bars represents the Central Colorado Mountain River Basin program. I'll talk about that more in a minute, but that's the program that I personally manage. And again, we set records last year. No surprise, it was a great year for seeding based on conditions. And you'll see a few interesting things here where Vail, Beaver Creek in the blue, used to be a leader in the program. And in fact, the history there is really interesting, going back to the early 70s. One of the first ones to seed in Colorado. After the pandemic, we sort of lost support for that program, but they're sort of emblematic of our efforts that, again, ebb and flow with ski areas and other cooperators to try to get interest in the program and investments. You'll also see a new one, the St. Vrain, for the first time on the eastern side of the Rockies, trying to seed and take advantage of some of those extra area effects, and also directly targeting some east slopes of the Rockies. So, like all states, you've heard about suspension criteria. Won't have to belabor this, except the same issues are there that limit our abilities to seed at all times. There's some really interesting tools that NRCS has developed in conjunction with other agencies, state and federal, as well as the Colorado Avalanche Information Center, which really helps us look at avalanche hazards, and obviously we curtail when those agencies are exceeding the criteria that are published under the permits. Make sure I got everything that Andrew had on his notes. You know, the seeding has started this year already. We had a quick start. We typically go from November to April, thereabouts. We've had 2 seedable storms across the northern portion of the area, so that's good news. So always likes to show this remote. This was built by Desert Research Institute. We're getting several more of these. These are remotely controlled units on wheels that can be moved around, and this was named for Joe Busto. So some of you knew about Joe. Unfortunately, he passed, but this is sort of a testament to his imprint on and influence on Colorado cloud seeding. So that leads me to myself and my talk, as I just rushed through Andrew's notes. Hopefully I did him proud. It says state of Colorado, but really we are a subdivision state at the Colorado River districts. And so I'm going to zero in on this green polygon that you saw earlier and tell you a little bit more specifics about our CCMRB, Central Colorado Mountain River Basin Program. Encompasses 4 counties, On the ground, we've got 20 to 25 generators. Each year it changes depending on funding, also depending on prevailing conditions. But we have a program and a footprint that's responds to and is flexible to those conditions as they change. In addition, we've got 4 remotely operated ground-based generators. We're really trying to expand the remote operations or generators, as you can guess, moving away from the manuals. We've got a budget of about $330,000 of combined funds, and again, that's state and local. So again, I'm going to jump in and give a little bit of overview about the Colorado River Basin and why, how we fit in at the Colorado River District and why we find cloud seeding to be so significantly important. You can kind of see where we sit in the entire Colorado River Basin and the 7 states therein. What you'll also see is these dark areas that depend upon exports from the Colorado River Basin. It's, as some people like to say, or I like to say, it's sort of the James Brown of rivers. It's one of the hardest working rivers out there, and it really does services 40 million people, 7 states, 2 countries, and right in the middle there, Lee Ferry is our sort of compliance point. There are measurements there that dictate who gets what. It's the foundation of what we call the law of the river. And again, so we are under stress in the basin, as you can guess, and as you'll see through the following slides. But the Colorado River District, here shown in sort of psychedelic colors. This is 15 counties. There, here you can kind of see where we fit within Colorado itself. Only about a third of the state, but it's mostly high elevation. It's extremely productive when it comes to snow. One of my favorite top stats, fun facts, 60 to 70% of the natural flow of Colorado River at that magic compliance point, Lee Ferry, arises in our little slice of heaven here in my backyard. Again, our program, you can kind of see the mouse, is here, but we do have other programs that extend in the Gunnison Basin and point south. We do not manage or I should say we're a policy and planning agency only, non-regulatory, but we exclude the San Juan Basin, sub-basin of Colorado River. So again, the other interesting thing here, you'll see of that significant yield of the Colorado River, most of it comes from about 8,500 feet. That's what this map is showing by elevation. So it's super important to optimize the resources in those high elevation areas. Really the sweet spot between 8,500 and about 10,000, 11,000 feet. The bulk of the snowfall arises and is retained there, which is only about 15% of the upper Colorado River Basin. So really important to kind of understand and to optimize and leverage that geography with cloud seeding. So, again, policy and planning is what we do. Protection, conservation, use, and development, focused on the Colorado River and those threats that would sort of dewater those areas. And some of that is here again, if you're not familiar with Colorado and the dynamics, the 80% of the water on the west side and 85% of the people or more living in the greater Front Range area. And you can kind of see the river basins. And so it's dramatic, sort of what I call a tug of war. You'll see that, the way that we meet the demands, and I say we, the state of Colorado, exporting water from the Colorado River through trans-basin diversions, almost 500,000 acre feet leaves the natural basin, never to return, through about 25 ditches and tunnels. The list is shown here. So a significant impact. And again, a lot of pressure within our area here. The other thing to point out in the overview of the basin about 90% of the water above Leaf Area, about 90% of the people below Leaf Area. So it's really, to me, fascinating and makes life interesting, shall we say. May we all live in interesting times. And so we have friends and colleagues across the basin, but obviously makes for interesting conversations. So that's us in our little district, stretched thin, competition for limited resources, and so we need to meet the needs within Colorado while still meeting the obligations under the law of the Colorado River, the Colorado River Compact, and the whole compendium of agreements. So that's, you know, graphically showing how we feel every day. And this is, again, what we're faced with. And I'm sure everybody here that's a water resource manager deals with these things. But what we're trying to do is make the rope stronger through augmentation, right? So pretty obvious things here. But the pressures not only are from exports and from use, it's from warming. And again, this graphic, I think, is extremely powerful when you look at how the bullseyes of climate change are being observed. Our district there outlined, you can see in the observed record since the late 1800s, you know, 4 to almost, well, over 4 degrees of Fahrenheit rise in temperatures since that time. This is not modeled, these are observed data, and of course that's a pretty strong drying pressure on our resource. So it's kind of a triple whammy when you think about it. Probably don't need to say this, but I will anyway. You know, we have allocated water based on a stable supply. We really don't have a stable supply. We have a decreasing trend. Cloud seeding is sort of our hedge against that. And again, that's why my board of directors and the state of Colorado are in the game, so to speak, on weather modification and cloud seeding in particular. So I've raced through that stuff. There's a lot more information. We've got social media channels. This is how you find us. And I'm really pleased to be here. I should have said at the beginning, thank you for inviting us to represent. So thanks. We'll look forward to talking to you.
And actually, in the spirit of cooperation, DK helped me a lot with some, because I can skip over some of the slides that I had, and more just talk about the agreement and the cooperation that we do have going on. So as DK touched on, there's a map of the Colorado River Basin, and this water drop graphic on the side shows under normal conditions how much water everyone gets. That adds up to about 16 million acre feet. But realistically, the flows of the river lately are, I think, closer to 13 or 14. So it obviously creates an issue of the supply balance and the inflows coming in. Let's see here. So inflows, this is a similar statistic. I don't know if DK, your slides just talked about Colorado with the land mass and contributions, but so here's a picture of the basin that it's a very similar number, where the inflow, 92% of the inflow contributions come from the upper Colorado River Basin, and you get only about 8% coming from the lower. But the important thing, and that this map illustrates, is that 92% of the supply comes from only 20% of the land mass in the upper basin. You know, much of it in Colorado, gets up in Wyoming, and then in Utah. So I think everyone in the basin recognizes the importance of that area and trying to get more supply in that area. Hence, we've been helping cooperatively fund cloud seeding projects since 2007. That we had an agreement that we entered into in 2018, but up before then, we would all just individually, you know, California 6-Agency Committee, the Central Arizona Project, Southern Nevada Water Authority, and the New Mexico Interstate Commission. We would all contribute individually to these projects, and it sort of it worked out really well, because the one thing that you probably noticed from all these presentations is these programs are all run differently. So there's not really a one-size-fits-all type of solution in order to fund these. So like some of our, like my management wanted a more streamlined approach to funding it. So the projects, instead of going to our board with some of these projects every year, we said, okay, well, let's look forward to 2026 and come up with a way to, a programmatic funding agreement. So we always emphasize that it's a programmatic funding agreement. It's not a programmatic weather mod program where everyone's sort of doing the same thing. I think that's a very important take home, is that all the states, local entities, they need to keep operating in the same way. You don't really want to put it one size fits all on there. So let's see here, go on to the next. So this is a really interesting map here. This is a map based on the reports we received from the individual states and the entities. These are all the generators, the ground-based generators. So you see they're all, and some outside the basin there. I think all of Utah's just sort of I got all their generators, not just Colorado River Basin ones. So that just shows like the cooperations that's been going on and has gone on in the past. You have Central Arizona Water Conservation District, the AKCP, something about Water 36 Agency Committee of California, Mexican Stream Commission, Wyoming Water Development Office, and CWCD, Utah Division of Water Resources. So, as stated earlier today, it's important. I think this works because everyone agrees that this water becomes system water. It's not. We don't tally up how many acre feet here, how many acre feet there. We don't also we could also make the proportional argument. It's like, well, California uses the most water. Maybe they should be paying more than other people. And I think if we started talking about that, things would fall apart really quickly. It would not work. So I think that really drives that point home, that you really need to look at this as a benefit to the system as a whole. And one thing I'm really proud of, that every year we have we meet. We have I think the process is very important. We have a technical committee that we all get together in July of the year before the operations start to meet, say, hey, here's where the states say, upper basin states entities say, here's what we're thinking of funding this year. So we get together, meet over that, figure out where that money would be best spent. You know, from the lower basin, the agreement is for $1.5 million per year from the lower basin up to the upper basin. So basically $500,000 each from Arizona, California, and Nevada, and then as DK said, that New Mexico Industry Stream Commission kicks in $20,000 for the San Juan program, and I'm glad we're doing that, because before it was sort of just 6 states doing it, it would have looked sort of weird. So New Mexico's getting their toes in the water with the weather modification and kicking in for that. So that's great that we have everything, and I'm also proud that every year we send a document around to all 7 Colorado River Basin states, get it signed. And you don't see that in too many places where we all sign this exhibit to say, hey, here's what we agree. The lower basin agrees on funding for the upper basin. So yeah, like I said, I think that the process is important to have in setting up an agreement like this. It's important to have a timeline. I think that was actually the biggest part where we were debating, is just what the timeline would look like, when we would pay, who would pay who, when we get deliverables, when we would meet on those items. That actually sort of became the longest part of setting this programmatic agreement up. So and sort of building on the success of this programmatic agreement in our technical committee, we gained the attention of the Bureau of Reclamation, the Lower Colorado River Operations Office. They have a pool of money that they have where they give out directed grants for combating drought. So normally when in the lower basin, when you think of saving water, it's land fallowing or making agriculture more efficient, or ripping out lawns as if you've ever visited Las Vegas. There's personal injury attorney commercials, and there's rip out your lawn commercials. That's what it seems to be all on the local TV, the commercials down there. So so someone at Reclamation said, hey, I'd like to see this money go towards like cloud seeding operations, which I just almost dropped the phone when I heard that, So I thought that was very, very good. And so we have SNWA was awarded the grant, and the reason for that, but the purpose of the money is to fund operations and research now, I'll talk about that in a second, in the upper basin. SNWA has worked with the Lower Colorado River Office of Reclamation a lot for grants that we get for our Las Vegas wash. It's a riparian area where a lot of our wastewater flows through for return flow guidance. So we already had a good mechanism. We had the staff set up to handle the reporting requirements, because there's reporting requirements that come with the grant. There's audit requirements that come with the grant. So they said, let's put it through SNWA, but then we will work through this technical committee to distribute that money. And so we're working at this, that's what we're working on right now, is this grant reimbursement workflow. It's a little complicated. We're working out some of the kinks in that. So basically it stays at the local and state level. I just said state entity there just to be generic, but they're contracting the work, and then they're sending the invoice up the chain to us. We get reimbursed from Reclamation and send the money back down to reimburse. So we're still, this agreement, we received the grant award back in the spring. We still haven't spent any money yet. We're looking at buying some radiometers as a first step. Looking at doing, that's what the guy at Radiometrics is saying too. Because the one thing you really have to caution with this grant money, it's almost like that movie Brewster's Millions we were talking about. You get all this money and spend it, and one of the initial concerns that came up first is like, well, we don't want to invest in a giant like aerial program or do all this equipment, and then when the money runs out, he's stuck holding these recurring operating costs. So we thought a radiometer, even though that comes with an operating expense, that would be an excellent tool to put out there. We thought, get some generators out there. And then one of the states asked, like, well, we want to start doing we didn't initially have feasibility or program evaluations in there. And so we felt that would be a good use for the money. So we approached Reclamation, and we're working on that right now to get those two items added to the grant, which I think will be a good use for that money as well. We're also, the original timeline was, the deadline to use this money was January 2025, and we thought that was, with the way some of these projects evolve, that wasn't enough time, so we were able to add another year to it. It's like we were under the impression at first that we had till 2025, and so we got another year to it, and they're like, yeah, and we're like, okay, let's do that then. So that's just, I think it's been a great success story. We're getting putting this money to work, and like I said, we got the attention of this because of the success of our cooperative funding agreement that we have. So in the interest of time, that's all I have.
You want to talk about the state of Nevada except for Las Vegas? Las Vegas is its own entity in terms of water and everything else. So we have the Nevada State Program, which basically provides water and extra snowfall for the parts of the rest of the state. So Nevada is the driest state in the U.S. We have some primary areas that are significant for the important water supplies. Number one is the Sierra Nevada. We have 3 rivers that run off the east side of the Sierra Nevada into Nevada, and they serve both farming and urban areas, and through the Truckee, the Carson, and the Walker rivers. And then out in eastern Nevada, it's out here in northeastern Nevada, there's a river called the Humboldt River, which starts up in the Jarvidge and the Ruby Mountains up here and heads out to the east or to the west and ends up in a sink out here. And so this is important ranch land and farming, and there's a few small towns. And then most of the rest of Nevada is basin and range. So every one of these are all ridges. We have, we have a lot of mountain ranges in Nevada, and they're all isolated basins. So you have all these ridges, and between each one of these ridges you have a basin, and each basin is its own thing, and no water gets out of these basins. So you have hundreds of independent basins inside the state that are isolated from each other in terms of water supply. And they include some higher ranges like these mountains here, and then down here the Spring Mountains that I talked about a little bit earlier. And obviously these mountain ranges have different storm tracks that are important to bring that moisture into these mountain areas that are, of course, up here in northern Nevada, the interior northern Nevada. We have the primary storm tracks come in from the northwest over the Cascades, but the Cascades are these isolated peaks. A lot of moisture can make it over the Cascades and around the high peaks and get in here. That drives snowfall in these locations. The Sierra Nevadas, southwesterly flow right off the Pacific. These mountains just get crushed with snowfall, and sometimes some of the snowiest mountains in the U.S. And then the Great Basin ranges in the southern part, the moisture has to get south of the Sierra Nevada before it can bring any moisture in. So the Spring Mountains in these areas, the primary storm track is on southwestern flow. So cloud seeding's been done in Nevada for almost 60 years now. Some of the scientists in Nevada, some of the first scientists at the Desert Research Institute were cloud seeders. And some of the mountain ranges, the Sierra and the Rubies, were seeded as early as 1962. There were some big federal projects. Desert Research Institute was critical, and especially in the Sierra Nevada ones. The research continued into the 70s. With lots of research programs, and the results of these research programs suggested that the snowfall was being enhanced, but at where we are today, we don't really know by how much. I think they came up with, this is where maybe the first 10% came up with. They were estimating about 0.1 inch of SWE per 0.1 per 1 inch of SWE, or 1 inch of snowfall per 10 inches. And just as an aside, this is the DRI had a research aircraft back in the day, back in the 60s and the 70s. And this aircraft actually ended up crashing in 1980 on a flight over the sea, on a cloud seeding / icing flight, killed all 4 people on board. So it's kind of one of the tragedies of DRI. And I actually gave a talk on the accident, which maybe someday I'll get to the cloud seeding community.
Is that at Twin Beach?
I'm not sure which one this is. They had one. I think this one's from the 60s.
Yeah.
I think it was, I want to say a B-22, but I don't, basically what happened is after World War II, there was a bunch of aircraft hanging around that, all these old bombers that were no longer needed. And I think if you were like a research group, you could get your hands on these, and there were some companies that retrofitted them for instrumentation. And like every scientist ever, they put on so much stuff on there that some of the ideas was overloaded with equipment, and the center of gravity was shifted back a little bit. And so when it iced up going over the Sierra, there's this weird, it's hard to get the data, but there's some evidence of like this weird up and down kind of oscillation. And then they were loaded with ice, and they came down, they stalled once, and they recovered, and then they dropped down and went above freezing, and I guess all the ice started moving, and it stalled a second time, and this time it went over where they weren't able to recover. Anyway, sorry, that's not really what I'm talking about today. So after doing these 25, 30 years of research, they came up with what they called the chain of events. And the chain of events to conduct successful cloud seeding. Cloud seeding material must be successfully and reliably produced. And we talk about that. You got to continue to have a good supply of cloud seeding material during storms. The second thing is the seeding material has to be transported into the region of the cloud that has this super cooled liquid water. We know that. And the seeding material's got to be dispersed into the super cooled liquid water so that enough volume of cloud's affected so we can grow the ice in the water drops. You can't just have like a small area with a bunch of ice that doesn't have any water associated with it, or it's not going to grow to precipitation size. So you want seed and then have that ice spread throughout the super cooled water portion of the cloud. Temperature's got to be cold enough for new ice production. And then the last thing, the new ice has to be in a super cooled liquid portion of the cloud to grow to precipitation size. So they're all the critical results of the research. And so after this research was done in 1975 through 77, there was a pretty severe drought in the western U.S. Lots of people, like older folks, like they remember this thing. And the governor of Nevada came to DRI and asked them about, well, can you guys help us out now? We're having a lot of water resource issues. Before this, everything was research. And so the state came and said, well, can you guys, if we kick you some money, can we do some operational cloud seeding? And DRI was like, sure, we'll give it a shot. And so DRI started doing cloud seeding for the state and in the right around 75, 76. And they were successful in terms of the way they, did their validation. And the program was designed using the chain of events, and everybody was pretty happy. And so that was the beginning of the Nevada State Cloud Seeding Program. The state program was considered a research/operational program, so the state required research to be done every year. It wasn't just an operational, there always had to be some type of research done. And the program continued for over 30 years. And it ended in 2009 and 10 after the Great Recession crushed Nevada's budget, and so they had to cut it. They axed the program. And at that year, the state funding was $500K per year, and the state funded everything. There was no local support, so when the state pulled the plug, it was pretty much a full-on crisis, like the program was going to go down the tubes because there was nobody else to participate. And the estimates of the state program, they were estimating between 50 and 75,000 acre feet of additional snowfall a year, and the estimate was about $10 an acre foot. Some of the accomplishments, they pioneered the remote control generator back in the 1980s, and this is some stuff that's still used today. These generators are up on the mountaintops or up on the ridges where they're in the mainstream flow above the inversion. And you don't have as much challenges with vertical mixing of the plume to get it into the proper portions of the clouds. DRI also pioneered the improvement of the silver iodide molecule. Back in the old days, they would just release silver iodide. The hope was silver iodide was just going to float around and crash into a drop and freeze it. And that wasn't that efficient. So what they came up with was if you combine the silver iodide with a salt molecule, then you get condensation on the salt, and then you have a silver iodide molecule inside the drop, so you have the ice nuclei as part of the drop, and so that's much more efficient at creating ice nucleation. And that was some of the stuff. They also pioneered the use of trace chemistry for cloud seeding validation, and I still use that all the time to this day. So after the state program ended, things got a little tough. We were able to keep the Tahoe Truckee program alive through local Reno funding. The Ruby Mountains was actually funded by the Southern Nevada Water Authority for 3 years, which they had absolutely nothing to do with the Ruby Mountains. They just were like ready state participants. And then after 2012, that was gone. And so we started diversifying at this point. We moved into Colorado and started trying to do some projects in Colorado. And we just started trying to hustle up local funding because there was nothing available on the federal level. And we limped along for 13 years, and just this past legislative session, we were able to get the state program refunded. And so, yeah, it took a lot of crying and begging and boozing down at the state capitol, but we were able to get a 2-year program past $600K. And like somebody else had already said, by this point, nobody in the legislature knows anything about cloud seeding. So they had to be fully educated. We got unanimous approval from both the Assembly and the Senate 0 no votes, which I think that's partly because the opponents were caught flat-footed. They didn't even know it was coming. So we'll see how it goes. So our goal here is to make sure we educate the legislature folks over the next 2 years and see if we can keep it going. And so anyway, we're running a statewide program again. We have the Sierra Nevada, the Rubies, the Santa Rosa Mountains up here, and then we have the Spring Mountains. So these are our project areas right now. Everything's ground-based at the moment. We're looking into this Diamond Range, which is right here. This is really got some issues with water overuse. And then we're also thinking about taking a look at this Jarbidge Range, which is not that important to Nevada, but there's some folks up here in Idaho that have run off the north side of these mountains, and they're definitely seedable. We did a feasibility study up there, so that's another area that we're kind of trying to do some research in. And then we do have matching funds. Here's all our matching partners. I'm not going to talk about that. And I also want to point out this picture here. This is a picture of rime ice. This is the stuff that's going by in clouds that isn't precipitating out. And so what we're trying to do is take the droplets that are free, that can be seen frozen on there, and converting them to snowfall, and that's where the extra fuel to create the snowfall comes from. So I'll just let that sit up there, and yeah. So anyway, that's the Nevada program.
Yeah, my name is Matthew Scudato. I'm a senior hydrologist with Santa Barbara County. I'm in no way a meteorologist. I'm a program manager for the cloud seeding program. My role is strictly to work with the contractors, the board of supervisors for Santa Barbara County. I operate out leases on private properties and kind of coordinate with 9 partners throughout Santa Barbara who help with the funding and deal with the public inquiries as well. I can't speak for all of California, but currently there are 16 operational programs. Most, as you can see from this slide, are for snowpack up in the Sierra. Tend to be funded by power utilities for hydropower, water resources, additional supplies, conservation districts, and ski areas. Our program, let's see if I can, oh, here we go. Now, my program, compared to what a lot of people have seen throughout the day, is much smaller scale in comparison. So our function and our goal is primarily to enhance rainfall in the watersheds above 2 of the major reservoirs in Santa Barbara County, North County and South County. Each reservoir holds about 195,000 acre feet. The northern reservoir called Twitchell Dam, that's strictly for flood control and very slow summer release for the recharge of a groundwater basin. Lake Achuma, down along the San Ynez target area, is primarily water distribution to some of the larger cities such as Santa Barbara, Goleta, Montecito, and there are a couple of other smaller 5,000, 6,000 acre foot reservoirs above Lake Achuma. So these are our main focus areas. We contract and have been contracting for quite some time with North American Weather Consultants. And this program has actually been operational consistently since 1981. So it's been going on for 50 plus years. And the program kind of changes each year depending on what the participants want and how much water is within the reservoir. So we can have a strictly ground-based program, which is, as you can see, these kind of round black dots. So we have about 7 operational ground sites. Or at times we'll have an airplane as well. We did have one last year. Yeah, we don't get much rain here along the Central Coast. The program tends to be operational December through March. And in an attempt to save kind of some funding, we keep the ground sites operational longer, and we just kind of focus the airplane during the months of high rain intensity, which would be January through March. This is just a graph of about 50 years worth of precipitation in Santa Barbara. It's really highly variable. And, as you can see from the last 12 years, 9 of those years were below average. Really created a lot of issues in terms of reservoir management, allocations, operations. So we try to use cloud seeding as a source of increasing this rainfall and capturing that with behind our reservoirs. These are the storage within those reservoirs. And as you can see in recent years, particularly 2017, as a result of the drought, we were in a bit of a pickle because along the coast here, really it takes 2 or 3 major storms to make or break us. Those storms, like I said, are January through March, and we try to use the cloud seeding program to help augment rainfall between these larger storms. Yeah. So, and actually to back that up, and if we're kind of lacking on allocations for our Kachuma Reservoir, say, we do end up having to pump quite a bit from our groundwater basins, which tends to cause a lot of issues for, we've been over pumping, and some basins are let's just say they've been over pumped for many years now. So within Santa Barbara, we actually started this back in 1950. It wasn't a consistent program. I know the research was done back in 1946. So within 4 years of kind of the discovery of cloud seeding, there was cloud seeding sponsored by the city of Santa Barbara along the San Ynez River. That was done for about 5 years. And we had the benefit of quite a lot of research before the Water Agency took over this program. So the state of California and the University of California did a randomized study back in the late 50s, early 60s, and the result of that research showed about a 45% increase in rainfall along the Santa Ynez. They continued to study orographic clouds and continued with the research with the help of the Naval Weapons Center in China Lake, which is actually the study that our program right now is based on. So we did have the benefit of a lot of prior research to build from. In 2015, and since we do have quite a large data set now, because this program's been going on for quite a few years, 24 to 27 storms were used and statistical analysis was done, which showed the results of that were that we're getting about a 20% increase within our southern reservoir, a 20% increase of rainfall, and about a 9% increase in our northern areas. And I know this has been said quite a bit today, and I totally support this, is continued studies and evaluation of one's program. How can we, what changes need to be made? Do we need more ground sites? Do we need to move those ground sites? Can we hit different storms to increase and improve that rainfall? So currently we're in now with new modeling and advances in modeling. We're in another study with DRI right now. Frank's working on helping us evaluate our program, see what changes can be made for improvements. And that tends to help me work with my partners and the public to show that we are getting a benefit from this program as well. So like I said, we have an airplane, we have some ground sites. The ground sites have about 32 flares. They're operated remotely. We work with North American Weather Consultants, so they operate this through actually in Salt Lake City. The flares are within these spark arresters. Really quick video. That was a test run we did a couple of years ago. And this would be a plane we have. We used a plane last year, but hadn't used one in a few years prior to that. Now, here we go. Now, we fund our program a little differently than many. Like I said, the program will vary each year depending on length, ground size. Sometimes we have to shut down certain areas as a result of fire. We've had quite a few fires in recent years. But the water agency will always sponsor 50% of the program, and the other 50% is distributed between 9 other agencies, all who benefit from the increase in precipitation behind these reservoirs. So what we do to break up the funding between the 9 agencies is base that on their annual water use and production. So they pay more if they use more. And we also now have the benefit, I know Kayla kind of mentioned this earlier, leveraging funds. We share some infrastructure with San Luis Obispo County, located north of us. We share 2 of our ground sites, and last year we shared an airplane as well. Airplane was used for Lopez Lake, Twitchell, and Cachuma. It definitely cut down our costs and the cost for San Luis Obispo as well. I did keep this short, but when I took over this job in 2016, we didn't really have a lot of data online, and I was receiving an enormous amount of interest and calls from the public. So I did beef up our web pages. All of the research is made publicly available, all of the operational programs from every year with a really good summary. And I noticed by just having this available to the public, it's definitely cut down on phone calls and my time, just allowing people to research what they need on their own.
Hi, everybody. So I'm Rachel Gray, the Water Resources Planning Manager. Not a meteorologist, but this has been a great experience for me in learning about it. So our program is 1 day old. It literally kicked off today. So we're pretty excited about that. So next slide, please. So just a little bit of an overview. We conducted our feasibility study back in 2020 to determine, if implementation of a program would be economically and technically feasible. We also contracted with North American Weather Consultants. They're operating our program. It's a 4-year pilot program. And so in the Santa Ana River watershed, our target areas are the mountain areas that you see in yellow here that drain into our watershed. We have the Santa Ana River as well as groundwater basins. So we're hoping that this can be, sort of an addition to our water supply strategy for recharge and supply in our basin. So, sorry. Okay. So sorry. One more thing on the previous slide. I just to reiterate, validation is critical for us for our pilot program because the results can then help, to advance a long-term program for us in our watershed and then communications as well. So next slide, Kayla. So just funding. So SAPA itself is a joint powers authority. And so we have 5 member agencies who are funding our program together with 8 additional agencies within our watershed. Next slide, please. We also applied for Proposition 1 grant funding from the Department of Water Resources, and we were able to secure about $860,000 for the 4-year program as well. Next slide. So just a summary, we have 15 ground-based seeding sites or units. We have 11 sponsors. You'll see the green are the CNGs. We have 1 remotely operated CNG and then 3 automated high output ground seeding units in our watershed that we're utilizing. No aerial seeding is being done for our watershed. Next slide, please. So consistent with my previous sort of discussion on CEQA, the findings for us were a couple of biological mitigation measures related to, conducting a biological survey 10 days prior to the installation of the equipment, as well as just being aware of the nesting season. We were outside of the nesting season, so that was okay. And then also if there's any cultural, fines, and then we had to develop an unanticipated discoveries plan as well related to tribal cultural resources. Next slide, please. So just, in advance of installing our our units, we wanted to conduct a preliminary biological survey to ensure that the locations where we're going to, install the units, there were no issues with sensitive, species or flora, fauna. So we did an initial biological survey in late July, and so there were no significant findings identified. Next slide, please. Fast forward, just to comply with that 10 day in advance of the construction, we completed our final biological survey. Again, no significant findings, but we wanted to minimize the risk when we were going to install the units. Next slide, please. So just our project team, SAPA, our operators are back up. Not North American Weather Consultants, they're operating the program, and Frank from DRI, he's going to be helping us with some validation over the 4 years of the project. Next slide, please. So we developed an operations plan. And just because it's a new program for us, we wanted to make sure that, we had an externally and internally facing document that we can share to sort of outline like, hey, here are our operational criteria, here are suspension criteria, so on and so forth. And if you go to the next slide, Kayla, it'll kind of describe some of the information that's in our operations plan. Like I said, when are we going to seed, when are we going to suspend, and how are we going to communicate? Next slide, please. So these 2 slides is just like a schedule that was developed. I'm not planning on going over it, just with the installation schedule and coordinating with all our site sponsors. So it took some work and coordination, but we got it done. So next slide. Next slide. Thank you. And then, just key timeline. So we conducted our preliminary biological surveys. We had to do a 45-day public notice of submission. And then we had our equipment set up, operator training, and, you'll see November 15th. It's actually, I don't know. It's great that we're having our workshop on the day that our program's starting. So it's kind of momentous. So like I said, day 1. Next slide, please. Again, we're partnering with Frank and Desert Research Institute, and just the validation for us is key, like I said, for implementation of a long-term program. And so, just the purpose is to verify, the deposition of silver iodide, verify any increases in precipitation and stream flows, maybe associated by target areas, so we can see maybe long-term who could also contribute to funding this program. And then just, independent review of North American Weather Consultants, like their operation and the suspension criteria. So that's critical as well to the success of our program. So next slide, please. And again, we're just using some, verifying the silver and the snow before and after seeding, as well as the target control methods for 2 areas. Next slide, please, Kayla. So again, it's just critical. Communication is critical for us. I mean, it's been day 1 and I've gotten probably like a handful of emails already like, hey, are you guys seeding? And it so happens that it's raining a little bit here, although it's not conducive to cloud seeding quite yet. So we're monitoring the conditions. Just all the different mechanisms, whether it's our website or, facts, FAQs, or just different outreach mechanisms, just making sure that we have information available. We set up a special weather modification email address, and then so the public can send us questions. So just making sure that we're transparent with communication. Next slide, please. Yeah, and then just our general program schedule. So we're currently on day 1 of our 4-year pilot program. So excited to be part of this group, and thanks for having me.
Since you already heard from me earlier about some aspects of our program, I'll keep it short. I've got a lot of questions recently about how we determine who our partners are, how we identify who the partners are, and then how we determine their contribution to the program. So Utah's been cloud seeding for a long time. There were early experiments in the 50s. In the 70s, they passed the Cloud Seeding Act, which gave the Division of Water Resources authority to permit cloud seeding. And that's what we've been doing ever since. So part of the procedure, these are the local sponsors that we have. There's a range of water conservancy districts and public utilities, county governments, private companies, and these agencies contract directly with the cloud seeding operator. So they're the ones who are interested in cloud seeding, and if there's a drainage basin that's being targeted for cloud seeding, and there's more than one of these, they determine amongst themselves how they're going to divide the costs of. So, for example, Salt Lake City Public Utilities, they're the only ones that participate in the Six Creeks program, and so they contract with the operator and they pay the full cost. Whereas we have some that have up to 3 of these partners. And so then what I do is I inquire every year the interest of potential sponsors in participating in the state program, which is a reimbursement program. So our reimbursement is a 50-50 split up to a certain amount. So we say we will we'll contract with you to reimburse your cloud seeding expenses up to a certain 50% up to a certain amount. And then there are 2 operators. There's one private company and then one water district, and they have to go through the public process. They have to demonstrate the proper insurance, the proper expertise in order to obtain a license and a permit. And then we monitor for suspension criteria throughout the year. At the end of the year, we reimburse the sponsors and then hopefully celebrate a massive snow year. These are the areas where we target. I already went over the sponsors, local sponsors. We also have regional sponsors, which has been covered. Those are agencies in the lower Colorado River Basin. They pay for a number of things: extensions, seeding in some areas where we have no local support. They provide funding for instrumentation and also research. Okay, so then this is a table of the water budget and the statewide program. So you can see there I have the areas, the target areas, and then each of the local sponsors. And then you can see there's a breakdown between the board, which is the Board of Water Resources for the state, and then the sponsors support. And that's approximately 50-50. Then there's a total for Utah, and then there's the contribution from the regional sponsors. And so all these activities come out to about $800,000 per year. That changed last year when the state invested a considerable amount of money. They increased the budget to $5 million and gave us $12 million in one-time funding, which is an incredible amount of money that we're not able to spend responsibly. And we need time in order to plan and implement these things. So here's a timeline of how the cost breakdown has been since the Cloud Seeding Act was passed. You can see gray there is the state portion, blue is local. You can see that the cost share percentages have varied over time. Then you can see in 2007, we signed the programmatic agreement with the Lower Colorado River Basin entities. That's in green. And then you can see last year how the increased budget led to quite a dramatic increase in statewide expenditure. And so those expenditures came from implementing 2 aerial programs, well, 1 pilot program, actually not 2, 1 pilot program, and then purchasing and building remote generators and conducting some other research to identify areas that are not currently targeted, but seedable conditions. Okay, so then the way that we do our cost benefit in using regression techniques, which have been mentioned, which are simple and rather inexpensive. And the last study we did in 2017 gave an estimated increased runoff through all of our programs of 186,000 acre-feet. And given the cost, it came out to about $2.40. Those, I think it's a bit underestimated. We're undergoing this study again to update these numbers. But importantly, we don't, because in our statute it says that augmented precipitation is treated as natural precipitation. And so that resolves a ton of conflict. So because of that, we're not really interested in knowing how much of the water that augmented precip that falls as snow becomes runoff, which then gets to a certain reservoir or a certain gate. We consider any additional water natural, and it becomes system water. So it's a benefit to the watershed. It's a benefit to everyone in the system. Kayla showed this earlier. You improved this quite a bit because this doesn't mean anything to people here. It means something to people in Utah. But we have the state agency regulator. We have a private operator, and then we have a public university research organization. And so the relationship between these three is very important. So so I'll leave it there.
Okay.
Okay.
Thanks, Jake. And Kayla Golden, State of Idaho. I'm going to give sort of a high-level overview of our program, hopefully some of the stuff that you hadn't heard about yet today. So water management in Idaho, this is sort of key to understanding how the funding works here. So in Idaho, we have the Department of Water Resources and we have the Water Resource Board. And so our department, on one hand, is really responsible for all your water rights licensing, hydrology, groundwater, stream channel protection, sort of more of the regulation side of water. The Idaho Water Resource Board, on the other hand, is responsible for the state's maintaining the sustainability of the state's water supply. And so that includes formulation and implementation of the state water plan, implementation and financing of large water projects, and operation of programs that support sustainable management. And that includes our cloud seeding program. And so the Idaho Water Resource Board does have regular appropriations annually, and our cloud seeding program is funded out of the board's annual appropriations. This is just a high level of our agency. So the Water Resource Board, by contrast of the department, doesn't actually have its own staff. So it is an 8-member appointed body made up of no more than 50% one political faction. And so because they don't have their own staff, the department, in fact, has a directive to provide that staffing for them. And so while I am department staff, our primary role is to carry out the missions and goals of the Water Resource Board and the Planning and Projects Bureau, which is where I fall. So overview of history, overview of cloud seeding in Idaho. Like some other states, cloud seeding has been going on here intermittently for quite some time, about since 1950. But really it hasn't been consistently going on until about the late 90s. And so in eastern Idaho, you may have heard Sean talk about earlier, we have some manual programs that have been operational over in eastern Idaho since about the late 90s. And that program over there is 100% funded by local stakeholders. So we're pretty proud of it. It's a very unique program. They've been able to get by since the 90s on local funding. And this is actually the first year that they have made a request to the state for some level of funding to support their program. Idaho Power, as you heard from Sean earlier, they've been operational consistently since about 2003. And then where you're seeing some of these blue dollar signs, I don't know if you can see my cursor here in some of these years, that's where the state has really come on board and started funding. So really the state has only been participating in cloud seeding, for the last 7 or 8 years, at least from a financial perspective. And so in Idaho, we have what we call the Collaborative Cloud Seeding Program. And what is that? So the Collaborative Cloud Seeding Program is that 3-legged stool that I talked about earlier. So we have the Idaho Water Resource Board, who is the state agency charged with cloud seeding. They also provide funding for cloud seeding in Idaho. Idaho Power Company, who operates the program, are program experts. And then local stakeholders and water users in the basins where we operate who provide funding as well. So Idaho Power operates the program, and then the state and local water users provide the funding. And that currently includes 4 basins, the Boise, the Wood, 3 basins in the collaborative, Boise, the Wood, and the Upper Snake River Basin of Idaho. And then the Payette River Basin is the basin that Idaho Power started independently. They still operate, manage, and fund that basin independently. But it is done in collaboration with the other basins. So a high-level history of our program, as Sean talked about the inception, the stakeholder or shareholder question that they got that really kicked this off. in the 1990s. They started their first operational program in 2003. And really, the state came to the table, not in terms of funding, but came to the table to start talking about participation in cloud seeding in 2008. And this was a result of what we call the ESPA CAMP, or the Eastern Snake River Plain Aquifer Comprehensive Aquifer Management Plan. And so Idaho actually has one of the world's most productive aquifers, one of the largest in the United States, and that is primarily where the agriculture in our state lies, is over the ESPA. And so a brief, very high-level history that kind of puts this into context. We started irrigating across the ESPA, in the early 1990s, and through flood and surface water. And so what that did was actually artificially charge our aquifer. And then about the 1950s, when pumping came online, we started to see a decrease. So it's sort of a perfect bell-shaped curve with charging of the aquifer from incidental. Pumping came online in the 50s, and then we've seen a decline. And so that has been something that our state has been heavily trying to attack, is the decline of the ESPA aquifer, because it is very critical to our economy. And so because of that, the Water Resource Board and the state came to the table during that planning back in 2008, and Idaho Power proposed to put on a 5-year pilot project in the Upper Snake Basin, which is primarily what contributes to the ESPA. And so the thought was, we'll put this 5-year pilot project out, and if it's successful, then the state and water users would come to the table to start providing funding. And so that's exactly what happened, and they were successful, and that project is still operational today. So between that time and between the state's participation, water users in the Wood and the Boise River basins came to the table and asked Idaho Power Company to partner with water users in the basin and begin projects in those basins. And so those kicked off in about 2014, 2015 time, which is about the first time that the Idaho Water Resource Board, or the state, made its first contribution to funding in cloud seeding. And that was done with an initial contribution for capital funding, about $500,000, that was used for generators to build out our program. 2016, so we made some changes in how the board was funding. So we started with funding a little bit of capital. 2016, we started contributing towards operations and modeling. At the time when we first came to the table with that, the idea was, we'll split it 3 ways. The state will pay a third, the power company with interest in hydropower will pay a third, and water users will pay a third. It hasn't quite panned out like that, and I'm not going to get too much into that. I will touch briefly on some of those challenges. But 2019 is essentially when we reached our existing level of build out, which consists of 3 aircraft, 57 remote ground generators, and a network of weather instrumentation. And so this is the map that I did show earlier. Again, we have our West Central Mountain region over here on the left-hand side, the Payette River Basin with this kind of long fork in the top, the Boise in the middle, and the Wood over here. And so each of these basins in this region share generators both on the divide, and they do have generators that independently support their basin. And then we have an aircraft, one aircraft between the Payette and the Boise, and another aircraft that is split costs between the Boise and the Wood River Basin. And so water users across the Boise and the Wood River Basin each share costs for some of those operations, and as well as share some of the costs with Idaho Power for the aircraft that is shared as well. Over in East Idaho, these green dots that you're seeing is the manual generator program that I talked about, the High Country RC&D program that's been operational since the 90s. And they've done so, again, just on localized funding. So this year is the first year that they have reached out and asked for state support, and we're working with them right now to figure out what that looks like moving into the future. Some photos of our aircraft. You've seen some of these photos today. We do have only the collaborative program anyway only operates remotely operated ground generators, and these are ground generators that have been built, developed, maintained, and ran since the inception of the program. And so Idaho Power has built and developed these. They've made improvements upon these, and we have about a good 20 years worth of data running these types of generators and making continual improvements. So here in Idaho, we're pretty proud of the generators that we have, and I think it would be our state's goal to move forward with the same type of infrastructure. But we are, as you heard from some of our presenters earlier, there is a very limited resource in terms of cloud seeding infrastructure and operators. And so one thing our state is challenged with right now is moving into other areas of the state where the power company may not have interest, how are we going to support that infrastructure potentially from other vendors or operators. And so we do run aircraft as well. Pictures of those, you've seen a few of these already today. Weather instrumentation, I'm not going to get into this. We do have a pretty full network of weather instruments across all of our projects to support accurate forecasting and analyses. Like all other programs, we do have guidelines for our program operations. We do conduct our annual ground schools for planning, and we are supported by a team of atmospheric scientists 24/7 around the clock from November 1st until about April 15th or the 31st for aerial. So high level, this is sort of the juicy information that everybody always wants to know of our West Central. I'm going to show you both our West Central Mountain Project and the Eastern Snake. And so you heard from, during the monitoring and analysis, primarily the speakers that you heard from were from Idaho, and that's largely because we're really the only state who has taken the evaluation, at least in depth, beyond the target control or beyond the precipitation measurement. And so I'm not going to get into how we do that, but these are some of the estimates, that we've come up with and the cost to operate these programs. And so the Boise River Basin, this is on an average annual basis that we're estimating in CAF, or 1,000 acre-feet of water on an average annual basis. And so this is averaged, over the time that the project has ran. This is not necessarily, the exact amount of water that you'll get in every single year. Just like the water year, we have good years and bad, but on average, these are the numbers that we see across these basins. It's about 273 in the Boise. The cost for that one is about 910. Theirs is a little bit higher because they share 2 aircrafts, one with the Wood and one with the Payette. The Wood River Basin, they don't have quite as much infrastructure here. Going back, so that program, it does have a little bit less, and it does cost a little bit less. Payette River Basin, we do have some numbers in here for reference as well for what Idaho Power estimates they get out of the Payette and their cost for that. Upper Snake River Basin projects, these ones are a little bit bigger. Geographically, the Upper Snake Basin project is similar in size to the entire West Central Mountain region. So over in the Snake River Basin, we have about 25 remote ground generators and a single aircraft to target the basin. This is definitely a basin where we've contemplated adding some additional aircraft, and we still kind of have that on the table, funding dependent in the future. But overall, our estimates for what we get out of this basin is about 632,000 acre-feet on an average annual basis. And so this program, collectively for all of the generators and the single aircraft, which they don't share costs with. So that's one of the reasons why you're seeing a significantly increase in cost on the Snake, is because they don't have other basins to share this cost with. So that is just absorbed between the state, the power company, and those local water users. They don't have leveraging funds to share. So I'm not going to get into this. This was just a high level of target control we've already talked about. This is a quick snapshot, though, of our target control estimated increases. So the Payette is our longest running project that Idaho Power has, so that's the place where we have the most amount of data. But on average, you can see across the state, we generally maintain close to 10% of an average annual increase across all basins. So summarizing that for the collaborative program, current cost of annual operations, and this does include Idaho Power's cost for the Payette, and then the total average annual runoff generated. So about 1.2 million acre-feet on an average annual basis. That's a pretty significant chunk of water, that we're, and this is across all state, or across the state, so all basins. But when you put that into the cost benefit, $4.2 million for 1.2 million acre-feet, that roughly pans out to, $3.50 an acre-foot, which is pretty cheap water across the West. So when you're looking at a $4 million program, yeah, that's pretty expensive, but the return on water that we're estimating and for how critical water is, that's pretty valuable. So current priorities for the collaborative program, like I said, the state has really come to the table very recently. So while our operational program is very much state of the art, the state as a public agency is very much in the infancy of developing, sort of the administrative side of the program. So we still have a lot of things to figure out from the administrative part. And I would say our current priorities are one, what is the state's role? What are we going to fund? What is the state's participation going to be in the long term? And what is going to be the long-term role of stakeholders? We talked about collaborative agreements, doing longer term versus year over year. We want to see longer term commitments. How is the program going to be funded long-term, and who are we going to create those agreements with? Assessing opportunities for program expansion or enhancement. So this was a directive that we were given, and I'll talk briefly about this from legislature a couple years ago. But we were directed to assess opportunities for program expansion and enhancement. And so one of the other considerations is how can we grow and be more effective? So we definitely have other basins across the state who are very much in need of water and would like to see cloud seeding. But the state is really trying to take a step back and develop a structure for the existing projects that we have that have been operational for quite some time. So most of you know, developing a state program is no short process, and developing a cloud seeding program is not really one that we have a how-to manual on how to do, as you've heard from us today. Every program kind of does it a little bit differently, and that's because our challenges are differently and our water needs are different. And so ongoing monitoring and analysis is another thing, we've talked about today. How will we ensure the long-term effectiveness of the program? So this is a quick snapshot of the timeline. This is relative to the state's participation. So I talked about the ESPA camp was really when the board or the state first came to the table. This shows when our projects kicked off in the Upper Snake River Basin. The WRF weather mod, I will briefly talk about. So this is something you heard about quite a bit earlier in today's talks from NCAR and from some others. So our state has contributed a pretty significant chunk of funding into developing out this model to support our program. And that really kicked off in 2011, initially funded 100% by Idaho Power, and the state has been funding about 50% of that model development since 2017. So I have a star here that really just shows the state's participation coming on about 2014 compared to when our programs have started. Some of our capital costs, that started about then when we started paying for operations and maintenance. 2017, we started paying for model development. And then the blue ones that you're seeing down here are individual projects that are either currently going on or we have done. The modeling, I'm not going to get too much into this, you've heard a lot, but sophisticated modeling is really necessary, or we've deemed it very necessary here in Idaho for planning and development, forecasting, guiding operations, and analyses. So I'm not going to talk too much about these models, but the one thing that I will say is, as Mel alluded to earlier, if the state of Oregon comes online with a cloud seeding project, that pretty much eliminates our control sites for being able to evaluate our programs, which is a pretty big deal because as a state or as a public agency, we have to be able to demonstrate a cost benefit to using these public funds. And so we have to have some sort of a mechanism to evaluate our programs and be able to respond, to our use of these public funds. And so modeling is really kind of the next frontier of the cloud seeding program and how we answer some of those questions. So I think that's really critical. I'm going to skip over some of these modeling. Real briefly, I do want to touch on some of the funding. Again, I mentioned Idaho Power did start some of the funding for this, with the state coming on later. Our initial development cost that the state, between Idaho Power and the state, have put into this model is about $5 million. So that's a pretty significant chunk, that we've contributed to this cloud seeding model and the development. We have currently, as of a couple years ago, we are doing ongoing model development. As models are never done. I'm sure you've probably heard that about every model. But you did hear from Dr. Tessendorf and a number of others that there is still a lot of improvements that need to be done to ensure the accuracy of these models. And so currently, the state and Idaho Power Company have each split costs for about $2.5 million. And that's in addition to a $300,000 Water Smart grant that we obtained. And what this work is doing is taking data from Snowy, so the field effort that you saw with the radar, the zigzag patterns, and using that data to update and validate the model. And so that's necessary continued work that needs to happen, and we are contributing funding to that as well. This last July, we are looking at expanding our projects into some other basins. We currently do have some feasibility and design going on. So we have contributed additional model costs to develop out the model for some of those basins as well. One thing that we didn't touch on, though, today with the modeling aspect, that I think is very critical and we're figuring out as a state is lots of modeling means lots of computing. These models need a lot of computer power to be able to run these multiple simulations, multiple ensembles. And so you can't just run this on your desktop computer. These things require significant supercomputing space. And so back in 2019, the state and Idaho Power partnered with Boise State University and the Idaho National Laboratory for purchase of a large computing system. Our capital for that was about $1.47 million. Annual administration, so that cost to keep this computer running is about $8,000. We split that with Idaho Power Company. And this computing resource is used for both our cloud seeding operations, but for research as well. And so what we've found out very quickly over the last several years is our program has rapidly grown, and we've started doing all of these analyses and evaluations, is that we outgrew that computer very rapidly. And so we are currently looking for other resources that may include cloud-based, potentially a new, more computing equipment or lease space on other computers. But I think this is something that all programs should be very mindful of. If you would like to get into the modeling aspect to better be able to evaluate your programs, you absolutely need to think about the computing aspect to be able to support those models. You have to have something to run them on. So in some of our talks today, we talked about, how to, the modeling, or the monitoring and analyses portion. And we talked about, some of the components of how do we evaluate cloud seeding? How do we know how much water we're generating? And what does that translate to in water on the ground? And so you heard from Mel, this is sort of my diagram of how this works. But the state of Idaho, about 3 or 4 years ago, started on what we're calling a cloud seeding impacts analysis, because we have been asked this question by lots of folks. Our stakeholders contribute to this program, and they want to know, well, what's the impact? How is this benefiting me? And so we tried to take a stab at answering this question. And so our objective for this project is to estimate, roughly how cloud seeding operations impact hydrology in the Piet, the Boise, the Wood, and the Upper Snake River basins. So our first cut at this, it took about 1.5 years. It was a very high-level, simplified analysis. It did not include, some of the significant modeling advancements that we've heard today. And so because of that, and because we didn't have, a high level of certainty in some of those results, the board directed us to start phase 2, or, a higher or a more in-depth evaluation for this. And so that part of it, it does involve the more detailed modeling. And so really what that looks like is currently, we're taking target control, which is the only resource we have now. I think you heard from Dr. Tessendorf and some others, that there's still a lot of improvements that need to happen to models to be able to use them for evaluating the precipitation. But right now, we use target control. So essentially how this works is we figure out how much precipitation was generated, and then we plug that into how does that translate to water on the ground. And then the third aspect of that is, okay, well, you have X amount of acre feet that translates to on the ground. Now, where does it go in the system? And so to do that, we're using a Riverware. This was the last presentation that David Hokema talked about, an operational or a regulatory model. So the Riverware is actually a planning model that was developed by the Bureau of Reclamation for the Upper Snake system. And so what we've done is take this Riverware model that was meant for planning purposes, but it very much captures all the regulatory aspects. And so we've been making improvements to it so that we can take that target control. How much precipitation did we increase? How much water does that need? And we can run it through the system and sort of see where that increase in supply pans out. And so that's a project that's been sort of ongoing. We're learning because the tools are really still under development to be able to do an analysis like this. So we have learned a lot, and there's a lot of good takeaways. And we're very excited to finally be presenting some of these results to our board here in the next couple of months. But the next, as I mentioned, this is an ongoing type of analysis, and largely because the tools are still under development. And so really the next phase or the next frontier of this analysis or being able to evaluate cloud seeding is to get away from the target control and use something like the WRF weather mod or the cloud seeding model to generate or better generate that precipitation for us. So again, as I mentioned, for us here in Idaho, we're very excited for folks over in Oregon at the prospect of getting cloud seeding online. I myself am a native of Central Oregon. My family were irrigators, so it's very much near and dear for me to see them get a project off the ground. But unfortunately, what that means for the state of Idaho is that we will lose our control sites for evaluating our program, as I mentioned. And so the next frontier for us is going to be moving away from target control analyses and using WRF weather mod to be that first input for the precipitation generation. And so largely, right now this evaluation is targeting our existing basins of operation, but ultimately we'd like to be able to use this resource to evaluate other projects as well. And as well, the Riverware model, the planning model, still has a lot of improvements that needs to be made in it. Things like reservoir operations, some of our groundwater responses. We have some pretty cool groundwater models here in Idaho, but they've had some upgrades recently. And so, making all those transitions, improving the diversions, looking at flow augmentation, recharge. There's a lot that goes into the development. So legislation, this is a pretty key piece for the state of Idaho. About 2 years ago, the state of Idaho, under House Bill 266, this was the first time that we had legislation that really created a state agency that's responsible for cloud seeding and gave some directive to that. And so House Bill 266 directed the board to continue the analysis of cloud seeding projects. So the analysis that I just mentioned, it directed us to complete an assessment of opportunities for cloud seeding in other basins, knowing that there's water users across the state who would like to see support. And it also gave the Water Resource Board the authority to authorize cloud seeding programs in Idaho. And so in Idaho, we don't have any licensing or permitting, and it's actually specifically stated in our legislation that permitting and licensing is not required. In lieu of that, you have to obtain authorization from the Idaho Water Resource Board. And so what does that mean? Well, this happened 2 years ago, so we're still kind of figuring that out, what the authorization means, what is the state's role, what should the regulatory mechanisms be. And so right now, what an authorization means is really just a reporting mechanism for us to track, what some of these operations are doing in our basins. And so we came up with some criteria to obtain an authorization that basically includes, a detail of what the project is that you're operating, what type of materials you're operating, when you operate, and it requires annual reports, as well as a requested update for authorization if there is any changes to the program. And so this year, for example, Idaho Power Company is putting some liquid propane generators in their Payette River Basin project. That would be an example of something that would trigger, a need to get a new authorization. But otherwise, those authorizations are currently indefinite. I'm not going to cover that again. The statewide assessment, this was something we contracted out to NCAR. Basically, what it did was just take a high level of the state and look at all of the areas that have high frequency of seeding opportunities. And so that's the coloration that you're seeing in these maps. On the left-hand side, we have a map of seeding opportunities for the ground layer, so the 0 to 1 kilometer, and then for the airborne seeding layer on the right, in the 3.5 to 4.5 kilometer, which is based on our safe mean flight level. Feasibility and design studies. So you heard folks talk about this earlier. So in the state of Idaho, we kicked off the Bear River Basin study a few years back. That was completed last December, and we actually just finally presented that to our board here in September with the final results. And we are currently working with the state of Utah and potentially the state of Wyoming to look at potential partnerships in the Bears. That is a tri-state basin. So again, going back to leveraging funds and collaborations, that is very critical. And so the Bear River Basin is one project we are hoping to get kicked off next. But again, we have a lot to figure out as a state agency for our existing projects. So that really is our focus mainly right now. The other basin that we've kicked off for feasibility and design is the Lemhi River Basin. The Lemhi River Basin borders the state of Montana, who has also just recently gotten funding for feasibility and design for a project just across the border. So we have also started conversations with the state of Montana about potentially sharing infrastructure between those projects, which would give us the ability to leverage funds between states. So leveraging funds, I cannot stress enough, is probably the most critical to being able to fund sort of the gold standard of a program. Some research and development efforts. I'm not going to get too much into these, but we have kicked off some research efforts on liquid propane as a possible alternative to cloud seeding. So you've heard earlier from some folks, liquid propane has a warmer, it can seed or nucleate ice at warmer temperatures. So as the climate continues to change, this may be an opportunity for us to enhance our program. It's also cheaper to operate, so that's another consideration we'd like to think about. So we are currently working on a proposal to potentially get some support from the state of Utah and some other funding participants, because we definitely recognize that we are not the only ones interested in this research. Although I think the state of Idaho definitely feels like we've taken on, a pretty significant chunk of the funding in some of this. And so we are currently looking for collaborative partners, to support us in some of this research as well. On the instrumentation side, we've been working on the development of what we are calling a SWEDAR device. This is meant to essentially be a micro SNOTEL. So implementing SNOTEL sites are very, very expensive. It's also a pretty lengthy process to get SNOTEL sites in. But we really need that data to be able to efficiently evaluate your program. You really need those data points. And so because it's so expensive to get SNOTEL and because of the need for data, we've been looking at developing these micro SNOTEL devices. And we did finally get a prototype out that's being deployed this winter. So we're really excited to see how that does and potentially get these implemented to our project in the future. So I'm just going to wrap up here really quickly with our budget. So we do have a pretty sizable budget. Like I mentioned, we started in 2014, 2015 with a $500,000 contribution. So that's a pretty significant change in the last 5-7 years to go from 500,000 to 7 million. And that's because we've had some great support in our state for cloud seeding, and we've been able to, maintain these collaborations. So, our board funds this year we're funding about 2/3 in total of the costs for our collaborative program. Some of the water users in those basins will be expected to pay some of that as well. And the other 1/3 of that is paid for by Idaho Power Company. So we did set aside, again, money for instrumentation, for the modeling that I've spoke of, that's pretty significant, and some potential funding for new infrastructure. And you will see that we do have, a good chunk of money set aside for research and development as well. So this is the last one I'm going to wrap up with. Again, our program priorities. These are basically everything I talked about before. What's our state's role, the role of stakeholders, securing those long-term agreements, ensuring that we have somebody to operate and fund this program into the future. The next step beyond that, once we can figure out the structure and the collaborative agreements, is assessing opportunities for expansion or enhancement. So how can we support other areas of the state? How can we continue ongoing monitoring and analysis to ensure that we're being effective?